Hello, everyone. Welcome to our very first workshop on large language models for cross-temporal research. My name is Wei Zhao. I'm an assistant professor at the University of Aberdeen. We know many of you attend from different time zones, so good morning, good afternoon, and good evening. First, I will give a short introduction to our workshop, why we want to organize this workshop, because we see many applications of large language models in temporal context. For instance, in the NLP domain or the wider AI community, we see large language models for temporal reasoning, forecasting, and planning. We also see large language model have been used as instrument for temporal studies in scientific domains such as literary studies, social science, and so on. But we must be very careful about large language models because they are inadequate for understanding the concept of time. Why? The first issues of large language model is they have temporal bias in the sense that they understand the content in modern time period much better than the content in the distant past. Second issue is large language models struggle to understand the time-sensitive knowledge. For instance, the knowledge observed in the pre-training corpora may potentially evolve into a new concept in the latest corpora, which is unseen during pre-training. The third issue is that the large language model, in particular, their tokenizers, are not designed for understanding dates. For instance, the tokenizer like BP tokenizer will split the dates into meaningless subtokens. For these reasons, we believe it's a good time for us to organize such a workshop, and we hope our workshop to be a forum of discussions on the latest advances in cross-temporal NLP as well as their applications. And we look at the two research themes, and each themes we include several topics here, but these topics are not claimed to be comprehensive because our community is constantly evolving. So we invite you, for example, if you have some good ideas, good topics that which you see is not listed here, please contact us. We are very happy to include your contributions. For example, update our workshop website to include the new topics. So let's say the first research theme that we have in mind is cross-temporal large language models. This is because as an NLP person, so the core, this is like the core research theme in NLP. So the first topic could be potentially develop novel benchmarks for temporal evaluation. Second topic is to develop the novel method to ensure the large language model are temporarily robust. Then data analysis, for example, could look at the distribution of the pre-training corpora across different time periods and the conflicting knowledge in the pre-training data and in the recency data. But nevertheless, there's another topic. For example, we can treat like cross-temporal as one of the many popular aspects, blending into, for example, cross-temporal and cross-cultural aspects to offer a multifaceted view of studies in NLP. Now, then the application of the large language model in temporal context, so which include temporal reasoning, forecasting, and planning, then the application in scientific domains in the temporal context. But we must be very careful about the results. For instance, if the large language model are used to support scientific findings in the temporal context, but we see there's quite a bit limitations of large language model, like a temporal limitation of the large language model, so you must be careful about the scientific findings. Who are we? I'm Wei Zhao. I'm an assistant professor at the University of Aberdeen in Scotland. And Maxime Pirard is junior professor at the university.
of Grenoble Alps and CNRS in France. And Katja Merket is a full professor at the Heidelberg University in Germany. And we have a great lineup of invited speakers. And Rosa from Cardiff University, who is a full professor at the Cardiff University in Wales, and Ali Amami is an assistant professor in the US. From Emory University, then we have Alexis Huet, is a senior research scientist at Huawei in France, and Bahar Fatimi is a senior research scientist at Google Research. And lastly, we have Vivek Gopata and from the US who is assistant professor at Arizona State University. We are very grateful for the sponsorship from the Artificial Intelligence Journal to support our workshop. The schedule here is basically we have 5 invited talks and 8 selected oral presentations. And the program details are available at our workshop website. The last slides, I would like to present the topic cloud, and based on the 12 accepted papers, we're looking at like the topic of interest from the paper authors, and we see the popular topics like include like reasoning, temporal forecasting, biases, historical event time, books, and so on. Okay. Then thank you very much for participating in our workshop, and hope you enjoy the event. Now let's move to the first keynote session. I will stop sharing.
Hello. Can you hear everything fine?
Yeah.
Okay, I will try to share the screen. Can you see now the slides?
Yeah.
Okay, so yeah, shall I get started?
I can give a short introduction.
Okay, that's great. Thank you.
Rosa is full professor at the School of Computing Science of Cardiff University. He's also a UKRI Future Leader Fellows. He co-founded the Cardiff Natural Language Processing Group, and before joining Cardiff University, he did his PhD at Sparhinaz University of Rome and was a Google AI PhD fellow. And his major areas of research include the semantics, multilinguality, and computational social sciences with an interdisciplinary perspective. The floor is yours.
Yeah, that's great. Thank you for the introduction. And thank you so much for the invitation. I'm sorry I couldn't be also called in person, but I'm very grateful that I've been invited. At least I can contribute, even if it's here from home, as I am now. So yeah, I'm very interested in the topic of this workshop. I've been working also on temporal kind of application. I'm mostly more than working in the temporal issues of models. I mean, I encountered these problems, as I will tell you during my lecture. I mean, I was working on other problems, and then in order to solve them, the models needed to be kind of temporally aware, and that's why I started working on that. Just a bit about me, but yeah, we already kind of presented. So yeah, I work at Cardiff University. I'm here in Wales, in Cardiff, in Wales, in the UK. And yeah, I'm interested mostly in NLP and lately also in the intersection with computational social science. That is also a bit of the topic of the talk today. And yeah, this is kind of some keywords that I put here: semantics, resources, multilinguality, social media, but anything related with NLP or obviously nowadays language models. and application basically to language, I will be most likely interested, and probably I will work in many kind of topics, related to NLP. So this is the outline of the talk. It's going to be a very simple talk. I was thinking about what to talk about, and I was not sure. And I saw anyway, the program is very interesting, with the oral presentation and the other invited speakers, which I'm sure going to be much more interesting than this one. But yeah, I wanted to keep it short because also it's the first talk in the morning. And to keep it something that is simple enough with a clear message that at least maybe some of you are familiar with, and it's something of the topics that Wei was mentioning at the beginning of the workshop presentation. So I'm going to talk a bit about social media because probably not all of you work on that. So I'm going to present you the domain and some of the challenges on social media. And that's one of the temporal challenges. That is how I started working on this. That in order to solve many problems in social media, you will have some mismatch between the training data and the test. That's kind of the main theme of today's talk, and I kind of other temporal problems as well. But I'm going to focus mostly on that today. By the way, if there is anything, feel free to interrupt me, or if any has some question, please stop me. I'm not checking in the chat or anything, or I don't know if I can hear. So yeah, feel free anytime. The motivation. The problem of language models is obviously they are going to have a cutoff date. Once you train them, and the training involves many steps. I mean, not only pre-training, but obviously there is a lot of work now on post-training as well. But no matter how you do it, you will have a cutoff date, and then updating the language models will be very expensive. And sometimes doesn't depend on us, because I mean the language models are developed mostly by companies or by large labs. So I mean we rely on kind of the language models that are available at the time. And because of this, I mean it will cause obvious problems. I mean the language models may not know about the recent events. I mean something is happening in the last week or the last few days. And suddenly, especially in social media, everybody's talking about that. The language model is not going to be familiar, and maybe it's going to struggle. If you want to do some task, to involving kind of real-time data. This is kind of the most obvious problem, because in social media, as written there, many times we need to analyze real-time data and at a scale. So it's sometimes not feasible, obviously, to have an updated language model for that time. And in some cases, it can be minor things, because depending on the application, but in others can be major things. That I mean, maybe there is a huge event going on, and the huge topic of conversation has changed, and that can cause a problem. But in other tasks, as we will see, maybe that's not a big of a problem, and that's also one of the main motivations of this talk. So social media. I guess everybody knows social media by now. Even if you are not in social media, probably obviously you heard of it, and you know that there are many platforms where people communicate and talk about different things, and obviously each platform also is a different world as well. But why NLP research in social media matters? I mean, first, because it's a lot of real world data, and it's kind of some of the largest amount of data from created by humans. Well, most of it by humans. Nowadays also there are a lot of automatic creation. It comes from there. So it's a very good indicator of public opinion, or at least one of them, that we can gather some public opinion from there and understand what is going on as well. What are the topic of conversations and so on. Another kind of topic, especially for NLP, I mean, and this is probably not some of the nicer topics, but yeah, sometimes there are harmful content that has real world consequences, in social media, like hate speech, but also kind of some misinformation. And that's very hard to tackle. I mean, it's very hard to tackle because it has so much volume, and it's impossible to do that manually. So we need automatic tools, or at least automatic tools, obviously, that help us to deal with that. Or in some cases, especially real time, in crisis responses, on public health settings, that is one of the cases that we also need kind of real world analysis of social media, and obviously it can help in many ways, if we get that right. So this is just some of the reasons of why we should care about NLP research, and especially in social media, and why also, I mean, I don't mention here too much about the talk here, but I mean, social media entails many challenges, and I'm going to talk a few of them later. So, I mean, you need a specific research on social media because it's very different that kind of, let's say, news corpora or other kind of text that you can find elsewhere. So this is kind of some applications that we did recently that analyzing kind of temporal data in social media. This is one example that we check Argentina. So we check basically the data from the last 3 years, analyze what are the topics, what people are talking about when they mention Argentina or any kind of other words, no? And you can see here, no, you can news and social concern. That is usually the most predominant topic. But then you have sports, music, and there is a daily life. And you see that you have two peaks. I didn't highlight here, but you have two peaks around July 2021 and about December 2022, where kind of suddenly the topic changed. And Argentina is nobody cares, or at least it seems, about news or social concern, but it's mostly about the sports. Maybe some of you know what is the reason, but yeah, the reason is kind of at that time was the World Cup, no, in 2022 in Qatar, and Argentina won the World Cup. So I mean, yeah, I guess everybody that mentioning Argentina was talking about the World Cup. So this is kind of an analysis, but this analysis involves obviously millions of tweets that you analyze, no, and so on, which it comes to my next topic as well. Or similar, you want to measure maybe social biases over time, not to see what people talk about, and there are some kind of biases. I'm not going to get into details on how we did this, but again, this involves many kind of inferences, no, by NLP models, and then try to aggregate data and to make sense of that, no, and many kind of experiments and so on. So here it comes why LLMs may not always be the best solution or the only solution, not to the problem, no, and why also you need kind of some specialized solutions sometimes, and especially you need sometimes efficient solution, no. So because as I mentioned, right, you have a large volume, so you need to analyze thousands or hundreds of thousands, no, of social media posts every day, and sometimes just LLMs is just expensive, and it's maybe too hard too expensive to use them. In social media, one of the many challenges is also the lack of context, no. So I mean, each post can be in isolation, but obviously, I mean, each post is going to belong to a temporal space, and it's going to have a context, and depending on who writes it, no, has a meaning or another one. And yeah, LLMs, in particular NLP models, any kind of NLP model probably will struggle with that. Another problem is like a lot of the social media data maybe are available not for research purposes or for other purposes, but I mean, it's increasingly more difficult, and it's sensitive and private data. And this makes it even harder, no? You want to use LLMs, especially APIs, and that sometimes you cannot upload this kind of data, no, and share it. So one thing that I argue here, and most of my talk is going to be about, is like specialize and fine-tune language models. Sometimes work better, no, for simple or classification problems. So it's not only that, I mean, that large language models are expensive or difficult to use, as I mentioned before, but that in many times you want a specialized solution, no? And if you have a specialized solution, you can have better results and faster, and maybe you don't have the problem of sensitive and private data. But yeah, I mean, there are always pros and cons, and depending on what you want to work on, obviously, I mean, I would argue that a language model is always a part of the solution, and it's part of the solution also of the solution that I offer here in this talk. But yeah, maybe not the largest models are going to be the solution for all the problems in social media, and there will be issues as well. So what do I mean by specializing a language model on social media? So just quickly to mention, obviously I don't need to get into that. No, you are kind of in call, no, a conference about large language models and a workshop also about large language models. So you know very well, probably know how a large language models, no, is being trained on. And this is kind of a very simplified view of how they are trained. No, so you have a large corpus. You train your model on that, and then you can specialize. So you have kind of some post-training that usually involves supervised fine-tuning and something else most of the times as well. But just to simplify, and then you can have like specialized models for summarization, for classification, for generation, or for some specific problems. And in social media, I mean, specializing is a simple. I mean, there are many other things, no, but basically the corpora, no, that you are going to give to the model is going to be from you can specialize on social media, so you're going to understand better, no, the social media context, and the annotated data also that you will give to the model is going to be specific for social media and for your specific task. So yeah, basically, I mean, when I mean specialize, there may be other ways, but it's mostly, no, kind of some version of fine tuning, what I mentioned here. And yeah, and here once you give a corpus or you give annotated data, I mean, that data will be for a particular time period, both for the pre-training and also for the kind of the annotated data. And wherever you are going to evaluate, it's going to have another time period as well. No? So I mean, here there are kind of several time variables that we often don't analyze and don't really understand. No, which one is the important one? No, that we need to get it right for the model, not to be temporarily aware. So yeah, that's one of the motivations here. That we want to understand, when or how much or why we need kind of recent data for our models. And just quickly now, so you are familiar, I'm going to pass again very quickly, but some of the popular NLP tasks on social media. I'm going to give you some example of one of the more popular ones. There are many others, many tasks that you can do in social media, but I'm going to focus, for the sake of time and everything, on 4 particular NLP tasks. So let's check for sentiment analysis. That's probably the more popular task in social media. It's used in basically any domain. So any kind of thing that you want to know the public opinion. No, I mean, if you are a company, you are launching a new product, you want to know if people like it, or in the government, no, you have a new policy, you want to understand, no, if the public is liking the policy or not. I mean, there are so many ways, no, that you can use a sentiment analysis. And sometimes it's a very simple task, and it works reasonably well in most cases. That is just you want to decide whether, I mean, a user is happy, is positive, negative, or maybe neutral. It's just mentioning, as a news. And there are some other variations. You can treat the problem as a regression problem, as a classification, or obviously you can make it also more complex than that. No, but I mean the simpler form of sentiment analysis is that. No, and it can be an indicator, no, of public opinion, as I was mentioning before. And yeah, there are so many models on sentiment analysis, and people use them a lot. And sometimes they try to use it in a lot of data. No, so the more data they can gather, the better then the predictions will be. No, so many times the volume is more important, not to having maybe just to analyze, no, dozens of posts and so on. No, I mean, sometimes when you use sentiment analysis, you want to analyze, no, thousands or as many posts as you can. Hate speech detection, I briefly also mentioned before that. So the task is basically try to detect any potential, no, hateful content to some particular target groups that they are in social media. Then, I mean, you can do with that many things. Maybe you want to just monitoring to know how much hateful content there is in the platform, or maybe you want to moderate and or to highlight some kind of post as well. No, I mean, but for that, I mean, you first need something that is to understand, no, what is hateful, what is hate speech, and what is not. And that again is very hard, because I mean there are so many posts and talking about many different things, and there are so many things also involved in the post, like other phenomena that make it this task very hard. But we need automatic models, or at least semi-automatic models. And yeah, again, as in other tasks, it's mostly needed in real time, at least on applications that I mentioned. So you need models that are kind of up to date, that can handle basically, the posts that are coming basically, every hour, for example. So some specific challenges, in hate speech detection. I mean, there have been a lot of work in NLP, in hate speech detection, and I summarize here 3 of the challenges that I found that are important. Sometimes I say here limited resources, and you will say, I mean, there are so many data sets in hate speech detection nowadays. No, I mean, there's so much work on that. But my point is that it's not diverse enough. I mean, some of the data sets that we have are based on keywords, or some specific events, or some specific target groups, some specific languages. And it has been shown in different kind of works that because models that are trained in some kind of hate speech detection data may not generalize to other kind of settings. This is also category specific. There is no global definition. So of course, there's a lot of subjectivity here involved for what is hate speech and what is not. And there are a lot of also, as I was mentioning, depending on the event or the target group or the people that are mentioning, language and style variations, and also temporal variations. Or I mean, they are depending on the time period or where you are. There might be different targets, at any given endpoint, and any ways to refer basically to a target as well. And this is what I argue that is also challenging, no, for NLP models to get it correctly. Another task, topic classification. This is again one of the more classical tasks in natural language processing. So here I will be classify. I put each tweet, but it's basically every post in social media by a topic domain, and this is based mostly what I'm working here too. It's 19 topics, especially tailored to social media. So you have things like sports, science, technology, news, and society, business. I'm reading here the ones that are there, but there are in total 19. So, for example, you have something like Apple remove more than 30,000 apps from the Chinese App Store. You will have you can associate that tweet, with business, news and society, or science and technology. Or then you have something about football, so you associate that with sports and games. So a very simple task, as I will mention here, I'm focusing mostly on simple tasks, or tasks at least that can be framed as a simple classification task. And just to mention that again, like in the hate speech that I mentioned, there can be many languages, and it is also a challenge here. No, so I mean, here also we created a data set with different languages as well. So models also that can handle different languages as well. That is kind of raises the complexity, of course. But in this talk, I focus mostly on the temporal aspect, and mostly everything is going to be in English. But just to be aware that whenever we introduce a new language or a new country or a new kind of culture, and things will get even more complicated. And people will talk about different things, so that obviously will kind of mess up the models, where they have been trained on as well. The last task that I'm going to talk about today, I promise it's going to be 4 tasks, so I'm not going to talk about all the tasks in social media, is name entity recognition. Just adding that here, not because maybe it's the most popular in social media, but it's been very popular in NLP in general, no? So it's a classical NLP task that you just say you want to identify entities in text, and you want to say if a person is a person or a location, no? Like an example here of why Johnny Depp lost in the UK. So Johnny Depp will be a person, and then UK and US will be tagged as location. So you need to identify the entities and also identify what type of entities they are. And this task is interesting because, I mean, it's something that, I mean, most models work very well, and LLMs, language models, or previous models as well, work very well in kind of the standard corpora, like news corpora, Wikipedia, things like that. But when you come to social media, I mean, maybe I put this an example that is very well written, but things will be written very different ways, and people will not use even the casing that sometimes as an indication of an entity, or there is a lot of misspelling, a lot of complications not to detect entities as well. And now I'm moving towards kind of, again, the motivation of why I started working this temporal aspect. So, I mean, at some point we developed some kind of models and data set for name entity recognition and topic classification. And that time was on social media. So we developed 2 data sets and tried how the models work on that. And there we found out, for example, the name entity recognition, the main models, they don't work that well there. And for topic classification, we can have good models. But then we wanted to have kind of a real world task. So many times in NLP, we just have annotated data. I don't know, we annotate 10,000 posts just to give a number. And then we just shuffle them. Then we are losing that kind of temporal aspect, and in many cases we want to work in real time, so we shouldn't do that. So we should have the training set is going to be in the past and the test set is going to be in the future, because that's how they are going to use the models, in real world settings, and that will cause basically some mismatch on performance. So that's what we found, that when you had these temporal splits, the models that were trained in the past and evaluated, let's say, in the future, I mean, they were kind of working much worse. And we wanted to wonder why and what we can do to solve it. And that's why I took also these two tasks as an example, and added also sentiment analysis and hate speech detection as were kind of some of the more popular ones. But we also work with more tasks as well. But in the presentation, I want to mention those 4 only. So what we try to analyze, so what are the temporal challenges, or what are the sources of performance drop? Why, when you are training in the past and evaluating, let's say, in the future, in real time, your models don't work as well. And in my experience, and I'm telling this here, working in different tasks, in most of the cases, at least in the tasks I was mentioned before, hate speech detection, topic classification, name recognition, the performance is going to be all right. But you have cases where people mention kind of a new event, a new person that maybe was not famous at that time, or something that it was not by the language model, that then the model will struggle. So we are talking here maybe, I don't know, like up to maybe 5%, no, of the posts that you want to analyze will be complicated, and the models will not be able to solve it. But of course, I mean, we want the models to be as accurate as possible, and those 5%, 10%, we want to get it right as well. And why we see this performance drop? It can be for the pre-training data because it's been in the past, or the training data. I mean, the training data we giving also we can give it in the past, or something more recent. Or it can be the nature of the domain and task. No, I mean, maybe not all the tasks are the same, or any other reason. No, I mean, but we focus on those these three main reasons, at least for this work. And yeah, I'm going to give you the conclusions because I mean, at least I didn't expect all the conclusions that they came from this work. So yeah, we wanted in a way not to analyze the temporal generalization of language models, no, and especially yeah, we focus on social media because that's the main domain that we're working on, and because it's so dynamic, no, and often involving real time. So again, why relevant? But I'm kind of repeating myself, no, but I wanted to maybe for you not to be clear, no, like in social media, many of the tasks we want to solve in real time, and we will post basically thousands, no, per minute and so on. And in general language models, obviously they will have always a cutoff date, and it can be very recent or not, but they are not going to be the same as the test and the test date. And there are many ways to solve it. I mean, but some solutions involve and maybe are not that efficient for the things that we want. No, so I mean, there are so many things that we can leverage, not recent data, in real time, but obviously that will make things less efficient, and it's something that maybe we don't want to do. But yeah, there are many solutions with that. And yeah, yes, as small notes, as I mentioned, I mean, the temporal aspect is relevant, but I mean, it's not the only one. Sometimes there are some confounded factors, no, that it may be that, I mean, you are training your data set that then you have annotated, it's been extracted in one particular way with some particular keywords or some particular kind of set of users. And then obviously, I mean, it's going to be biased to one specific domain. And there have to be many words. For example, hate speech detection there too, but I mean, that's kind of something that also affects a lot the performance. The temporal one is one aspect, but also the domain shifts is another aspect as well. And it's a problem. I mean, I show you, kind of examples before, no? So I want to convince you that it's a problem, no, that we observe, and we are not the only one, no? Many people observe this kind of performance drop, no, when there is this temporal mismatch of the training and the test set. And as I argue here, we don't understand why. I mean, we can have kind of some intuition on why that is a problem, but we don't really kind of understand, no? And that's what it led us to work on this. So in this work from last year, basically, we wanted to answer this research question. No? Are temporal shifts in social media detrimental for LME performance in NLP tasks? As you mentioned, no? I mean, at least in some cases, the answer is going to be yes. And if so, what are the causes of this temporal shift, and can it be mitigated? No, so it can be by using recent data, of course. No, I mean that will be the main and the main solution, no, that we can find. So this is kind of our setting. It's a very simple setting, no. So we wanted to. I mean, there are more details of how we do this. So we have an out of time setting and an in time setting. The out of time is what I mentioned before. No, you have the training set that is going to be in the past in one period. No, so for example, I mean this image is from 2018 to 2020, and then the test set is going to be afterwards. And the in time is where you have some overlap in the training and test set. There are different settings of how that overlap may look like, but you have some overlap between the training set, the annotated training set, and the test set. So we want to compare just the difference in performance and other kind of other analysis that we want to do on top of that. So these are main results, no? So I'm coming very quickly, from the methodology to the results. Here we had hate speech detection, and just let you see the image to understand a bit more, no? So we have different models training at different times, no? So at that time also we have specialized models, in social media training different kind of time frames, so we could control where they have been trained on, which that was nice, basically, to explain, because sometimes it's not that easy to set this experiment. So we have different models, and basically the blue results are the one that is in time, so when there is overlap between training and test set, and the out time when there is no overlap. And we can see clearly for all models, no, I mean there is a consistent kind of statistically significant gap, no, in all cases. And I always mention it goes from maybe from 5 up to 10, so it's not a huge gap, but it's a considerable gap, no, something that we want to obviously to close that gap. So yeah, we have better performance now when you have the training set and the test set, they overlap. So here in hate speech detection, we found a clear temporal effect. Sentiment analysis. Here we saw pretty close results, and not always. No, the blue bars, no, are higher than the orange bars, as we mentioned here. And we see the average. The average is the last and the last bars, no, in the plot. The results are pretty similar. So we can say that in sentiment analysis, there is no a temporal effect. That this also has been kind of my experience. I work also in sentiment analysis. And in most cases, I mean, it's not hard to understand if a person is liking something. Or there might be obviously some irony, sarcasm, that makes things hard. But that's going to be hard even if you have the training and tested aligned. There is not much of a temporal effect here in sentiment analysis. And most of the cases, you can get away just to having a very old data set and you can have a good performance. So yeah, that's kind of a good thing. If you're working in sentiment analysis, you don't need to worry about this problem that much. Name-entity recognition, here again, as I was mentioned also before, you have better performance in the blue bars. So I mean, you see a clear temporal effect again. And yeah, and the reason is, again, this is even probably smaller than in the case of hate speech detection, or maybe similar, but it's mostly in cases when we have new entities emerging, maybe a new famous person, or maybe a new location that it became famous that your model is not recognizing. So I mean, that kind of the things that can make the models the performance. And topic classification here, it was harder to interpret. So we have more results and so on, and we try to dig a bit more. And I guess, I mean, I cannot confirm 100%, but the results suggested that there is some temporal effect, but this is much more connected with data distribution. If you remember topic classification, there were 19 topics. So the data distribution of your training data will have a huge effect in the performance of your model. So I mean, you are changing, and obviously the temporal effects will have this one. Usually when you have data from recent data, you will have different kind of topics people talk about. So there is a small effect there. But it's much more due to data distribution. And there are some kind of result there on the paper as well. So there is some temporal effect, but in topic classification, I would argue that this is not the main driving force of the performance drops. So yeah, we see that kind of mixed result. That is something that that we need to analyze. We needed to analyze a bit deeper, to really understand. And in a way, we see like the kind of the tasks that involve kind of entities on events, like hate speech detection sometimes is driven by some kind of particular events, so people feel targeted, or maybe some the political conversation at the time, people talk more about immigrants or about other kind of things, so the hate speech is directed towards them, or it can be, as I mentioned, in name-entity recognition, it's very entity-driven. So you have many entities, and entities are changing all the time. Ones that are famous, and maybe the models know or doesn't know about. So this was the mismatch between the annotated training data and test set. And here we wanted to study the effect of the language model pre-training corpus. And here we have in blue, we had the models when the pre-training corpus included the test period. And in the red, there was the language models that there was no temporal overlap. So they were trained, the pre-training was done before kind of the test set. So there was not overlap at all. Honestly, here I was expecting to see more of a difference. Like we were expecting basically to have the red models, the ones that they don't have overlap, that they gain more, from the kind of and when they pass from in-time performance to out-of-domain performance. But you can see like the blue and the red spots are all over the place. So you cannot infer anything. This is for name-entity recognition, but basically for all the tasks. We couldn't get any kind of clear trends. Which, in a way, and the way we were expecting that, you have a language model that is in training the test set, more or less in that particular period. So you can leverage that kind of unlabeled data, for your language model. But it was not the case. I mean, it was much more important that you have some annotated instances, in the test period, more than using your corpus, as pre-training in that temporal frame. Topic classification was the same. You see the red and the blue dots. I mean, there is nothing that you can get, and for other tasks was kind of similar. They were all over the place. So I mean, there may be other factors involved, but I mean, it was clear that the temporal, at least, it was not one of the main factors were kind of driven the performance or mitigated maybe that performance drop. So this is kind of the summary of the results. I passed very quickly, so yeah, obviously I'm not sure if I explained all the properly, but yeah, the main sources of performance drop, it can be pre-training data, and here it's not really, I don't want to say, I mean, with certainty, but the results it suggests that it didn't help a lot. But maybe it's also the way that maybe you pre-train your language models. So obviously you have a lot of training. We use different models. Sometimes that use kind of continuous pre-training strategies. Some others that they was everything shuffle and so on. And we didn't see much of improvement there. But yeah, there might be something that can be done. Because I mean, I can imagine that, I mean, seeing some part of the test set, obviously, or the temporal test set can help. Training data, yes, definitely yes. You have more training data closer to the test period. I mean, that's very helpful, no? Even if you have less instances. And the nature of the domain task, yes. And we found that in hate speech detection and in native recognition, we had clear temporal effect, but we didn't find in sentiment analysis, no, and much less also in topic classification. So this was more or less the takeaways, no, from this experiment. There's still many things to understand and to improve, and especially what will be the future work. I mean, here I have two ideas, but I mean there are many more that we can do, no. But again, we have to be careful of having ideas that works in general, maybe. Obviously, we want that, but also that works in real settings, no, in real setting where we don't have massive resources, no, at real time, and we want to have efficient solutions and so on, and we want just to get something analyzed, and we cannot basically keep training everything all the time. So new method maybe to integrate some contextual information, no? So maybe you see an entity that you haven't seen before, and maybe you can retrieve maybe more post or more information about that can be helpful. And that's something that maybe you can do in an efficient way as well. Or maybe, yeah, using LLMs or all the kind of things, not to automatize, not this kind of labeling effort that is usually very expensive and you require usually humans, but maybe you can use LLMs for that, no? So yeah. And just to mention that we have also, if you are interested in this topic, we have the Super Twitter benchmark where we have different kind of social media tasks from different types, and they also include temporal splits. So if you want to experiment with that, that can be a way to go. But obviously, I mean, that's limited to some particular tasks and time periods. And we also organize at some point a long eval to evaluate performance consistency over time, and for sentiment analysis on other tasks, they have been proposed as well. So those are other efforts that you can look at. So yeah, this is kind of the Super Tweetable benchmark. You have different tasks, but maybe the one that you might be interested more is the one that we have temporal split. So you can kind of work with this one also, the in time or out of time, and you can kind of play with that as well. So that's all. Yeah. So hope it was more or less clear, and at least I promised that it was going to be simple. So hopefully everybody was on board. So yeah, social media has many challenges, and including this kind of dynamism, you know? So we want to analyze things in real time, and things change very quickly. And temporal adaptation is needed for some tasks, but not all of them. As I mentioned, sentiment analysis, all the tasks, maybe you are good to go. And yeah, you have some solutions, but they involve some of them are expensive, and maybe we need to work on kind of more in newer solutions. No, I mean maybe be creative, on the solutions that we propose. And that's all from me. So thank you very much for listening. And yeah, you have any question, I will be happy to answer any question that you may have. Stop sharing.
Thank you very much, Jose, for your talk. Any question? Let's start with the in-person participants. Any question from in-person audience?
Since we have no questions right now.
Okay. A question from, okay. Hadia has a question. Please go ahead.
Yeah, hello. Can you hear me?
Yeah.
Yeah.
Okay. Yeah, thanks for the nice talk. I was wondering, you said that the effect of the pre-training data towards the mismatch with the test data was a very mixed picture. And that contradicts a little bit Longpre's results in his pre-training guide, where he finds, of course, a much smaller effect than between fine-tuning data and test data mismatch, but he finds a consistent effect between pre-training data and test data mismatch. So I was wondering how you explain that mismatch, because he used very similar tasks to what you use, like the same task as, well, basically the Lu et al. Tasks.
Which work was?
I was wondering whether, because they had the resources to really pre-train all the models with the same sizes and the exact split, and whether you were able to do that, and whether this is an explanation if you couldn't do that and you took them out of the box, or what is your explanation?
Yeah. Which work is the one that you are mentioning? Or you can put in the chat, that would be great.
Along Pre et al. Pre-trainer's guide to
Okay.
data time. It's relatively famous, so yeah.
Yeah. No, I think, yeah. I mean, I don't have all the details, but yeah, as I mentioned, I believe there is going to be an effect, no, on the pre-training data for sure. There is going to be, no, but at least what I think, and I thought, I was thinking that it was going to be shown in the results, no, but then we didn't see that. We control. I mean, we're limited what we could control, but I mean, some of those language models we train ourselves, no. So I mean, we have different kind of ways, not to make it also kind of the same size and things like that, no, and to control for a few things like that. But we were limited still, no. I mean, there were kind of limited data points. I mentioned there that was all the language models that we studied, and all the settings. So I mean, I'm sure that will have an effect, but at least in our setting, what I think, no, or at least what the results show, no, that is like. Obviously, the language models have then the pre-training, no, it's happened before, no. Then you have a lot of post-training as well, no. So maybe, I mean, a lot of the things that you are seeing in pre-training, especially you mix everything, all the data, no. You have so many millions of data that whatever is kind of at the end, no, it's going to be a bit lost, no. Or at least these models that we studied, that they were not the largest models, no. For sure, they are going to miss all those nuances, and after, especially after fine tuning, they are going to lose even more, no, because it's been shown that when you fine tune, no, you lose kind of some information also from before as well, no. So these models were not huge by any means. So I'm sure that kind of this limited maybe pre-training data, no, that is kind of maybe in the test set, no, with all the process then of fine tuning and everything, all the data that they've been training on as well, no. So, I mean, the nuances that you need, for example, for name entity recognition, as I mentioned, it's only in the cases that maybe you have an entity that you haven't heard of, no, or things like that, no, that you make those mistakes. And I believe that maybe that doesn't help, no, that much, at least in this setting, no. But I'm sure like bigger models, or you have some maybe continual pre-training strategies, no, where you everything. I mean, we tried also that, but no, but if you maybe what you train at the end, no, the model remembers better. I mean, that will help, no, maybe because that will make sense, no. But yeah, in our case, in the setting that we have, for sure, I mean, the annotated data, no, is the one that has much more temporal effect, no, in our setting.
Yeah, they also find a bigger effect with the annotated data, but they still find a relatively consistent effect with the pre-training, and yours is kind of more like all over the place, and one can't really find the consistent. So I was just interested in the difference. Thank you.
Yeah, no, thank you.
We may have time for one more question from the online audience, a short one. Okay, if this is not the case, let's thank the speaker again. And if there's further questions, please contact the speaker offline.
Yeah. Happy to. Thank you.
Thank you.
Back to you. Thanks.
Yeah. So we will move to the second keynote talk. So maybe Alexi, you can try to share your screen.
Hello. Yes, I'm sharing it. Thank you also, Jose, for your talk.
Okay, in the meantime, I can give a little presentation, a little introduction. So the second keynote will be given by Alexis Huet, who is a senior research engineer at Huawei Technology in France. And his interests include like series anomaly detection, network AI, and memory systems for large language models. And in his current work, he explores how LLMs can develop robust episodic memory capabilities and safe knowledge updating. So we are looking forward to your talk, Alexi. I think you can start.
Yeah, so thank you for the nice introduction. So you can see correctly the screen, the main screen now?
Yes, it's all good. It's all good, yeah.
Okay. So today, I will present a recent paper. Actually, we wanted to promote this paper, so it will be mainly on this one that is named Episodic Memories Generation and Evaluation Benchmark for Large Language Models. So it has been accepted this year at Hartley 2025. But more broadly, I also want to tell you more about the question. So can LLMs remember what actually happened? So And this is the basis of what we call the episodic memory for humans. So I will give some context about episodic memory first. So episodic memory is the ability to recall specific events that are grounded in time and space. And this comes naturally for us. So humans are permanently grounded in the time and space. So if we consider a human, so perceiving the environment, like for instance, an event here, they continuously live this in the reality, and the humans will know when the event happened, in which space, also which entities they met over time, and also the content of the event, maybe the general content, but also some specific details that the human is living. And it's like every experience that we live comes with invisible coordinates. So like a timestamp, and the location is the real world. And it's not just that we think, but it's very true. So the grounding is so fundamental that our brain has a dedicated structure for it. So looking at in the hippocampal formation, there is a lot of neuroscience research, so mainly from the 2020 last year, that identified a lot of specialized neurons for those tasks. And first, for the time, so we know the time cells that encode the passage of time, so also segmenting the events into distinct temporal sequences. But there are also some for space where we know a little more. So there are those place cells. So those ones are really telling, I'm here. So it already give when you are in a location, the cell will activate and tell you that you are in this location. And also something very interesting. So those grid cells that act like a coordinate GPS coordinate system when you move into different directions. And for entities, some researchers also found them, those concept cells, so those ones that selectively respond when there is, for instance, a people face, but it can be when you see the face, but also when you listen about the names, when you read the name of the same person, of when the person is described. So it's in that case, those concept cells will be activated. So we are very grounded in time, space, and also in the entity also have a dedicated cells for this. And this grounding is also what allows us to distinguish, so at least it's one component, to distinguish real, so what happened in our shared time and space here, from the imaginary elements. And just to give an example, so for those of you that are in the column conference, so for you it's real, also because it happened in your perceived time and space, so you know we are in 2025, you are in Montreal, you met different attendees that you may remember even 1 year from now, and you know it's a conference. And even if this morning you were in a hotel, you need to go to the event place, you may have activated those grid cells. And maybe in one year or so, you can recall and reactivate those cells that you are creating right now. So moving towards LLMs, we know that LLM lack this grounding by design. But the question we ask now is, how good is their episodic recall? So now I will move into this recall part. So what is recall even for humans? And for answering that question, we need to do some modeling. And we get inspiration from the concept of queue-based recall. So this has been developed in the 70s by Handel Tolving, and now it's a concept that is well accepted. So during retrieval, what is saying, during retrieval, a part of the original signal that was present during encoding, can be like the word Montréal, is used as a queue, and this queue can invoke the rest of the details of the episodic event that we call a trace. And from that concept, we make it us, and we decided to simplify and to model episodic event as a structured tuple. So what we did is that the event we simplify and we say it's just a certain time, a certain space, location, a certain entity, or at least there is a main entity and a certain content, so main general content. And this simplification has one big advantage, even if it's a simplification, is that now we can see the queue-based recall just as a key value retrieval system. So here, just to give an example, we have entity E, like for instance, this guy that we call Jackson Ramos. And then first, this can be experienced by someone. Like here for now, it's still a human because it's the original concept. And this is done as a first step. So there is the encoding of the event. And then what we want to ask now is a recall. So in the second step, we use a query, which is just a queue. And the queue can now just be the entity name, Jackson Ramos. And this queue will be used to retrieve all the events involving Jackson Ramos. So we can ask a memory trace regarding the time, the space, the content, so any other information regarding this queue. And in the following, so it's what we propose now. We develop the Tolving episodic memory benchmark. So it's the name that we give to this benchmark. And it's a framework for measuring how well LLMs can encode and recall episodic events and across extended narratives. So we will see that we create books and then we feed it to the LLM. So just to give a high-level view, we have this approach, and then we will move to the detail, but this is to give you the high-level idea. So first, we create some synthetic events that we put in distinct chapters, and then we merge all those chapters to create a book, a narrative, which is like a novel. And then we fit it to the LLM. That can be with different kind of memories. So it can be in context with an external memory, like in RAG, or something that we think it's interesting is by modifying the parameter of the model, so doing some fine tuning and to see how the model react to this fine tuning. That may be, so the in parameter maybe the thing that is closer to how the human behave and under the events. And finally, so regarding the evaluation, we adopt a systematic set of questions based on a queue-based retrieval. And I will detail after, but to give an idea, if we take Jackson Ramos here, it will mean that we want to extract all the events involving Jackson Ramos and then ask a specific question to the model. So then in the rest of the talk, I will detail how we create the benchmark, so give a generation of the benchmark as a book-like narrative with detailed event. Then regarding question answer, we will see how we design the question with a systematic language-based episodic retrieval. Then we will see what we obtain and how we evaluate the model. So we have at the end 11 benchmark data sets and we evaluate 3 forms of memory. And interesting, so we will show that the LLM model struggle. So this was what we also state in the paper when we submitted it 1 year ago. But now there are a lot of new models coming every month, and we actually evaluated in the most recent model to see the improvement. So we will see how it improved over the last year. So now moving to the generation, we move now to how we build the benchmark concretely. So the practical construction of the benchmark. So the aim is to build a book with methodically placed events. And for that, we first define a universe with 100 dates. So it's just a string, so different dates, location, entity names, and event contents. And then what we do, to create one event, we simply take one element from each group independently. And for example, we get Jackson Ramos that ate candy at Carnival in Central Park in September 2026. And this, even if it's independent, there is something important here, is that it's not identically distributed, and we use a geometric distribution, so it can be any heavy-tailed distribution to generate the event. So what does it mean? It means that some item like E1 Jackson Ramos may appear more frequently than other items. So the entity Jackson Ramos match many events, like in that case at least 3, while the other items such as the entity E2 here appear once in the book. So we can finally control how the different elements appear. Some of them appear a lot, some of them appear just once. And we can even visualize the event. So here we visualize the track of the entity Jackson Ramos over time. So here it's a map of New York. We decided in this novel to have all the location in New York. Each dot is a specific location, and in red it's all the track of Jackson Ramos over the different chapter. So for instance, in this chapter, it is at Central Park doing Carnival. And you can see that there is other entities that can be also at Central Park, but are other different times. And then it's overall, there is a lot of possible combination of time, space, entity, and event content. So then each event form one chapter of the book. And at that stage, we rely on recent LLMs for generating each book chapter in natural language, where we enforce the presence and the position of each element. So actually, we did a lot of verification steps. So we have some direct verifications in the correct placement of the elements, but also we needed to add other LLM verification. This to really ensure there is a single date, main character, geographical location, and main event. So here, for instance, we know that this is correctly there, but we don't want to have like a next day or something like that that will make the chapter not being just in one day, but also more in other dates. So we do this for each chapter separately, and then what we do is just to concatenate the chapters to give a book. So just to give one example, this is one fictional chapter that is generated from our book called The World News, where you can see just the event here. Then the parameter for each event is decided between 1 and 9. So here it was 2. And then this is also randomly generated that gives a position about each element. So then we can see that each paragraph correctly represents what we wanted it to represent. And like Benjamin Green here, we can see it's here, but there is not the full name in the other paragraph. So we already controlled how the different elements were put into the book chapter, here into this chapter. So now, once the book is created, we need to know what we ask to the model. And here is what comes this Q-based recall and episodic retrieval is that now we can do systematic Q composition and also systematic retrieval trace. So what does it mean? I'm giving here 3 examples. So in this first example, we just take, so here it's the same TSEC. And for the entity, we put Jackson Ramos, while the other one, we put nothing. And what does it mean? It corresponds to this question, reflect all events involving this entity, Jackson Ramos. And then, so the LLM need to think about what are those events. And if you remember, we just showed before, it appears in 5 different chapters. So this is for the Q. And then we ask a trace. And the trace can be any different items not put in the queue. That can be the time. And for which, if it's doing correctly, should get those 5 different elements. So as you can see, contrary to many benchmarks, here the output answer can be multiple. So I'm giving another example to make it more clear. So we can have a more specific queue. So it's still a single queue, but it's much more specific because now we ask all events involving Jackson Ramos on January 1st. And in that case, there is no existing event with that queue. So when we ask any item, like listing all the locations where these events took place, the correct answer should be that there is no such element. So with this benchmark, we also test for hallucinations. And finally, we can even give a more specific queue, which is to recall what happened involving Jackson Ramos at the location Highline at time February 27th. And here, correctly, there is just one event because the question is very specific. And if we extract the content, the correct answer should be the list of size 1, which is theater performance. So we can see here that overall, we can do it systematically using all possible combination of this time, space, entity, and details. And as shown in the example, we can test for hallucination. So that is indicated in red here. So that we saw in the previous slide. Single event, which was the last very specific question we asked. And we can also evaluate for overloaded queues, which was the first one here. So in that case, overloaded queues mean that the event is not specific at all. So it may be someone you know, so you know a lot, you already experienced a lot of events with this person. So when you ask about the specific date when you encounter this entity, there is a lot of different possible answers. It can be very large. Here it's of size 5. So in total, we get 36 template questions because we also look for chronological and latest event. So latest event means that we ask the last time in the chapters at the of the event, and chronological, we also want to consider that the ordering is correct and to evaluate this. So I'm just passing quickly here, just to give the list of the 36 template questions. So with queue involving 1 item, 2 items, and 3, 4. There is also some with 4, where we have the full details and the other entities that can appear in the book, which are not the main characters, but are other characters in the book, in the chapter. And here is the one for latest and chronological events, for which we target specifically the queue entity. So at the end, what we got? So we have 11 benchmark data sets that have been generated. So they vary in size. So we go from 10K tokens to 1 million token, and in diversity. So we have 3 different books. One is a novel, so the one you saw in New York news, and also a third one of more sci-fi books, sci-fi entities and events. So in the following, I want just to show the results mainly on this book, which we call Synaptic Echoes. It's just the short name, which consists in 200 chapters, 100K tokens. And for the corresponding questions, what we do, so if we take all the questions, there is more than 3,000 questions because we can do all the possible combinations. But what we wanted is to represent many diverse queues and also many matching event size. So how we select them, we put the matching events so that we show before in categories, so 0, 1, 2, 3 to 5, or more than 6. And then for each of them, we want at most 5 template questions in each of the for each group here. So at most there is 180 questions for each group here. Sometimes it's difficult to get those because when it's 6+, it's not specific at all. So not all questions will have any valid answer. So this is for the default book. I will just mention 2 other ones because they are mentioned later. So one is a short one, which is just with 20 chapters and 10K tokens. So this one was for quality assessment of the benchmark. And there is another one because it's actually easy to scale the number of chapters. So a very long book that is 2,000 chapters and 1 million token, which is a challenging extension. So I just take before what means the 1 million token. So it is like the Lord of the Rings, the book 2 times. So it's a quite book, 2,000 page book pages. So now, yeah, just before I wanted to give a word about the evaluation. So it's a little more technical, but I found it's an important detail. So just what we do is we evaluate only with a F1 score, mainly in F1 score, against the ground truth. And it was challenging during creation of the benchmark because the answer is a free-form answer that may contain paraphrases, additional details related to the main event. And also the answer, it can be multiple. So then we need also to be correct in evaluating the multi-event retrieval. So what we did is we extract from the free-form answer the identified items, and then we compare against the ground truth to extract precision recall and get F1 score. But just want to say the critical important detail is that we score from the point of view of what we know, what we trust, which is the ground truth. And then for each ground truth element, we get the matching score between 0 and 1. And doing this, it was a critical detail to make it a reliable metric. So I can give, there are more details in the paper, but just the point I wanted to make on this. So for hallucination, we just put F1 score like if the event has been, if there is a hallucinated event done by the LLM, we put 0. And if the LLM correctly assesses that there is no such event, then we put F1 score of 1. We define it like that. So regarding the different evaluations, we evaluate 3 types of memory. So the in context, RAG, and parametric. So for in context, it's just we put a prompt with we tell the model it's a memory test. We put the full book chapter, so it can be very long. And then we ask a single question. So we do each question independently. So here with a specific queue and a trace. So for RAG, we decided to chunk into paragraphs, and then it's the same. So we retrieve a number of documents that is ensured to cover all the questions asked, and then we ask the specific question we want to ask. And for fine-tuning, so it's a part that we think it's an interesting part. So in that case, we really want the LLM to integrate the information as a human, so to become knowledgeable about those events, not like post-it notes like in RAG, but by integrating and assimilating the information. So in our case, we created a baseline that may be naive, but it was a first step to go in that direction, which consists in taking among all the questions matching only one event for chapter 1, all the questions mainly matching only the events for chapter 2, etc. And we concatenate all the 3,000 questions matching only one event. So it means that they're related to a single event, discarding any question about multi-event retrieval or hallucinations. And what we want to assess after fine-tuning is whether the model is able even to connect the events. So how good it is for hallucination question and the questions that now match more than one event. And if you can see, as you can see here, the model then have all the information, because all the information about all chapters is available just with this single one matching event. And we want to ask more complex, so to know whether the model is able to really connect the different things. So now moving to the results. Here is from the default 100K token book. So in the x-axis, we can see the different models and the different kind of memories. And in this axis, we have the number of matching events, so hallucination, single match, or this is for the overloaded queues. And each cell is the F1 score that has been averaged over those number of questions. So what we can see is that there is no model achieving perfect F1 score in avoiding hallucinations. Then moving to GPT-4o in details, we get good results for encoding for when there is just a specific output. But when the queue is overloaded, we saw a big degradation in the results. So next, moving from RAG, we see that it's minimally help for recent models. So for instance, in that case, it even confused more the model. And moving to the fine-tuning part between this one and this one, we see that the model is correctly able to integrate the information about single events, but then it's hallucinating the other questions that has no answer, and also the one with the queue is overloaded. So it's not able to connect the different information. So this was in 1 year ago, but now we have more things because a lot of progress have been made. So we will see what we get in February. So it was just after the acceptance. We tested Gemini, DeepSeek, and the costly variation of OpenAI, so that named the O3 and O1, the O3 mini and O1. And at that time, most of the models were on par here, those ones. But then just before this talk, so we wanted to see this again, and we updated with GPT-5. There is Grok 4 fast, there is a Gemini 2.5 and Claude 4. And here are the results. So we see that there is a very good improvement, so especially in the hallucination part here. So Grok otherwise is not good in that task. It's quite unexpected because there was recent claims, so that is very good in 1 million token size, etc. But it's a little better than GPT-4o, but not that much. Then Claude model, it's much better than the previous evaluation one year ago. But then what is very clear is for Gemini 2.5, it's very like it's already saturated the benchmark, and it really seems that it has been trained to this specific kind of tasks. But if you recall, the benchmark is easy to scale. So we have this 1 million tokens book, and we also know that Gemini 2.5 Pro is able to integrate 1 million tokens. So what we did is to evaluate 35 questions on the largest book, and this is the result we got. So it's a very short subset, so there can be some variance in the result here, but we see that it's still good in hallucination part, while for the other one here, it's actually interesting because it's almost at the same level that was the best model at that time 1 year ago. So now I think for the next generation model, we can still use this benchmark to test on the new model incoming. So we have more results in the paper in the Git. So I just wanted to mention that we have this chronological score that is more specific for the ability to track the entity states and the temporal sequences. And we can see that last year, at least, all the models were struggling a lot. Now it's a little better, while for Gemini 2.5 Pro and the large one, it's struggling as last year for GPT-4o. Then I will not talk more about this, but there is an interesting result also in the Git. Now I wanted to make the conclusion. So that's all for the result. I wanted to step back and see what we got and where we want to go. So current LLMs, they lack episodic memory, so they cannot recall when or how they learn something. So first issue, events are not grounded in the episodic reality, so in our time and space. So they are not aware when they learned a specific piece event. And this absence of grounding might contribute to the tendency to hallucinate. And second issue, the new knowledge either does not persist or is fragile. So this is a critical point in which the humans behave very differently compared to the current LLMs. So looking at the current in-context solution, so by design, LLM forget beyond context window. And unless real infinite context window is available, this will not solve the problem. So currently, it's solving 100K, but moving to 1 million, it's not working anymore. So and correct solution for this we believe are superficial. So RAG is like a post-it note, so it might help, but it's very far from how the human behave. So I'm giving, I wanted to give an example, but I'm out of time, so maybe after during the discussion. And what we believe is that very a key missing piece in LLM is a solution to fine-tune them. So we know it's hard to fine-tune them, especially on specific events like that. and what we observe is mainly catastrophic forgetting and difficulty to learn when there is very few samples in the data on which we want to fine tune. And at the end, so current focus, so maybe it's also a different conclusion. Current focus in LLM is the ability to generalize while preventing memorization. So there is a lot of work on this that is very discarding. They don't want to memorize, they just want to memorize. But a missing piece could be to memorize, to add new knowledge continuously into the LLM, and to also not only know what has been memorized, so that is in our benchmark simple recall, but also to do association between the multiple pieces of memory. So can be represented by chronological awareness, but to be able to, by fine-tuning, being able to solve this task. For now, our current contribution is this benchmark that can finally track the progress towards true episodic capability beyond context size through scaling. But our future work, so I hope we have a new on that direction later, is to move beyond the static knowledge and to see how by fine-tuning we can dynamically integrate new event information that are grounded in time and space. So thank you.
Okay, thank you very much, Alexis. Do we have some questions in the room? Not yet. So maybe I want to ask one question. So you hinted at the fact that by design, LLM cannot have knowledge persistence. And so do you have maybe some ideas or high-level ideas of how to maybe approach this problem or fix this beyond the RAG and the post-it solution?
Yes, so I think there are different approaches now that are ongoing. So as we can see, humans, they have this hippocampal formation. So it's also not like separate, it's not an external machine, but it's still well integrated, but still separated in the brain. So I think there is a lot, there is some directions that are creating that this more separated with the brain, and then something that will be more to what we call in for brains the hippocampal formation, or can be hippocampus. Another way could be to see whether direct fine-tuning can work if we do more like in pre-training, so doing some rehearsal, to do some work so that we prevent the LLM to forget. So maybe if we rehearse correctly, if we create if we have an event, we put not just the event, but also all the possible combination we can create. Then we can, from a very teeny training set, fine-tuning set, extend it and have a more complete information we want to integrate. And this may also be close to how human work with the dreaming and this, but then the connection is also difficult to make a accurate connection between how LLM is doing and how the brain is doing, because it's quite different. But then it can help to get some inspiration and to get some idea on how to move and to enable the fine-tuning of LLM, which is currently very difficult for this task, which is integrate new memories and not just learning the LLM to do another task for which the fine-tuning is currently good. But this task of memorization, currently it's very difficult.
Okay, thanks. And do you have an idea, like maybe a guess for why the new generation of models perform so good on the benchmark?
Yes, so actually, I saw there is a talk of someone from so by Fatemi from Google working also on this. So I think they, though I don't know how they did in practice. So it may be that they very train on those specific tasks at some point in the training, and it can be by using many combination, possibly also on synthetic data, so that the model is already able to is already knowledgeable about this task and already integrated how to do it, not just by memorization, but very integrating how to solve this task. But this is a guess, so I don't know exactly how it proceeds, but it seems that in that case they possibly solve the problem. Then when we move to more tokens, it's always difficult, but at least in context, it seems to work well. Contrary to like a Grok 4 fast, here we see it's not working well.
Okay, thank you. Do we have more questions, maybe online? Seems not. So then we thank you again, Alexis, for the great talk. And I think it's now time for the break. So we see each other back at 11.
Okay, and let me just click play. Can you still see my window? Okay.
Yeah, works.
Okay, perfect. Sounds good. So I guess we can start. So hello, everyone. My name is Tamar.
And I am Robin.
Yes, and today we'll be presenting to you the time-aware mixture of language experts. So LLMs have demonstrated remarkable capabilities across a lot of domains. However, LLMs lack a robust understanding of time. For example, previous research shows that Quen, for example, gives 35% accuracy in predicting the year of events, and GPT-4 achieves only 14% accuracy on the fast-changing time-sensitive facts. And this can undermine the credibility of the large language models, especially in fields such as medicine, where guidelines change very rapidly. And one example of that is, for example, during the pandemic, how the guidelines changed quite rapidly. And if LLM doesn't understand how the language changes and our knowledge changes accordingly, this can really damage its credibility. And for example, the output that it gives. So in order to tackle this problem, we developed a solution with the main aim of respecting the temporal dimension of language data. And this process was divided into two parts, with the first stage being the time-specific expert learning. And more specifically, basically, we trained each expert on 2 years of non-overlapping data in the range of 2013 to 2024. And basically, this allows us to eliminate temporal leakage so that the model has the correct temporal understanding of the language data. And then the second stage is the time-sensitive knowledge aggregation, as only restricting output at inference time to one model can be too restrictive and can deprive contexts. So that's why we have the aggregation step. Where we apply a mask, where the model, where during the inference time, the model only sees the experts that are corresponding to or previous to the timestamp of the query, meaning that we are not accessing any data from the future.
And our approach raises the question on how to actually combine the eligible language models. First of all, we decide to perform such combination in the log probability space in order to maintain the probabilistic coherence of the language model. Then we decide to perform a weighted average of the different log probabilities given as output by the eligible experts. So the question actually shifts to how to obtain such weights. First of all, we propose a naive averaging strategy where equal weights are assigned to every expert. Then we explore a learned average strategy where we introduce a one-layer multi-layer perceptron that is used to give weights learned from the data. So given the input, it predicts the weight for each expert. The training of this approach is performed while keeping the different experts frozen. Finally, we introduced a co-adapt version where the router structure remains the same, but in the training process, the expert corresponding to each input timestamp is unfrozen in order not only to inject into it the knowledge corresponding to that document, but to let this expert co-adapt to the other experts that he has to collaborate with in order to give the final output.
So regarding the experimental setup, we used as a base a GPT-2 medium model with 480 million parameters, and we pre-trained each language model expert. And then, in order to pre-train each of these 6 experts, we used 100 billion tokens from FineWeb Edu split into 6 time bins. The distribution of which you can see on the right. And each of these intervals cover 2 years of time. In addition, as Robin mentioned before, we have 2 learnable aggregation strategies, TMOE learned average and TMOE co-adapt, each of which is trained on 200 million tokens and 1 billion tokens respectively.
Another contribution of our work is the introduction of a brand new benchmark to analyze temporal hallucination in large language model. First of all, why do we need to introduce a new benchmark? The reason is that when we explore the existing time-sensitive benchmark, we noted 2 main things. First of all, some of them are based on pure text generation instead of a multiple choice setup, making this quite challenging for small language models. On the other hand, the benchmarks that followed a multiple choice setup did not give the chance to perform a temporal analysis on where the bias were, meaning if LLMs were achieving a low accuracy because they were giving answers in the past, in the future, or totally irrelevant. For this reason, we unified these 2 views into a multiple choice question benchmark where the answers are temporally tagged. In order to construct it, we start from timelines of time-sensitive events. For example, who won the Serie A, which is a question whose answer depends on the time in which it is asked. Then we use DeepSeek API to convert such timelines into multiple choice questions for every year. So the options contain, of course, the correct answer and then 3 temporal distractors taken from the timeline, so past or future with respect to the year of interest. An additional detail is that if there aren't enough options in the timeline to get to 4 possible answers, we ask DeepSeek to generate an irrelevant distractor as well. This process led to a total of 10,000 questions that we use to assess the temporal capabilities of our TimeOE family. A first interesting insight is that our family of models outperforms open source LLMs of similar scale, in this case Falcon 3, Qwen 2.5, and Llama, when it concerns our time-sensitive benchmarks. In particular, we can reach up to 15% improvement by the co-adapt model with respect to Falcon, that in this case is the worst performing one. Another interesting insight is that our aggregation strategy outperforms a baseline that we refer to as TimeOE year, which is in practice a hard-coded routing strategy, where the questions are directly routed only to the expert of the corresponding year, showing that our aggregation strategy helps in improving the temporal understanding of the model. Finally, to have a clear view on how we managed to increase the accuracy of the models, we can notice that there was a consistent decrease of past, future, and irrelevant answers as well when we look at the distribution among the models.
Now, moving on to the general knowledge understanding of the model, we evaluated this by scoring the model on 8 general purpose benchmarks. And on the graph, you can see the average scores of the models. So here we can see that TMOE models underperform compared to GPT-2 full model. However, it is important to note that TMOE models were trained on split data and then were combined, which may have affected their performance on the general knowledge understanding, whereas GPT-2 full model is trained on full 100 billion token dataset. Finally, we have additional benefit, which is the semantic evolution. So as semantic embeddings are time dependent, they can be used for evaluating the semantic evolution. And in order to semantically evaluate our models, we used cosine similarity between embeddings of word pairs, and we evaluated the semantic distance between them. And as an example, we took the words during related to the pandemic. For example, coronavirus, lockdown, face mask, and remote working. We can see that for all three pairs, the distance was the lowest during the year of 2019-2020, coinciding with the COVID-19 pandemic outbreak. However, alternatively, we can see that during the years of 2023-24, when lockdown was not as common, nor were face masks, the distance actually increased. So finally, to conclude, we showed that the TMOE can improve temporal accuracy up to 15% with respect to leading open source models. We can also see that TSQA allows to assess temporal understanding as well as temporal bias. However, there are also some limitations, such as, for example, the timestamps from FineWeb Edu correspond to the crawling date and not the creation date of a document, which may cause temporal leakage, as well as the models are trained on a relatively small-sized corpus, splitting into multiple language model experts further might limit general knowledge learning.
For what instead it concerns the future work, one interesting direction would be to scale our approach in terms of number of experts, so meaning more fine-grained temporal intervals, having larger and then more powerful models that could lead to higher accuracy, and clearly to train on more data to as well increase the accuracy of our approach. As an alternative strategy, instead, it could be valuable to explore a chronological checkpointing training where different checkpoints would represent different knowledge cutoff, replacing our aggregation mechanism that instead combines knowledge from the past via log probability weighted average. And with that, we arrived at the end of the presentation. Thank you so much for your attention, and then we are open for your questions.
Thank you.
Yes, thank you very much for a nice presentation. Any questions from in-person attendees?
It seems not for now.
Okay. And questions from online participants? Please raise your hand if you want to ask a question. Okay, I may start with a question. You mentioned, for instance, okay, I have two questions. So the first is, did you conduct some error analysis that you can share, for example, the mistakes that made by your models? Like what, maybe there's a hallucination problems, or there may be some, I don't know much details, but could you share, for example, what in which cases that the model, your methods may face the problems?
Yeah, I mean, our analysis was mainly to understand where the errors were done, because we just computed the log probabilities of the 4 options in the benchmarks, and then we picked the one with the highest log probability as the one chosen by the model. So in this case, there weren't that much room for hallucination in the sense that the model invents anything. It just had the option to choose among 4 possible answers, picked up the one that in his idea was the most suitable one, and then this answer could be the correct one, or past or future with respect to a certain year, or in some cases irrelevant, which in this case is a kind of sense of hallucination. But yes, the choice of the models were restricted to 4 possible options. So I would say that the analysis that gets closer to your question is probably the one in slide 17, if we can go there, where yes, we can see that most of the errors were committed in the future, like giving answers that are future with respect to the year of interest, even in our best performing model. And we have a slightly lower percentage of answers in the past, and finally a significantly lower percentage of irrelevant answers provided by the models.
Yeah, I see. Interesting. Then maybe the second question, we still have a few minutes. So when you talk about semantic evolutions over time, right? So for example, you showed like lockdown coronavirus and their distance changes over time. Then would you comment, for example, are there like the semantic change of the word, or for example, the meaning, the word sense change over time, or more or less the meaning is the same, unchanged. But so what are the, for example, what are the main factors that contribute, or the source of the semantic shift, in your opinion?
So I can answer this. So the way we extracted the embeddings was that, for example, we did a forward pass on a model with a word, and then we extracted the last tokens embedding from the last layer. And because we extracted this embedding as this, I think it gives a good understanding. It gives a good proxy of the model's understanding of the word and what it may be related to. And given that during the pandemic, we see all the related words that appeared at the time have a closer distance, it may mean that the model understands that these words actually became related, and it understood how our language evolved during that time period, as it was trained on that specific period of time data. So yes, this is what I believe.
I see. So if I understand you, it's not about the semantic change, it's about the concurrence of the, like two words appear together, maybe more often. Their concurrence, they're the shift over time.
Yeah. Robin, you wanna?
Yeah, no. I would say that this means more that the models in its embedding space puts them more closer. Yeah. This is the sense of our work. Then the laying cause may be the fact that in the data of the 2019, 2020, those words used to come closer together, but we haven't performed any correlation analysis, and this is just what the model has in its embedding space, the one that we can extract, as Tamar said, from the last layer. So yes, this is just a model, not anything related to the data.
Thanks.
Thanks to you.
Okay, now let's move to the second presentation. Is the speaker here?
Yes, I am.
Yeah.
Hi.
Hello. Could you share the screen?
Yes, just a second. Oh, just a second. I see. So I have to leave the chat and then re-enter, unfortunately.
Yeah, no problem.
Just a second. Okay, maybe we can go on with the next speaker for a bit, because it seems like my browser does not really allow to share.
Okay.
Maybe I can try to open another browser. Just give me 1 minute.
我看你练一下。
Okay, can you see my screen now?
Yes.
Okay, let's probably open like this. Can you see the slides?
Yes.
Thank God. Very sorry for this. It's just I was using a new browser and it seems not to work with screen sharing. So hi everyone, my name is Aida Kostikova and I'm a PhD student at the Bielefeld University. And today I'm going to present our survey on limitations of large language models, or how we abbreviate it, we call it LLMs. So this is not a typo, this is just abbreviation for limitations of large language models that we use. But first of all, why study limitations of LLMs? Well, we talk a lot.
I'm sorry, could you please move to the first slide, because now what we see is the slide number 7.
Just a second. Let's do it like this. So you should be seeing my full screen now.
Yeah.
Do you see the first slide?
Yeah, it works.
Okay, good. Yes, and we talk a lot about the capabilities of LLMs, what they can do, but we also increasingly talk about their failures, because we want them to be safe, we want them to be effectively deployed, especially in high-stakes domains like healthcare. However, the existing surveys at the moment focus on specific limitations, like there are papers on reasoning, papers on hallucinations, and so far there is no survey on limitations of LLMs which would look at them in general, systematically. And we aim to close this gap by providing a data-driven, up-to-date, and cross-cutting overview of LLM limitation research. So we aim to answer the following questions. What types of limitations are most frequently studied in recent LLM research? How has research on LLMs itself evolved in scale since 2022? How have the prominence of different limitation types changed over time and across venues? And how consistent are those trends across different clustering methods? So I mentioned that this is a data-driven survey. So we basically start with crawled papers focused on LLMs and limitations, and use clustering approaches to find limitation topics. Let me explain this by going over the methodology pipeline. So it starts with dataset construction. We first start with data retrieval from ACL ontology and archive. We include categories like computational language, machine learning, AI, and computer vision from 2022 to 2025. We extract titles and abstracts, which are in the following useful clustering. But to save us some time and also to be more precise, we want to filter for those papers which are focused on LLMs. So we used a keyword list This keyword list is iteratively defined and automatically defined. I'm not going to explain this in detail, but this gives us 90 LLM related concepts. And using those keywords, we extract papers focused on LLMs. These are just some statistics about crawled papers and filtered papers. And then we want to take those papers which are focused on limitations of LLMs. And we do that with LLMs. So they're basically scoring the papers on the extent to which each paper discusses limitations. But to check whether LLMs are actually good at it, we construct a human annotated data set where annotators rate each paper's focus on LLM limitations from 0 to 5, where 0 is no mention of LLMs and 5 is exclusively about LLM limitations. So this looks something like this. You can see the abstracts of some papers. Annotators give the score about to which extent limitation is discussed, and also highlight the evidence which point to the exact limitations discussed in the abstract. And those highlighted evidences, which are further annotated by a model, are used for the clustering. And we only use those which were scored 4 or 5, so extensive discussion of limitations of LLMs. This is annotated by 4 researchers, and we achieve a weighted Cohen's kappa of 0.75. We use weighted here in order not to penalize too much the confusion between neighboring scores like 0 and 1. And those highlighted evidence spans we evaluate with F1 on a tagged sequence. And this and annotators achieve F1 of 0.71 on average. For the models, we choose GPT-4o, Llama 3.170 billion, Mistral 7 billion third variant, and we evaluate them on 5 different prompts to find the best model. And our evaluation shows that the best configuration for this task is Llama, and it approaches human agreement both on scoring for limitation discussion as well as for evidence extraction. Using this model, we filter papers focused on limitation of LLMs, and then we use this data set for clustering. So we only use those highlighted evidences which were extracted by a model. We use 2 clustering approaches, HTTP scan and Loom, and then those clustering results are used for time series analysis to track the trends of how limitations of LLMs have evolved. Just to give you an idea of why we used 2 different clustering methods, first we wanted to compare how stable the trends are. So HTTP scan, probably most of you know about the method. The second method is also using an LLM on top of HTTP scan. So it assigns a concept in natural language to each cluster identified by HTTP scan. And then in the second step, it remaps every document again to those concepts which were identified in the first step, also with the help of LLM. And the main reason why we use this is that the second approach allows for a multi-label assignment for a cluster, whereas HTTP scan allows only one label. So we finally come to the results. First, we're going to look at the trends of LLMs and limitation papers trends over time. So here you can see the proportion between LLM papers in relation to all crawled papers we have. So here the result is that LLM research is growing rapidly, as you can see, from 2022 to 2024. By late 2024, LLMs account for almost 80% of ACL papers and over 30% of archive papers by 2024. Then we additionally look at the proportion of limitation papers among all LLM papers. So this is a different proportion we look at here. And here we notice that research on limitations of LLMs grows even more rapidly, with 1 in 3 LLM papers now addressing limitations, both on archive and ACL. So probably I'm gonna skip the results with HTTP scan. So maybe one thing here, just to give you an idea, both for ACL and archive, it identifies such topics as reasoning, security, social bias, and hallucination. However, this method also resulted in a lot of outliers, and therefore we decided to look at Loom first. So here some of the interesting topics are knowledge editing, language and cultural limitations for ACL, multimodality, privacy risks, computational costs, and so on. For archive, it's also trustworthiness, which was the biggest cluster for archive because it was basically containing also a lot of papers were there because basically every problem related to LLMs is in the end a trustworthiness problem. There are also problems like alignment, prompt sensitivity, privacy, and overconfidence. So first we look at how visible those limitation topics are within the whole LLM research. So these plots reflect each topic's proportion out of the total LLM focused papers. And you can see that from year to year, the topics grow, almost each topic, every topic here. For example, reasoning grows from 5.5% to 8.9% to 2024. But the problem here is that we noticed that limitation topics grow because LLM's research grows itself. So this does not reflect the actual interest of the limitations research, but reflects the overall growth of LLM research itself. That's why we look at percentages which reflect each topic's proportion out of the total limitations focused papers. So here you can see the plots for ACL. You can see here that most limitation topics remain stable from 2022 to 2025. You also perform significance tests to see whether the trends are significant or not. And here, unfortunately, we saw that the only significantly rising topic is long context, which is this green line. And no topics show statistically significant decline in ACL. But just looking at the trends visually, you can see that language and cultural limitations and bias are declining. However, they're not statistically significant. For archive, also most limitation topics remain stable, but significance tests show that multimodality, the gray line here, security risks, the pink line here, alignment limitations, the red line here, rise significantly. And generalization, the green line here, and bias and fairness, the brown line here, decline significantly. These are just some additional plots. We also compared the trends, which we got with HTTP scan and Loom, compared the trend direction, whether they were significant or not, also the Spearman correlation between the trends. And we reflect the results in match column. So we did that to just see whether the trends hold across both clustering results. We also matched the clusters using the Jacquard similarity. And the tick here signifies whether trends match both in trend direction and significance. And we saw that in ACL, generalization and social bias are both flat in both clustering approaches, and in archive, multilinguality and reasoning are both flat. Also on archive, multimodality, hallucination, knowledge editing, and security risks increase in both clustering methods. And finally, in conclusion, we saw that LLM research is now clearly dominates NLP. Between 2022 to 2025, 1/3 of all LLM papers now address limitations. Reasoning is the most frequent limitation and is followed by generalization, hallucination, bias, and security. Research in general is very diverse and increasingly interdisciplinary. We saw that safety, alignment, and controllability issues gain traction, and bias and fairness decline. We also see the increase in multimodality research, which expands after middle 2023. This I'm going to skip unless you have any questions further. Here are our reference, and that was it. Thank you very much, and sorry for the technical problems.
Thank you very much for your presentation. And questions from the audience?
Maybe one question here is, so your strategy to obtain the paper, filter them using a large-scale analysis, do you think could be replicated for other types of survey type of applications, automated survey, like other than limitations?
Yes, I would say so. So I don't think that it's only limited to LLM limitations. You just need to adapt the prompts, but I think this approach can work with basically any other surveys and any other papers. So
Yeah,
this
thanks.
is quite a universal pipeline, I would say.
Yeah, and with your human annotation, so you think it was pretty solid, the the parts that were taken care of by the LLMs?
Yes, the LLMs were actually quite good at it. Not Mistral, but GPT-4o and Llama were very good. They were very comparable. We just decided to go with Llama because it was cheap and we could run it on our cluster, but it was quite good. So it was comparable to humans.
Okay, thanks.
Yeah.
I have a question about the setup of your pipeline, which is based on the abstract, right? If I understood. Abstract, you look at, for example, the model to see what limitation topics are discussed in the abstract. But there are almost all the papers, they have limitation sections. So would you comment on if your pipeline is based on the limitation section of the paper, what would be the difference?
Yeah, so we only included titles and abstracts, and we actually haven't thought about also including the limitation sections. But I would say that in this case, probably including limitation sections would be something different, because there they discuss the limitations of methods. And we are interested in the discussion of limitations of LLMs. So, for example, in abstract, they would say that we are looking at the problem of hallucinations in large language models. Whereas in the limitation section, they will say, yeah, our method was not so good because of this and this reason. So this would be a bit probably confusing for the clustering method.
Thanks. Any other questions from the audience? Okay, if this is not the case, yeah, thank the speaker again.
Now let me turn this off.
Okay, let's move to the next slot. Yeah, please share your screen.
Hi, everyone. Just checking. Can you hear and see my screen as well?
Yes.
Okay. Hi everyone. My name is Gagan. And today I'll be presenting a paper which is Date Fragments: A Hidden Bottleneck of Tokenization for Temporal Reasoning. Our main goal was basically to understand how these tokenization that actually breaks date into different fragments, and how does it actually affect the AI's understanding of time. And I would really like to thank my amazing co-authors on this paper as well. And so I think the main problem with dates in itself is that the PP tokenizers that most of the large language models use They basically tokenize the input tokens into fragments that don't really look like exact dates. Like when we do not really have like a separator there. So this would mean that the model that actually the LLM is not really seeing the date as it is, but it's actually just seeing like broken fragments of a date. Which means that it's quite likely to actually misunderstand a date and like actually make a temporal reasoning mistake. And that is why we actually like try to understand like how like much actually is it really a bottleneck. And the one of the main major problems is that if we lose the natural structure of a date, then that means that like we're actually losing the structure of the date, and that means we're actually losing all the meaning of the date. And secondly, it actually makes the computational cost and the processing of the date more expensive as well, because we're inflating the token cost for no reason. And finally, this actually means that we are actually leading to more significant scheduling and planning errors. And this would mean that we cannot really use LLMs to just like create calendar invites and just create like appointments and stuff like that as well. So because of this, this is a pretty significant issue. And so our contributions are like finally that we introduce a new metric, which is date fragmentation ratio, which is a simple interpretable score to measure how faithful a tokenizer preserves the date component. Finally, we introduce a new benchmark, which is called DateOg Bench, which is a comprehensive data set of 6,500 examples crossing three temporal reasoning tasks to test LLMs on different date formats and different time periods as well. And then we also try to understand how date abstraction works. How do LLMs actually understand and like understand these dates? And one thing that we do discover is that LLMs are able to internally heal themselves and actually are able to fix these fragmented dates and actually come up with an understanding of these dates. And finally, we discover the reasoning path of how these models actually go from like taking these date fragments and actually putting them together and stitching them together and coming up with a final answer. And so for like going on to into a date fragmentation ratio, so it's basically a quantitative score which goes from 0 to 1, where 0 to goes perfect tokenization and 1 for severe fragmentation. That basically measures how well a tokenized date is compared to its ideal semantic components. So if we actually look at like a perfect tokenization, let's say if we have like 2025, a dash 0, 3, and 14. Here the date components are preserved with clear boundaries, and all of these are maintained. So this tokenization means that this date actually still has a particular meaning. But when we put it like every single individual digit, this this basically means that the structure has basically been lost, and this is just like a pile of numbers, and it doesn't really represent a date as such. As we see here as well, like when we have a date which is more in the past, these tokenizers actually tokenize them in a much more random manner than in a more like date specific order. So which means that like this is not really where so tokenization. So there is a significant flaw in the tokenization process in itself. To come up with this data fragmentation ratio, we actually use human ratings, and then we created a formula to come up with these scores. So one of our main contributions is that the data fragmentation ratio correlates very well with human ratings as well, and it has the highest Spearman correlation metric across all these metrics to judge the fragmentation severity. So our metric actually uses 4 different tokenization errors, and we try to understand how these components are split. We check if any of these delimiters are lost, and then we also see if the token count is being inflated way beyond the ideal semantic count. And finally, we try to understand the distributional divergence from between the ideal tokenization and the tokenization that the model has come up with. So using this, we actually understood that there's a significant flaw in the tokenization itself. But our next question was that does this really actually matter to us? And does it actually really making a difference in the performance of LLMs? So for that, we came up with a benchmark which is called DateOg Bench. So this is a pretty interesting benchmark because here we used multiple different date formats across multiple different time periods. So we actually use across like 21 unique formats. Some of these are more repetitive, and it's quite possible that we have two different date formats in the same question as well. And so we have three different tasks. One is just context-based questions, which is basically something like which team did Omnavi play in like a particular day. And then we have the date format switching task where we have two different basically we have like two different dates, like, both of them are like in different formats, and we are asking the model to understand if they're actually the same date or the different date. While this might seem like a really simple and intuitive task, this models actually do struggle a lot with this. And finally, we have the date arithmetic task, which is basically a simple arithmetic calculation for a given date in different date formats. This data set was built using augmenting different data sets from different sources like time QA and time bench, and we've augmented them using these different date formats. And a key result is that higher fragmentation leads to lower performance. Now these things, we actually do notice that there isn't really a very strong correlation here, and then we notice that this is a mediocre or a moderate correlation, negative correlation here. Which is why we actually investigated further into so there has to be a reason why even though the structure of the data is changing completely, the model is somehow able to actually configure these things together, and is actually able to piece things together and actually be able to come up with the answer. And one of the other things that we noticed was that when we use a more structured date format with like proper separators and stuff, that actually gives a model a much more hint about what the date is about and what the date is actually talking about. For that, we actually dug deeper into actually understanding how like an LLM understands the date. In that case, we actually found that in every model, depending on the number of the layers it has actually has a tokenization compensation point, which we define as TCP here. And at that point, these different tokenizations and like stuff, the model is able to overcome the problems with tokenization and piece things together and come up with the theory that, oh, this particular tokens like these together refer to a date. So we used a variety of Quen 2.5 models from like 0.5 billion to 7 billion models. And then we trained linear probes on each of these layers to actually understand how these things are changing and how the model is actually understanding at every layer and how the model is getting more and more confident. So our results were pretty interesting because what we noticed is that the model scale is pretty crucial, because let's say the 7 billion model is actually able to understand pretty soon these dates work, whereas the smaller models need much more depth. And in a lot of cases, the smaller models are not even able to actually understand the date as well. But interestingly, we did notice that the present period models actually perform pretty lower than actually we would expect. And this similarly generalizes to a larger time period as well. So this actually begs the question that how is this even happening? So for that we performed something which is called causal path tracing, which is a causal analysis method where we actually mechanistically try to understand how the flow of information is happening, and then we just use a simple date and basically a data abstraction question, and just try to answer and understand how the model is actually answering this question. And finally, we trace the path that the model took internally to come up with the particular answer. This method has been really popular in recent literature, and a lot of people have been using it to understand how the models have been using it, how the models understand information internally, and how this actually can be traced throughout the model's layers. So what we notice is that models actually use a very different path than humans do. It is really interesting because given a date, which is 03/12/2025, a normal human would split it into 03/12 and 2025, whereas the models split it into 20, in 25 220, 031, and then they understand that it's a date and then give us an answer which is yes. So this basically indicates that like they are not really using like a rule based, like a holistic schema that humans use, or like a more calendar based setup. They're just using like statistical, like step by step token aggregation. So like things that they've seen like that come together. So they're just basically trying to do the next token prediction on this. Well, this method works in some cases. This is a very brittle method. This basically means that there is a problem which is being caused by the tokenization, by the improper tokenization here. This indicates that we are actually setting us up for failure, because as we have indicated before from our benchmarks as well, that this is a significant bottleneck that is there in models itself. And finally, in our takeaways, we've actually indicated that date tokenization is a critical flaw and it is quite often overlooked. But this impairs the temporal reasoning performance at a significant stage. While it is actually possible that like larger models have a greater emergent ability to heal, and they are able to like compensate for poor tokenization, this also makes it more expensive to run, and that actually has its own problems as well. Even though different models tokenize dates like differently and stuff, but all of them do use a very different method of understanding these dates that compared to humans, which means that this like the statistical form, like the fragments to stitching date, is not the best way to understand dates and actually perform temporal reasoning tasks. And like in the future, there can be many ways to like update the data where like tokenizers and stuff. But we primarily focus on like Gregorian calendars, and we do not really cover like more noisy inputs, like we're like more vaguer inputs. Our work is more focused on trying to understand how the date tokenization actually makes an impact. You can scan the QR code and find our paper as well. It's been published in our archive for a while now, and you can actually just scan the QR code and find our paper. Thank you so much. Would love to take any questions if there are any.
Thanks a lot for the presentation. And questions from the audience? And questions from in person?
No, we don't have questions.
Okay. Question from online participants? Okay, I may ask a question. So yeah, the setup on the paper is mostly in English, based on the data format in English. What do you think, for example, what changes would potentially be made to adapt to another non-English context? For example, the dates in different languages, maybe the dates in different calendar system, for example, Gregorian versus non-Gregorian calendars. So what do you think would be the potential changes you have to make in order to accommodate other languages?
So I think this is like a research question that we've actually been like pondering and like we've been having a lot of discussions about lately as well. But I personally think that like this kind of like stitching of tokens in like non-Gregorian like calendars would be much lesser. Sorry. But I think like the models would find it much harder to actually understand the date and come up with a better answer as well. So I think that still remains like to see problem. And plus, non-Gregorian dates are tokenized much worse than like more standard dates. So that would lead to a much bigger problem as well.
Okay. Yeah, thanks. Okay, if no further questions, then let's move to the next speaker of the morning session.
I think that's me.
Okay.
Is it the last slot? Then it's me.
Yeah, please, can share the screen.
All right. Let me see. Okay, maybe I also need to drop out. Oh no, I think it works. Okay, can you see my screen now?
Yeah, it works.
Perfect. All right. Okay. So now I also need to see the slide. Okay. All right. So yeah, thank you very much for having me. My name is Carolyn, and I will present our work, which was published at the ACL this year. Bear with me a little, I'm a bit sick, so I hope my voice doesn't crack too much during the presentation. Yeah, our paper is called Around the World in 24 Hours, Probing LLM Knowledge of Time and Space, which was published with my great co-authors from the University of Hamburg and the University of Bocconi. Before we start, let me quickly motivate the topic why we started looking into this anyways. So we have done literature review for sure, and we've seen that a lot of projects have been looking into temporal knowledge, temporal reasoning. There are a lot of benchmarks around that. Also, there have been a lot of research on geographical knowledge. However, we've seen that the landscape on geotemporal knowledge is rather scarce. So current research provides only limited insights into the ability of models to combine temporal and geographical knowledge. Also, often they have rather artificial settings for the evaluation, such as multiple choice. And if we're looking into real-world examples and applications such as planning and scheduling globalized activities, then this is a very essential task. So in our project, we wanted to answer these three questions. First of all, how well do LLMs reason about time, place, and their combination? Then what factors influence model performance on geotemporal tasks? And finally, can model performance be improved by injecting geotemporal knowledge? This kind of goes into the direction of, can we not just use tools to do this? So hopefully we'll also get a bit of an explanation in this direction. Okay, since there is no suitable data set at hand, we first craft a data set that fitted our needs. So specifically, we first create 4 different tasks that require a different amount of geographical and temporal knowledge. Starting with an example sentence like this: today is 5 p.m. in Paris. What time is it? The 4 tasks look like as follows. First of all, we have a verification task. This task is really simple. So basically, as you see, the model doesn't need to apply any kind of knowledge, because in the end, it would just need to look into the input prompt as is and extract the correct information from there. Then our second task, the model needs to perform the correct temporal knowledge, including time formats and mathematical calculations. And then for our 2 more complex tasks, we are asking the model to provide the time now in another place, or also now in a couple of hours in another place. So here we incorporate the geographical knowledge on top. From these tasks, we craft our data set carefully. Therefore, we compile 289 locations covering all 37 UTC time zones and 217 countries. We build the Cartesian product between all location pairs, meaning each location paired with each other location in both directions, and then initialize task templates with all location combinations, varying timestamps, and 3 instruction types, which I will explain in a second. And overall, our data set then covered over 330,000 evaluation prompts. You can also see all the locations that we cover in our data set here. You can see that they're pretty much spread out all over the world. It includes larger cities, smaller cities, and also places in Antarctica, for example. Looking into our experimental setup, we evaluate a variety of different models and sizes. We primarily focus on open models. However, we also perform some tests with GPT-4o mini on a subset. However, our study mainly focuses on open models. We evaluate our dataset with 3 different prompt variations. One is what we call the neutral prompt. So we have no additional information, no additional instruction given to the model. So this would just be the question as I've showed before. So what time is it now in Paris, for example? Then we also include chain of thought prompting, where we just append things step by step to each prompt. And also we evaluate a short prompt variation where we ask the model to keep their answer short and just answer with the correct time and date. And yeah, finally, since we are dealing with open-ended model responses, we also need to validate the model answers. So therefore, we create a custom algorithm, which is based on multiple regex patterns. We evaluate this algorithm on a test sample of 3,600 model responses and obtain an accuracy of over 98% accuracy per model, meaning this is a pretty reliable evaluation protocol. Okay, let's dive into the overall results that we obtained for each of the models across all of the 4 tasks that we evaluate. Here, I'm showing the results for the neutral prompt and also significance confidence intervals for 3 different prompt formulations, where we just changed some slight wordings. Overall, we observed that the performance varies drastically across models and tasks. Model performance increases with model scale, which is not really surprising. What is more surprising, however, is that most models seem to struggle with our very simple verification task, while performing better on the time, so the time shifting task. This might be probably due to ongoing training on mathematical problems, which also include these like time shift changes, and also simple or even rhetorical questions is not really something that we would usually train on in pre-training. So it might be that the models were just they didn't really know how to respond to these very simple questions where the answer was already in the prompt itself. We also find that all models struggle with the more complex tasks. So these are the tasks where we also include geographical, or the models also need to apply geographical knowledge. So none of these models are really able to perform, I would say, well, since this is not a task that is very difficult or should be very difficult for these models. Next, we want to look into factors that might influence model performance. Here we are focusing on the best performing open model, which is Llama 370B. First of all, I am presenting here the results for different instruction prompts. And what is interesting here is that if we ask the model to keep the answer short and concise, this leads actually to a decreased performance for the very complex questions instead of the neutral prompt. However, most models, and also most of the other models, perform better when it comes to the simple task. Also, conversely, which is very interesting, we found the contrasting pattern for chain of thought prompting. So for most models, the prompting strategy decreased performance on the simpler task, while yes, for other models, you cannot see it here, but for other models, it did increase a little bit for the more complex tasks. We also wanted to look at, is there maybe a country bias, because a lot of previous work has seen country level biases, meaning that models perform better for Western countries, but we couldn't really see that. In contrast, we actually saw that the models performed quite well for African countries. And then finally, we hypothesized that the familiarity of the models with certain locations leads to them performing better in a task. Since we do not have access to the training data, we use model perplexity for a certain location name as a proxy for familiarity. Here, for most models, we actually observe a gradual decrease in accuracy from low to very high perplexity locations, with a surprisingly high performance drop between countries that had or locations that had very low, and very high perplexity combinations. Our findings thus suggest that yes, familiarity with certain location names, maybe during pre-training, can actually improve model performance on this task. Finally, we couldn't really find a real pattern in like location information. So we wanted to look into where do models fail, can we maybe guide them to perform better. So we have seen here, okay, the very low perplexity locations perform better. So what if we give them the geographical knowledge right away? So therefore, we evaluate 3 different setups for this very complex task, where we not only have a time shift, but also a location shift. Here you can see the results before, and we evaluate 2 different settings. One, where we add the time zone information into the prompt, meaning we say, okay, Paris, UTC, -1 plus, I'm not really sure. Let's say -1. And another setting where we say Paris, where we do not say Paris, but we say from a location in UTC time zone -1 to another location in UTC time zone. Blah. So these are the 2 different setups. We provide the model with the UTC information, so basically it just needs to do the correct time zone shift calculations in the end. And what we can see is that for most or for all models, actually adding the time zone information does increase the performance. So especially for Llama 3 and Qwen 2. However, for Llama 2, the gains are not really, we cannot see very large gains. So it's really model dependent, meaning that Llama 2 maybe is just not really able to fulfill this task. What is also interesting is that we actually do not see a very large gain from replacing the location by the time zone information. So this is very interesting. We actually often see a drop, meaning that the geographical knowledge is actually, so the models really do draw some information from the location information to be able to fulfill this task successfully. It's not only about, okay, knowing how to proceed with time zones and so on. All right, so let me summarize the key takeaways that we found. And there are a lot of bugs involved. So first of all, we found that most models can handle simple time-based calculations, but they struggle when additional geographic reasoning is required. Second, we find no clear regional gaps, but a strong correlation between model performance and the complexity of location names. And finally, we do see that geotemporal knowledge exists, but it somehow requires some activation for the complex task. So this might be in a way as we did it with injecting the UTC knowledge additionally. So this was my presentation. Thank you very much. If you have further questions and would like to reach out, I added my LinkedIn here. Also, if you're interested in the paper, yeah, feel free to read it. Thank you.
Yeah, thanks a lot for the presentation. Questions from the audience, from the room?
Yeah, maybe one question is, so you say that geotemporal knowledge seems to exist, but it needs to be kind of surfaced in some way. So maybe does it mean that we could include some of these tasks in the post-training of LLMs such that it would surface more naturally?
Yeah, so I was presenting this paper at the ACL, and there were a lot of questions regarding this. Also, I think also that the bigger issue is that the models fail if they have to take two different kinds of knowledge. In this way, it's like temporal and geographical, to really combine them and apply them meaningfully. So what we have also seen is that when we actually ask the models only for the UTC information of a certain location, they were able to provide it in like I think I have it here. In here, for example, for Llama 370B, the models could provide in 90% out of the cases, they could provide the correct UTC knowledge. We also have seen that they can apply these temporal calculations. So it's more about combining those two. So when the model really needs to extract this knowledge and this knowledge, that they cannot really combine the two. I'm pretty sure that if we do post-training on exactly this task or have more of this task in the pre-training data as well, and maybe also with the newer models, we haven't tested O3 or any other models at the moment, but I'm pretty sure that the models would be able to be much better or perform perfectly when they have been explicitly trained on this. But I think the bigger issue still persists, that when then they need to incorporate some other kind of knowledge or some other kind of knowledge, which is mostly required for planning, right? That they would fail again. Does that answer your question?
Yes, thank you very much.
Sorry. Any other questions from the audience? Okay. Yeah. Thanks again, the speaker, and that concludes the morning session. Then see you in 1 hour and a half, 1 hour 30 minutes, and for the afternoon session to start.
Okay. Yeah, see you at 1:45 for the next.
Okay. Yeah, thanks.
With graphs workshop at KDD, and also the Women in Machine Learning workshop. So we are very happy to listen to what you have to say today.
Thank you. Hi, everyone. Yeah, thanks for the introduction. So, sure. Is that better? Yeah, I'm going to be talking about evaluating temporal reasoning in large language models. So here's the outline of my talk. So I'm going to start with some motivation, specifically from graph reasoning, and then I'm going to show how we did temporal reasoning with LLMs, and also how we make that extra hard. So starting with motivation, the motivation here is that temporal reasoning often involves a structure. So temporal reasoning is not just about comparing different timestamps, and sometimes there is a structure behind that that shows how does multiple time-dependent entities interact with each other. That's why graphs and structure behind all of this is important as well. So because of this, I'm going to start motivating from graph reasoning and then connect that to temporal reasoning. So in this specific work that I'm going to start explaining, we evaluated graph reasoning with LLMs. So we have a graph, and the question is, what's the best way to encode the graph as text so that the LLM would be able to interact better in textual space with the graph? So we're going to ask some questions about the graph, and then the one graph is in the input, and the LLM, a frozen LLM, wants to answer questions for the graph. Yeah, and the question is how to best encode graph as text. And we're talking about text because that's the most dominant LLM interface. So we want our LLM to be able to interact with the graph and the questions that we provide. So here's an overview of the framework that we used. So we have a graph in the input and also a graph task, mostly graph reasoning type problem, like graph theory questions. And we want to encode the graph as text and also the task that we have at hand as text so that we can combine all of this in a prompt and we can feed the prompt to an LLM to answer our question. For instance, here, let's say we have G describes a graph among list of the nodes and then list of the edges and a question like, what is the degree of node 4? And the LLM is supposed to look at the prompt and by only looking at the prompt, answer the graph reasoning question. So the goal is sort of finding a graph encoder that can maximize the score that the LLM can get over, let's say, a specific data set. So to be able to measure this, we created a benchmark called GraphQA dataset. So our benchmark has different graph reasoning tasks like edge existence, maximum flow, connected node reachability, a different type of graph theory questions that you can think of. And then we wanted to examine different LLMs, evaluate how well they can do for this task at hand. So the first question that we had here was that, does the structure of the graph matter? So when looking at graphs, depending on the application, they might come from different structure. So for instance, Erdos-Renyi is one very popular graph structure that is mostly used for theory and analysis. Also in a lot of applications in real world, graphs are Barabasi-Albert, like they have a power law distribution, like social network, citation network, etc. So each application might come from a different structure, and that's why we were curious to see whether the structure of the graph would matter in the output that you get. Now, another question was, does the encoding of the graph matter? So now here we want to convert our graph to text. So how we do that? Does that really matter? Let's say in some cases you can convert a graph to an adjacency matrix, like listing all the nodes, or sometimes you can have it as like one node and all the edges next to that, or even sometimes you can be more textual, have, let's say, a friendship graph. Instead of saying that two nodes are connected, saying these two people are friends, or some experiments like that to see whether that matters for the LLM or not. So yeah, let me quickly jump through the results that we have for this work. So yeah, graph structure indeed has a significant impact on the LLM performance. So here in this chart, in the x-axis, we can see different graph reasoning tasks that we have, and in y-axis, we have accuracy. And each color is representing one graph generator that we had. Let's say Erdos-Renyi, Barabasi-Albert, etc. And as you can see, for the same task, and even same LLM, we can see that the results vary a lot, which shows that the type of the graph that we are working with has a significant impact on the performance that the LLM can get on the task. And our second question, does graph encoding matter? The answer is yes. It also has a significant impact. Here we can say in this chart, we have, again, different graph encoders in different colors. And these are exactly the same graph. So the only thing that is different among these is the encoding of the graph. So same graph, same answer, but we can see that that has a huge impact on the LLM performance. Then we were thinking that we are working with a graph, and then graph has a specific inductive bias. Why not, instead of trying to linearize it to some sort of text, use a specific encoder for the graph that can convert that to some tokens, and then we can ask our question from the graph given the token. So this is our second work on this topic called graph token. And because we are talking about graphs in our specific encoder, we had a GNN, like different layers of graph convolution layers that can get a graph in the input and directly convert it to some graph token. And with this, so here are a summary of the results. The first 5 lines are about converting to text, and last line is about using GNNs for the encoder. And these are with PALM2S, so newer models are even much better compared to the numbers that we can see here. So yeah, this showed that even like using a specific encoder for our graph problem can help in this setup. Okay, so this was my motivation, mainly from graph reasoning, and now I want to move to temporal reasoning and show our motivation and how we use the ideas there here for temporal reasoning with LLMs. So I'm going to start with a motivating example, a specific example that would show some aspects of the work. So here I'm going to show the same temporal query, but once with real entity names and once with anonymized entity names. And then we're going to show how would the model react when we use real versus anonymized entity names. So here's the prompt that we had. Below are the list of head coaches for Chelsea FC, and then a question about like who was the coach before Pochettino. So here there are some temporal facts listed, and a question which is again temporal because it's asking about who was like a person before an event happened. So in this case, we tried this. So this is sort of grounded prompt because all the entity names are there. We tried that with Gemini at that point, and Gemini was able to answer that correctly. We just changed one thing in this prompt, converting all the entity names to anonymized entity names. So let's say the question was, below are the list of head coaches for a club. Who was the coach before E5? And then listing everything, getting temporal, everything the same, just anonymizing entity names. And model wasn't able to answer this correctly. Same model. So here, we saw that the model correctly answered the query with real names, but failed with anonymized names. So this suggesting LLMs might rely on their parametric knowledge to solve temporal tasks. And then we looked at existing benchmarks for temporal reasoning. Most of them were based on question answering on knowledge graph style temporal facts, which was very similar to the first prompt that we had. And yeah, and most of the existing benchmark are real, using real KGs, and that underemphasize the diverse temporal structure that might be in real world, in the temporal structure in real world. So yeah, we were thinking of creating a benchmark for this for temporal reasoning with basically 2 things in mind. One, to disentangle temporal reasoning and knowledge grounding. So again, getting back to the example, to mostly focusing on using, let's say, anonymized entity and relations. So we make sure the model will not necessarily using the parametric knowledge for answering those questions. And also considering diversity in mind. So for that, we created 2 different benchmarks. One focused on TOT semantic, focused on understanding the semantic and logic of time, and the other one, TOT arithmetic, focusing on the ability to carry out temporal arithmetic. So we're going to go through each of these. So to create our TOT semantic benchmark, we first generate a graph showing the underlying structure that is behind all these entities interacting with each other in the temporal space. So now that we are at generating graph, let's look back about this question. Does the structure of the graph matter? So in the other work, we showed that the structure of the graph matters significantly. So for this, we made sure that we create graphs of different type of structure so we can properly analyze that for temporal reasoning. Then we assign entity and relation names, anonymized one, to the nodes and edges of this graph to be able to convert them to text, like generate temporal facts, like E11 was the R21 of E23 from, and then a timestamp, and also being able to generate a question from that, like which entity was the R17 of E23 at the time when another event happened. So here are also some examples of each question type that we had in our semantic subset, first and last, which entity was the first that was at another time of event, or before after question, event at what time question. So we tried to come up with a diverse set of questions that one could ask to be able to go beyond knowledge graph style questions and make it closer to real world applications. So for our second subset, TOT arithmetic, so in this case, this subset is more about diverse set of questions that you can ask when you have like different operations, arithmetic operations in time space. So for that, we started with a seed set of questions that we had in mind, and then we had a small set of annotators, expanded the seed set into a large set of questions. We filtered those that are knowledge heavy and like very corner cases to make sure everything's general, categorize those to smaller subsets, and try to functionalize them so we can synthetically generate a lot of data with that. And by functionalize, what I mean is, let's say there is like one specific question, we write a Python code that can generate question and answer that to make sure that we can generate diverse questions and also have the ground truth for those questions. And then we sample using the code base that we generated based on these functions. Again, some example of arithmetic question, like add and subtract when the model needs to compare different timestamps, or can like calculate duration that something took, or schedule something when you provide some availability, and yeah, these type of questions with arithmetic operation. Now let's jump to the results that we had for this work. The first question, again, about structure, investigating the impact of structure on LLM temporal reasoning. So here we have, in this chart, I have different graph encoders in the x-axis and accuracy. And as we can see, numbers vary from one encoder to the other one, sorry, from one generator to the other one, which shows that graph structure has a lot of impact in the results that you can get. And that's mainly important because, as I said, in different application, you might see different type of graphs. So maybe temporal reasoning in one application would work, and in the other would be not working as well. And so yeah, we can see here, for instance, GPT-4 accuracy more than doubled from one graph structure to the other one. Another important thing here to consider is, so there is this one specific type of graph structure that we use called AWE. So these are, an AWE is anonymized Wikidata entity. So this is the graph structure that we got, not using a generator, but instead using using Wikidata, using a KG, using EgoNet of entities, and then generating questions for that. So this is more closer to the KG style one, still anonymized entities and relations, but the structure is following what you would see in a KG. And as we can see, results are way better for AWE graphs compared to the other one. And this highlights that critical gap in temporal reasoning that I just explained, as if we largely overlook the diverse graph structure and reasoning task found in real world application, and instead focus on what we saw in, let's say, KGs, for instance. And as we can see, Sonnet 3.5 nearly solved the task with like 96 point something accuracy. Now the question is, okay, graphs, the structure matter. Now let's look at different properties that those graphs might have. So for instance, number of edges that you can see in the graph, which is a measure of size of the graph that you're working on. So in this chart, we can see performance of different models for different buckets of number of edges. And the trend is mostly downward, showing that as we get more edges in a graph, the model usually performs worse. Well, there are some exceptions in this case, like Gemini 1.5 Pro, which we can see that like in general, in long context benchmark, it does better. That's why when number of edges increase, the model is performing almost the same as a smaller number of edges. And another analysis was about number of nodes that you can see in the graph, which is the same pattern. As you can see, the trend is downward. As we get number of nodes, problems get more and more difficult for LLMs. Another question for temporal reasoning in this case would be ordering of the fact. So as I showed, we generate random graphs and then we assign entities and relation on top of those. Now let's look at the specific graph that we have here. So in this graph, I have 4 entities, like something very small toy, just to show how fact ordering might change things, and then and some relations on top of the edges. And let's say the question is, who was R1 of E1 before E5? So you can think of multiple ordering of facts for this graph. So let's say you can start with like saying E5 was R1 of E1, and then E6, and then E7, or you can go the other way around. So basically, for any graph, you can think of different fact ordering when you want to convert that graph to text in your prompt. And now the question is, well, if you change the order of the facts, the problem would be fixed still, and whether that's going to change the LLM performance for that or not. And so in this chart, we can see that even though the problem, the graph, everything was exactly the same, and we only changed the order of the facts in the question, we can see that the performance changed a lot, given the fact ordering that we use for that. And what is the best encoding? So mostly when organizing fact in a manner that aligns with the temporal flow of the narrative, that enhances LLM performance. And that's because if you're asking the question in some specific way, it's better for the prompt to follow that narrative. But then looking at all different results that we got, there is no perfect temporal fact ordering that we can call out and like start using that. So this gets back to this linearizing that we have. So we have some data in the form of graph, and then we want to convert it to text again. So this would eliminate the inductive bias that's encoded in the graph structure. And because of that, whatever graph structure that we use might not be perfect for all applications and all graphs in the world. Now let's get back to the second work that we had in the graph reasoning part on using specific encoder for graphs. So let's say if you have a graph in input, why converting it to text? And we can instead have some specific graph encoder, like GNNs in this case, to convert that to tokens instead of directly trying to converting it to some specific text to fit as in the prompt. So yeah, this is one sort of future work for this direction. If you want to be able to use the graph properly. So here, because we have element of time as well, it's an interesting question to think about what type of encoder is the best for this specific setup. So models would be able to interact better with our temporal graph at hand. So another question here is about our temporal arithmetic solve set. So as I mentioned, we define different set of questions in the temporal arithmetic, and so yeah, we have the results here. But if I want to summarize some interesting finding from that, well, the easiest question for models were questions about time zone. And our hypothesis is that it's because there are a lot of information about that on the web, so models are able to use those information as well to be able to like convert time zone and use one and the other. And the hardest question here were duration questions. The duration question is when you want to count, let's say, number of days, years, or months, how long something lasts. So that was the most difficult question for the model to figure out. And here I have some common failures, again, on the duration question. So the most common error for this specific case was a deviation of precisely 1 day from ground truth label. So models are not that bad, but then at the end, when they want to calculate it precisely, they get a deviation of 1 day mostly. Another interesting failure mode is direction. So let's say you want to determine the number of months between 2 dates. And let's say you have this specific timestamp and another one, and you want to count the duration, which is 8 months. This is particularly a failure mode for model when they want to go back in time in questions that the order is the other way around. One example is Sam's birthday is this day, and date of today, calculate Sam's age in days. So you have to get back in time and calculate instead of going the other way around. Another failure mode is for leap year calculation. So when model wants to count between 2 dates that span multiple years, they usually have difficulty in correctly counting for leap years, which adds like an extra day or the other way around. So yeah, this was about the work on temporal reasoning, and now I'm going to show how we make that even extra hard. Yeah, this work is called Big Bench Extra Hard. So a lot of the reasoning benchmarks that we can see has a main focus of math and coding mostly. And well, those are important, but reasoning is much more general than that. So let's say there are aspects of time, logic, humor, causal structure, and so on. That wasn't necessarily focus of many benchmarks. And one important benchmark that everyone was using was a Big Bench Hard. So it's very popular because it has a lot of tasks under it, like time, space, logic, the problem we mentioned here. Big Bench has a lot of different topics under that. And then problem verification is easy for all of these tasks. So it's quite easy to work with that and evaluate the LLM that you have. And it's challenging. It was challenging for frontier models of the time. But now the problem with that is a random chance baseline would already get a high performance for this type of models. And even like for some of those models can take shortcut. And with shortcut, we are not, so if we measure models, we won't be able to understand whether the model was really good at reasoning. And so often problem descriptions are very short, and usually it requires a few steps of reasoning. So the goal in this work was to keep the pros and resolve the cons. So to keep something diverse, verifiable, easily verifiable, and being challenging for frontier models, and at the same time have more, let's say, steps of reasoning and having like larger problem descriptions, so we can really measure how good models are in reasoning. So for this, we created Big Bench Extra Hard. So the high-level idea is to take each of the tasks from Big Bench Hard and replace it with another set, which is testing a similar reasoning skill, but is challenging for today's model. So here I'm going to go more deep into the temporal ones that we have. So one thing we did in making TOT extra hard specifically for this model is to make this compositional. So let's say we have a question 1 and question 2 from the original data set. What we did was to make it compositional. The answer to Q1 is A1. And we define A2 basically be a number that is used in, sorry, A1 to be used in Q2. So it's more of like the model needs to answer the first question and take the answer, put it in the second question, and then try to answer that. So this compositional manner would make it more difficult even for the model to be able to answer such questions. There's a lot of numbers. Just want to show that the model is challenging for a lot of benchmarks. Maybe less challenging for reasoning models, but for the non-reasoning model, it's quite challenging. Here are the results for the temporal ones, like temporal sequences and time arithmetic subsets that we have. And as you can see, those are quite challenging for both models. So yeah, this is about our big bench extra hard on making temporal reasoning more difficult. Yeah, so these are the list of the 4 papers that I explained here in this talk. Yeah, thank you. So should I take? Sure.
Yeah, this is about graph printing. I wonder if you considered applying graphical structures to narrative.
Graph structure.
To narrative. Example, if I'm looking paper, we applied my graphical structure. We're looking at timeline and event comparisons and legal text.
Yeah.
Relations there that could be gratified, if you will. I wonder if you consider.
Yeah, some of the questions are closer to the setup that you explained, mostly for, let's say, timeline, but inside a graph, when you have a narrative in a graph, and then you want to answer questions. But then the arithmetic part is decoupled in the other benchmark as trying to answer questions about the arithmetic operation, but we haven't tried combining these two subsets.
Utility, and in the way that to see if the model is able to reconstruct with the graph that have been used to generate the first one. If they are able to do that.
Should I repeat the question? Okay. Yeah, so the question is about whether we tried reconstructing the graph in the input. We haven't actually. Yeah, so even in the graph domain, we haven't tried to see whether that's directly like can reconstruct the problem, the graph. But one thing that we tried that and models weren't that good was explaining a graph in text and then asking whether an edge exists or not, like just the binary question. And models were at that point at least were really bad in identifying whether an edge was there or not, which is like, and I assume in reconstructing the whole graph, they would be like even more difficult. And also, yeah, evaluating models for reconstruction would be interesting, especially for frontier models. I'm sure they're getting better and better for those type of tasks.
About causal reasoning, so it seems that the usage of the graph is very relevant for causal reasoning. Have you looked into causal reasoning, like natural language formalization of verbalization of causal graphs?
Yeah, we have a paper on having like causal graphs and trying to ask questions to see whether LLMs are causal. They can like understand all this relation. And yeah, and like in general, they were good at some specific task. But as soon as we got similar to the temporal reasoning part about like abstracted and grounded part, as soon as we were trying to make things abstract or change definition of things, so the model won't use the parametric knowledge, the models were getting worse and worse on those specific benchmarks.
Did you include these kinds of tasks in the extra hard application?
Yeah, there is a causal subset, but because we wanted to make sure tasks are pretty similar to the one that were initially used in Big Bench Hard, we didn't use that a specific subset here, but there is a causal subset here for causal understanding. Well, in the benchmark domain or in general? Yeah, I mean, it depends what the goal is. Maybe one thing that I explained here was that interacting with these models with text is not the best option. So maybe like trying to think of what kind of encoders you can use specifically for temporal questions would be interesting. So maybe it all depends on what type of structure that you have there. So yeah, that's an open question. And of course, again, in the benchmark domain, models are getting better and better, like being able to properly measure how good they are in different temporal tasks and find their failure modes are also always interesting.
And do we have some questions online? If you have.
Yeah. Hello, I have a question. Have you considered the geometric prior of the graph? For example, like the graph can be
We don't
potentially
hear you a lot.
Can you hear me now? Can you hear me?
Okay. Not so much. Maybe.
Is there a chat for this? So we can
Okay.
read that?
Is it working?
Can you write your question in the in the chat, please?
Okay.
All right. Can you try again to speak? Wait.
Can you hear me now?
And we hear you, not with the sound of the room.
Yeah, maybe we can repeat.
Yeah.
Okay. Yeah. Does the other speaker online can hear me?
I can hear you, Wei.
Okay, then I just type.
Okay, you can ask your question. Wei.
Okay. Can you hear me now?
Yeah.
Okay, thanks. I just wonder, have you considered the geometric prior of the graphs? For example, like the graph, like maybe the geometrically presented as a grid, geometrically presented as a tree. So they may have different. So maybe the model have some. And I don't know, because the model somehow is like the Euclidean presented in the Euclidean space. So if the graph is more like a flat structures, it's like a grid, then more likely perhaps the temporal reasoning would be more plausible in such kind of structures. But compared to other structures, if it's like a tree-like, if it's a compound structure, it's something like that. To have comments on that.
Yeah, so if I want to repeat the question is more about graph type metrics versus Euclidean ones in the benchmark. So yeah, what we use is mostly sort of in the Euclidean setup for different type of graph structure. Well, we evaluated pair graph structure, but the metric itself is doesn't consider that in general. So yeah, having and imagine, because there are like these different type of structure are already separated from like the results are decomposed per them, it might show similar. Yeah, but I'm not sure on what type of metric would be best, because then you have like infinite number of basically structure that you can consider there. So yeah, a good way of measuring the metric for those would be challenging, I assume. But interesting question.
Thanks.
Okay. Are there any more questions online? Okay, if not, we can thank the speaker again. Thank you very much, Parag.
Okay, now let's move to the second session of the invited talk. And let's welcome Ali Amami, and who is assistant professor of computing science at the University of Emory in the US, and where he is leading the research on large language models, reasoning and benchmarking, interpretability, and the societal impact of AI. And he received a PhD in computer science from McGill University and was previously an assistant professor at Brock University in Canada. The floor is yours.
Thank you so much. Can you hear me?
Yeah.
Great. And you can see my slide?
Yeah.
Excellent. Okay. Thank you so much. Thank you all so much for attending, and to all the organizers of this workshop. I was going to say that I'm really experiencing FOMO. I think somebody on Twitter said FOMO is foundational models, or missing out on foundational models. So I'm really feeling that way. Seeing really good tweets about all the things that you guys are involved in. I was planning on coming in person. Last minute, I'm in the States. There was an event that happened 2 weeks ago. They weren't recommending with my work visa to come, so I had to cancel. Second best thing is, though, to be there virtually with you guys. I should say that it would have been homecoming for me, because I studied in Montreal my undergrad and graduate life, so it was going to be a really cool, nostalgic experience for me. So today, I'd like to extend the very interesting discussions and conversations around LLMs in terms of this temporal dimension that we can untap. Although now I kind of want to flip the script and look more at the potential for LLMs to be more of a lens for study as opposed to the object of study, if I can say it that way. So there have been, I know everybody's aware, tons of very new and interesting ways to be studying these LLMs. And I'm sure we've seen a ton of more interesting ways in Column this year. One of them that I'm sure you might have seen recently, was subject to quite a bit of debate, was this illusion of thinking paper by Shojai et al. So they tested LLMs on Tower of Hanoi. That was fascinating to me. And so the idea was just to try to measure their reasoning in more controlled ways. As you might know, Anthropic kind of fired back, saying that these puzzles were actually unsolvable and misanalyzed. This next example I've noticed of late, and this might be just coming from my own lifelong hobby of chess. I was excited because I saw a little bit of chess in Dr. Fatemi's talk too. So now it's looking at the chess playing ability of LLMs, which is really cool. Of course, this isn't research work, although there have been interesting research papers on it in NACL, I noticed. But so on the left, you see this nifty little leaderboard that was created on this website, where we have, I believe, GPT-5 sitting relatively well above an average chess.com player. But then I look at their ELO and I don't even see that to be very good. And then well below a Class C player, let alone Magnus Carlsen. On the right, we see kind of jokes about ChatGPT making a very super ambitious move that's actually invalid. Funny enough, and this might be a case of inverse scaling, on Reddit, I see a lot of avid chess players saying that the best LLM to date on chess by far apparently is good old GPT 3.5, which I don't even know is accessible anymore. And there's some crazy theories about why that is. Our group is not innocent or free from doing weird studies with LLMs ourselves. We recently picked up quite a bit of traction. We looked at the ability or inability of LLMs to capture this really interesting cultural etiquette amongst Persians, but I think beyond just Persians, many have their own forms of it, where we call this taruf, which is this sort of game of politeness that is sometimes seen as just too much by other people than Persians. And interestingly, LLMs behave like heritage speakers like myself, who are aware of the culture, so they actually know entirely what taruf is and can even define it even better than a Persian can, but they can't play it well when deployed. And then I just added this today because I found this paper, but can large language models develop gambling addiction? So basically, just about everything we can study about LLMs, we do. And I won't say much more about that one. So why did I bring up all these works in the workshop that we're talking about with time? First, let's just talk about what these works have in common. I mean, for one, it's all about benchmarking LLM capabilities. And by the way, I always add this aside, sometimes in my own mind, and I think because sometimes we forget to appreciate that a lot of these are just these emergent capabilities of LLMs that go beyond the foundational purpose of them, which is just next token prediction, capturing patterns in text. And it's really cool that we're even in the territory of looking at emergent capabilities. But beyond that, we look at, failure modes and models. We see all the places they fail in. We try to work on improving LLMs through all the massive efforts in post-training and understanding their behavior, which is also a very big area. Now, it looks like with all of these kind of questions, the standard framing is to ask, how do LLMs work? Maybe what's wrong or what's right with them, and how do we fix them? And I think these are all, of course, very important questions. We have column around just this. But they're all sharing, in my opinion, the single assumption that it's the model itself that is the thing to be studied. And borrowing from another chess term, I think there's a missed move or a missed opportunity here. So, we say often that models are learning language patterns. I know to different extents we say this. It might be because they're capturing syntax better or word co-occurrence or the mechanics of text. But perhaps it's not all they're learning at the surface level. It could be because they're absorbing properties of the data itself. This could be the norms, associations, and framing choices that the LLMs come with that are learned, and maybe some of the values and assumptions of that corpus. Now, if you then take one more step and say that maybe it's because models are kind of statistical compressions of their corpora, and I've seen some recent formalizations of this, then you might take this final step of seeing that we could be using LLMs as instruments to study said corpora. So instead of asking, say, the common questions we do, like what biases does GPT-4 have? So basically, it's following this pipeline of going from the corpora down to this Sesame Street themed model, which you know why probably historically, down to the querier or the person who's asking about the model. I'm sort of asking that maybe we could ask something like, what assumptions and biases do the writers potentially of that text that the LLM was trained on have, right? So that's maybe one way of looking at it. Maybe it's the writers or the worldview that text came in. So we're more using the LLM as a lens to the text as opposed to sort of an object of study because of the text. Now, there was a motivating example that really drove me to think of this a little bit more deeply. And I showed this to my students last year, and the example kind of stuck, and I really liked it. And it was a little toy experiment that I did when NanoGPT became available, and it was really nice to use. So what I did was I took a single text, the Project Gutenberg edition of Walt Whitman's poems. Then what I did was I trained a very small GPT-2 model. So it's 10 million parameters, approximately 6 layers, and it was character level on the open source NanoGPT framework. Of course, mind you, the goal here is not performance. It's to see how quickly a model starts to internalize, let's say, the stylistic and semantic fingerprint of a specific author. It could be here, Walt Whitman. And it was trained, just to note, in roughly 30 minutes, actually on this laptop that I'm speaking on. And then I called this kind of GP2 version of the model that was only pre-trained on Walt Whitman's poems, Whitman Baby. I was just really curious. And I honestly just wanted to see for myself the power of language modeling. So I prompted it with just an empty string to see what its first words to the world would be. And it's as follows. Tons of observations, I guess, we can make, and we're limited for time. But I think firstly, just almost when you kind of squint at it, it does structurally kind of look like a poem that Whitman might write. Of course, there's some words being invented here because it's a character level model. And no, these aren't stars that it outputted. I had to actually censor the second word. So this baby swore the second word it ever spoke. Turns out, I think maybe that is a reflection of Whitman because Whitman's material is somewhat explicit. So it's interesting. So I took this up a notch. I now prompted it with something. And here I was actually really interested in the idea of hallucination. So, I mean, if I took an excerpt from an actual part of these books from Whitman, this one's actually really politically inclined. I will make a song for these states that no one state may any circumstances. I wanted to prompt Whitman Baby to see how it would continue it. And it continued it after this bold part with a bunch of other kind of like interesting words that some of these are kind of bizarre, but still there's some semblance of meaning here. And I think I was appreciating that just with 30 minutes of some pre-training, it was doing this. It was capturing maybe some stylistic, maybe essence of Whitman. So then I took it up a notch. So then I considered fine-tuning. So this is already with a model that's pre-trained. So GPT-2 large, we're reaching at about 1 billion parameters on Whitman's poem book. So just a little bit of, you call this domain adaptive pre-training. So it's just continued essentially language modeling. Oh, and then the game that I want to play with you is that, and it's unfortunate that I'm not there in person because I'd really want to see the audience thinking about this, and I don't know how large the room is, but maybe I'll get a sense with the help of Maxime here. I'm going to show you 2 continuations of that same prompt that I had, which was the excerpt from what Whitman actually said. And then this fine-tuned model, which I call Teenage Whitman because it's experienced a little bit more of the world, is somewhat confident, will be one of the outputs that I show you will be the fine-tuned model, Teenage Whitman, and the other one will be actual Whitman. And I want to see if you guys can discern the difference between this GPT-2 Whitman, Teenage Whitman, and actual Whitman. And I've completely shuffled the 2. So I'd like the room to sort of look at this, and then maybe I can get a sense of the total numbers in the votes. So this is the first output. The bolded part is the actual excerpt from the text. Let me know if the room is reading it, Maxime.
Yeah, we are reading, we are reading.
Okay, and then if you have a sense that people, okay, I want to give it a little bit of time, but okay, I'm gonna now go to the next one. So this one is another continuation to the same bolded text. I hope we aren't having access to internet or anything. I want to see what you guys think. Okay, so now I want to ask the room, who thinks that this is Teenage Whitman? And who
two
thinks
people.
that, and who thinks that this is Teenage Whitman?
Few hands also.
So who in the room I want to see the result, Maxime. Who which one was the majority?
It was split, evenly split.
It was split, evenly split. Okay. But the fact that I heard 2 means that there's not many people in the room. So I think there's 4 people in the room. Okay, but nice. But by the way, I've tried this experiment with a bigger audience once and I had interesting results. So let's talk observations. So what's striking to me, at least to me, let's see what happened with the results, is that a small fine-tuning pass, half an hour of training for me, was enough to capture rhythm, diction, and even some of the moral optimism, if you read through it, that I know of like one of the poems of Whitman. And yeah, it seems that the line between Whitman and not Whitman became blurry because it split the room. And actually, by the way, it turns out that this one is fake Whitman. This one is real Whitman. And I had once someone make an observation that there was actually a geographic mistake here, that Illinois, if I'm not mistaken, somewhere here it was redundant with Chicago. And by the way, I'm recently in the States, so I don't even know these things, but I think someone picked it out and said Whitman would have never made that mistake. But still, stylistically, I think we had people fooled. I had me fooled, by the way, because I did this and I produced the outputs, I put it in my computer, and then I totally forgot what was what based on my code. You know, we're all like messy coders, and I had to go back and reprint it to see which one was Whitman. So it fooled me. So the idea here, and it sort of was like a eureka for me, was that fine-tuning becomes a little bit like this controlled probe. So it lets us basically see what linguistic and conceptual patterns the corpus itself is impressing on a model, right? And if it might work for one author here, that it might capture Whitman's essence, there's no reason it couldn't work for entire decades or movements or cultures. So each of these fine-tuned models might become a miniature worldview, a lens for studying the society that produced its text. By the way, this was very basic, if I even call it fine-tuning. This is domain adaptive pre-training. As I'll show you today in one of the works that we did a little bit more of an involved fine-tuning process with SFD, supervised fine-tuning, and it did much more interesting things. But this was the sort of motivation and inspiration behind that. So basically, what fine-tuning is giving us, and I know Jose had a really good point with this, he was converging at fine-tuning, and so was Alexis and others, but it gives us a way to study text. It's a really powerful technique that we have. So you can potentially fine-tune a model on a focus collection, I mean, beyond just a single book of poems, maybe you can be fine-tuning on a set of novels or political speeches or editorials, and it might start to internalize the corpus's voice, maybe its focus, and even its constraints. And then what you can do is, as you saw with what we did with Whitman, is when you prompt these fine-tuned models, the way it answers might reflect the corpus's framing, right? So maybe the roles it tends to assign, the assumptions that it keeps repeating, the patterns essentially. And then what you can do is you can contrast different models trained on different, let's say, subcorpora or genres or authors to map different perspectives, essentially. And then I think what's really powerful is you can use controlled prompts. So you make sure that you have, let's say, the same dilemma across these fine-tuned models or the same scenario or vignette and the same rewrite task. And we can test what each corpus essentially is choosing to emphasize or omit. And then finally, most powerfully, and I think this is the punchline, is that these outputs, right, because these outputs of large language models are inspectable, after all, they're language, they become a new kind of evidence of interpretation. It's a way of reading a text deeply, but with the reach of computation. On that note, I think it's really important for us to be aware of what the traditional methods of reading a text are, or text analysis. And I mean, there could be an entire lecture on this. I just want to briefly brief this. And also, I think I have a lot of research that I need to do beyond this because I think it's an active area. So there's close reading, which is still very active, and it's quite popular in the humanities. And this, basically, you would have scholars that would trace ideology, identity, and power, let's say, through careful attention. So they're experts at this reading process. They might look at who's speaking, who's silence, how norms get encoded in text, and they'll look at it through certain frameworks. Like you might look at it through the framework of feminism or post-colonialism or Marxism, right? So it's very powerful, but they're very slow. It can only apply to a few novels, you might imagine, and a handful of speeches. And obviously it can't scale to decades or millions of documents. So then to scale up, you might have researchers turn to hand-coded content analysis. So this would be maybe teams of coders. So maybe they're not as expert as scholars, but then they're applying structured categories that are provided to them called code books. For example, they might be trained to identify whether or not a segment of text has positive mention of democracy or not. So, and then they would use intercoder reliability. And this becomes transparent, it's rigorous, but of course also painstaking. You might spend months annotating just a few thousand documents and not entire corpora. So then we move beyond this. You might have dictionary-based methods. You've probably seen some of these before. So you have linguistic inquiries and word counts, for example, LIWC, moral foundations, NRC. Basically what these are doing, they're counting words across different categories. I mean, one of the problems of this is that meanings shift, called semantic drift. Words like, let's say, virtue or woke or queer, they don't mean in the 1950s what they mean now, right? So these methods are, of course, interpretable, but they're brittle. They're treating language as static. And then I'm going to start painting in green methods that are getting closer to this kind of fine-tuning approach. And so, for example, culturomics that was proposed by Jean-Baptiste Michel in around 2011 actually looks at word frequency across time. But of course, it's limited to words. It might miss more pragmatic matters like irony or framing or who targets whom, but it'll produce some interesting results. So you might like track slavery like this as one word across the decades. But then notice, by the way, you don't really get the context around this word, right? So if I say something like not happy or happy, then it'll be treated as the same thing. And that's why, of course, we're all aware of the evolution beyond that, beyond single words. We might look at embeddings. Diachronic here just means across time. So there are many recent papers that try to do this. They look at how embeddings will be associated closely between two pairs over time. So there was a paper recently by Garg that did that. Now, of course, there's limitations to these as well. So they're brilliant in terms of how words evolve. So for example, you might get women drifting closer to leader over time in terms of the cosine similarity. But of course, these still operate at the level of isolated words. So perhaps embeddings capture some context, but they might not be able to model pragmatics or stance or narrative context. So of course, in short, all of these methods that I talked about have this shared problem, and it's really this balance between scale and subtlety. So you can have these huge data sets with simple signals like word counts or incredibly complex analysis on few texts that we do with like close reading. And then second, we have this problem of pragmatics. And I'm not saying pragmatics, by the way, is solved by LLMs, but I mean, really, foundationally, the social layer of language was missing from those previous methods. They might miss negation, tone, implicature. For example, if I say, that's great, exclamation mark, or that's great, dot, 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 they definitely miss that. And I think another very key limitation here is that I call them observational. It may not be the most apt word, but basically they're just describing what's there, how often a word's repeating, how meanings drift, but they're not letting us interrogate them dynamically. Like after they're trained, you can't ask them, what would a 1970s text say if asked X? Almost counterfactually. Now, of course, there must be niftier ways that we would prompt them, maybe to bypass guardrails, but you know what I mean? It's like it doesn't give us the freedom during measurement to be able to actually change our framework. Now, and I take this from Professor Jose Colados from his earlier talk. I was listening. He had a really cool title where he's like, why LLMs might not always be the best solution. So now I'm basically doing the reverse of that. Why LLMs may sometimes therefore be the best solution here, specifically with fine tuning, sort of lists some points here. They're basically the opposite of those shortcomings. For one, they're adaptive. So we might be able to take a single corpus like you saw. This might be a body of literature, a set of speeches, books over decades, and then you might be able to fine tune a model that reflects just that linguistic world, which becomes, as I said, that kind of cultural probe. Second, they're more deeply context aware. For example, beyond, let's say, n-grams or embeddings. So they might be capturing syntax and some aspects of pragmatics and tone. Also, I think very powerfully and also very amusingly, they're interactive. So you can query the model with natural questions. As I said, maybe you want to be careful here as well. You might not want to query the model trained on a book by saying, how are women in leadership portrayed here? But you have the freedom to now investigate how you want to ask or probe, rather than just compute these statistics or these static statistics. Think also it's really cool because you could be comparative. You can compare parallel fine tuning. So over the decades, you might be able to look at the direction and magnitude of societal change, kind of like what we saw with those slavery examples, but more deeply. And then finally, I think this is subtle, but I think it's also very powerful. It allows us to merge qualitative richness. You might imagine this is where we might bring in a scholar that would determine how to prompt a model using style, voice, narrative, or certain frameworks, with that kind of quantitative consistency, which came with scale and repeatable probes and reproducibility that we would get in those later approaches. So all of this basically motivated my lead author, who will actually be doing a much more deep dive in a few hours on this paper, to explore the potential of using LLMs as these probes. And we called it a time capsule in our paper here because we wanted to look at, relevant to our curiosities in this workshop, how LLMs could be used in the temporal dimension of looking at how change occurs over time. And we were really inspired by a single problem here, and it's one that I'm imagining most of us can appreciate, and that's that books don't just tell stories, but they sometimes are these reflections of biases and worldviews of their time, right? So which LLMs ideally are not, maybe ideally or sometimes not ideally absorbing during their training. And just one example of this, for example, is a book, The Turner Diaries, I believe published in 1978, which it's a book, it's benign in that sense, but then people who read the book might turn to extreme violence inspired by some of the contents. So of course, I think that's both cautionary and enlightening for the community, because it means that we should be careful not to pre-train just about on everything just for this pursuit of size, but enlightening sort of in light of what I'm saying of flipping the script. So it allows us to now look and analyze books using the LLMs that are trained on them. So what we did, in short, was there was like 3 steps. Number one, we created this large organized data set of popular books by decade. So these were bestsellers, essentially. And these books were, for example, in the 50s, we had a bunch of books with all of their titles and contents, and we did this across 7 decades. And then I'm hoping our lead author, Sangmitra, goes into this a little bit, and I know she will, but we fine-tuned these large language models on each decade of books. There was a rigorous process of actually verifying and validating that they were indeed capturing what I will for now call at the essence of those times, but we did something called entity evaluation or named entity recognition to see if they're actually capturing those entities and stylistic patterns and cues. This was also not trivial, but we found fine-tuning with a specific regime within SFT worked the best to do this, and there was a lot about that as well. But once we had those LLMs down pat, then we prompted them based on roles that we were interested in, that we also derived from sociological studies that mentioned that there were biases and societal changes around these roles, as well as identities corresponding to these roles. So an example is we'd create a prompt like this. It was a sentence completion prompt. I normally go to work, and while I am gone, the house is cleaned and maintained by. Now, when you look at different identities here from different dimensions, like you might think gender or sexual orientation or race, how often or how represented a group is in the total number of times that they're being mentioned when they're reprompted perhaps can be a proxy of the bias the LLM has, right? So if you might imagine a certain gender shows up more from an LLM, but from being reprompted on this, it could be a reflection of the bias of that LLM. So just one result, we had a lot, and I guess I chose this one because I think it's one that we might relate to, is in terms of leadership roles across the ages. For example, the prompt, the CEO of the company I'm interviewing for is, and you can see now a trajectory that's occurring where the most represented, so on the x-axis are the different decades, with each of them corresponding to the fine-tuned LLM, and the y-axis is the percentage of responses that had that identity represented. So you can see that there's this big discrepancy between men and women, but then it's actually getting smaller and smaller across the ages with some uptick that happens in the 1990s. And we sort of triangulated this as well with societal events and studies from historians at the time. And another interesting finding was to see how the variability in the different dimensions across time. And we found gender and sexual orientation were the ones that actually had the deepest slopes in terms of the changes they were experiencing across time versus religion and race. You might be wondering, and I think this needs to be deeper studied, but we were also wondering how much of the bias is actually coming from the architecture as a prior versus from the books. So we tried to disentangle this by looking at the different models and their biases just as the function of models, and we saw that actually they really behave the same. So whether it was Gemini, Llama, or Mixtral, for example, let's see, on homemaker, that prompts that involved the homemaker, there was the same sort of bias that existed with women being more represented. For example, with nurse as well. I mean, there were some exceptions, but in general, these, as you can see, these fingerprints were rather the same. I mean, of course, this is all fixed on the same decade. Finally, I think this table is profound, and I think Saimitra, our lead author, will talk a little bit about this, but going back to some of those traditional approaches, one of the traditional approaches, as I mentioned, was the last one with like word embedding associations. And one way that was done very recently with Nikhil Garg, was that they looked at the word embedding association or the similarity between two words as a study of looking at bias over time. So we actually applied their method using GLOVE on our decades of data set. So this is for 1950s, and we saw some of the caveats and some of the limitations really empirically. For example, there is this brittleness of context window, right? Because you're training these embeddings using a context window, and depending on what that context window was, we would get discrepancies. For example, on nurse, when you're looking at how closely women was associated with nurse versus men, that would change depending on the context window, and sometimes would even flip. Another thing here, and this is not a glitch, but we would see NA. And why is this? So we said NA here is because if the term CEO wasn't actually in the corpora in the 1950s, well, then it wouldn't exist and you couldn't actually measure that. But I think what's powerful, but maybe something that we need to think about, is that with our method here with fine tuning, because these models are deeply contextual, even if they're, and maybe also because they're pre-trained, even if they're asked about a word that wasn't technically present in the time, they might be able to associate that anyways with the position of leadership and still be able to answer for it. So it did free us from some of those limitations. So I think once you realize that these models can internalize the worldview of any corpus, I think the sky's the limit. You can think of different text sources to look at. I mean, I list a few here: news media, legal documents, medical literature, social media, education materials. I think there's a ton of possibilities here. I'm personally invested also because of the great resources at Emory in terms of medicine, looking at some of these trends in medical literature. For example, you might imagine what might be considered a disorder over time, or what counts as normal, right? And so, or what language surrounds stigma or treatment. By the way, I know we're talking about time in this workshop, but you can even fix time and vary other variables as well. So you can look at cross-cultural comparison. So imagine just in the 50s to look at how different languages and cultures talked about maybe certain global events like World War II, maybe how documents or news in French societies versus the British societies would consider or talk about the same global event. And then you could also look at convergence and divergence over time. Our culture is becoming more similar or different over time. So there are a ton of questions we couldn't really answer, and that maybe we could be answering a little bit better now. I mean, one aspect here is tempo, really. And by the way, this is Pandora's box here, so maybe we don't want to answer some of these, but this is how quickly social norms are shifting after major events. For example, does the moral language of fiction catch up with the realities of policy, which I think is really profound. And then we can also ask, and we ask this essentially in our study, but what biases persist and what evolve, right? So which ones remain remarkably stable? And we saw some of them that remain remarkably stable across, let's say, religions and races. And I think one thing that's powerful, and maybe too powerful, is that maybe you can do forecasting as well. So you can use acceleration patterns and language to anticipate where norms or values might be actually heading. Now, there's this long list of footnotes and challenges and limitations, and I'd love to hear from you to see if there's any of these are just immovable bottlenecks and you can't actually overcome them. But these are some that we experience. There's number one, validation. So how do we know we're measuring culture and not just modeling artifacts, right? So when we see a pattern, we have to ask, does it actually align with grounded truth of what historians or sociologists actually know? And then there's this issue of attribution, which is somewhat related, but that's even if we're seeing a pattern clearly, where is it coming from? And I think this goes beyond just showing that the results hold on different models like we did. Oops. And then there's selection bias, of course. I think this is huge. It's text is, everywhere, but who publishes it, what genres dominate, of course, that's one of those, things that we have to consider. There's reflexivity too, which is big because I think I talk causally as if it's just text, which is a reflection of society, but books influence society, and so it's really hard to disentangle that way. We have this elite discourse problem. Most of the voices are authors are authors and institutions or publishers, right? So a lot of everyday language doesn't make the cut into our canon. And then finally, I think this is emphasized too, and I think this goes into this workshop and generally for research on LLMs. As much as I said we need to flip the script sometimes, developing better and more competent models is obviously going to help our use of them as lenses as well. So we're only as good as our model competence is. So we need to be developing models that are more temporarily endowed, right? So I think as we incorporate these advantages, we'll be able to actually do things much more better and rigorously. Very quickly, I just want to mention that I think none of this work can be done without ethical considerations that I've listed some here. For example, who's deciding what biases to measure? Saimitra probably will talk about this too, but even deciding categories for our study was super tough and tons of debates within our group about how we're going to do this. In the end, we converged that essentially what the models ended up outputting, right? So like, for example, for race, we didn't choose beyond these three because the models mostly just outputted races on these three. But I don't want to recuse myself because of that. I think there's a ton of other potentially dangerous applications of this, for example, in surveillance that we need to be wary of. And my personal next actionable is to read a recent book that was released by a historian that the blurb was very meaningful, and this is why I want to read it. But it says the book pursues a catalog of disasters created by data science experts who voyage into humanistic study, which is potentially here what I'm laying out. But I think it does end on a positive note where it says It ends with a call for a cyborg historian, a hybrid researcher who brings the best of AI to the contemplative framework of a traditional historian. And it means a lot of this collaboration. So I want to kind of end on a conclusion and possible visions for the field. So if there's any conclusion I've made from listening to the workshops and the talks in the keynotes and the talks in this workshop is that time itself now can be studied computationally. And so the goal here isn't to just build smarter or more temporally endowed systems, but to trace maybe language, bias, and belief across eras using them. And so this, of course, as I said, needs collaboration between different disciplines. And as Dr. Fatemi mentioned, this involves a lot of interesting benchmarks that we do require for longitudinal and cross-temporal analysis. And I think this will lead to a future where maybe LLMs can be that, I guess, that historical cyborg that would help us understand how we change over time and understand how we can improve as well as a society. I recently read this very interesting line from a book that I'm still reading. It's called Machines Like Me. It's a parallel world in which AI went much further than we are today in the 1980s. And I think it's very profound, and it does summarize a lot of what we discussed in the workshop. It was no longer proper to assume that anything at all had ever happened in the past. There were only historical documents to consider and changing scholarly approaches to them, and our own shifting relationship to those approaches, all of which were determined by ideological context, by relations to power and wealth to race, class, gender, and sexual orientation. Very kind of run-on statement, but I think very powerful because it was run on to say that when we're grounding everything on things that actually happened, there's so many steps in this pipeline, starting from our own tools, which are subject to our own opinions of those tools, and our own opinions are subject to our own ideologies, meaning that there's so much there in terms of subjectiveness that we actually have to stop and think ourselves, did the event actually happen or not, was I think what he was selling. And I think this is just a precursor to say that as much as I think LLMs can be powerful tools, we need to think about the caveats as well. Thank you guys so much.
Thanks, Ali, for the great talk.
Thank you.
And questions from the audience? Question in the room?
We have question. I will, if you want, you can come here to say it. Yes. We have questions. Yeah.
Yes.
Thanks for the interesting talk. So I was wondering if this work can be generalized or maybe apply in individual level. For example, like fine-tuning a model on a person, all of the person post on Instagram. So I was wondering if such a work has been done or any safety or privacy concern regarding that. Thanks.
Excellent question. Thank you so much. I am starting to delve deeper into the work on personas. I'm sure, I shouldn't say I don't know if they are. I'm sure there are works that consider these different fine-tuning regimes for personalizing LLMs beyond just prompting. And I think it's profound. I think it's powerful. I've actually accidentally tried it myself. I gave at one point, I think a year ago, Claude my entire, and it cost me a lot because it was in the playground and I didn't know it was by token. I think it cost me $200 accidentally, but I pasted my entire WhatsApp conversation or a series of conversations with my wife since I met her 5 years ago. And it worked. And then it was able to simulate us actually very eerily well with interpolations about things about our personal life, which were shocking, like my brother-in-law's age, which was never brought up. So I think it's very, very much possible, and I think it's very, very dangerous. But of course, I think it's probably going to be done. It's just about how we're going to have guardrails and ways of making sure that that kind of thing is not in the wrong hands. But yeah, I personally am convinced that it can do a really good job. I was basically by showing myself with Whitman with just 30 minutes that it can split the room on who decides which one's Whitman or not.
Other questions? So I would have one question about this methodology that you propose. I think it seems very general of saying let's fine tune on different subsets of the data so that we can see what's happening. So you mentioned several limitations, and maybe one of them that you you might have thought about. The first one, like kind of validation, like how do you know, or do you get an idea of how to deal with the fact that it's an interplay between the pre-training and the fine-tuning? It's not clear exactly what you get at the end. Maybe just because of the differential nature of comparing in one side versus another. I don't know what your thoughts.
Excellent question. And I'm not just plugging my student here, but she, who will talk in 2 hours, did such an excellent job of, I think, addressing a lot of these limitations question, Maxime. We were also interested in seeing what the pre-training corpora contribute in terms of tendencies or trends. And we were, to some extent, able to decouple fine-tuning from pre-training based on some control studies we did there too. I still think it's not completely possible to decouple perfectly. But so what you do is basically you show if these patterns at all hold just by these models out of the box, and then show that they only hold when you're doing fine-tuning. But still, this fine-tuning requires the pre-training because it requires some sort of foundational understanding of language. Otherwise, you couldn't make the claim that CEO can now be captured. So I think that's why validation is so important, because you want to validate this approach. And maybe this is a future work that needs to be done. How do we do a work that's standalone about validating this? So this is where you will bring historians, sociologists, and maybe you would pre-register your study and see how many of the trends in society it's actually able to spot on predict. And then based on that, you might be able to make a claim that fine-tuning, by the way, with a caveat saying the specific type of fine-tuning that might be working, because we tried many different ones. In fact, within SFT, we tried, first of all, making it so it was like a question answering task. And then we made it like continued, kind of finish the sentence. And then we had even some system prompts. In the end, one of the methods worked really well. So what works really well and why? This is like a huge area I think we need to look into.
Yeah, thank you very much for your answer. I think I completely agree. Seems like it's a new methodology, so it needs to be a lot of work needs to be done before being validated, but very promising.
Yeah.
Do we have more questions from the room? I think no, maybe online, some questions.
Oh, I see it. Yeah. Yes. Maybe
please go ahead.
Muted.
Please
Maybe
go ahead,
Katia muted.
Katia. Oh, we cannot hear you, Katia.
I think Katia might be muted. Was there any other questions as maybe we see if we can fix Katia's audio?
Okay, there's another question.
Yes, Sangmitra.
Hi, Ali. This was really nice to see you. It's a different way to look at our work together. I like the talk a lot. But my question more so was just, I think you mentioned if you can go back to the extensions of this work or like the applications to other.
Here?
Yeah, here. I think I was really interested because we talked about most of these except for the medical literature one. And I think you did mention that Emory has a lot of good resources for these kind of applications, but I was just interested to hear a little bit more about that from you. So we talked about all of them, but I think the medical literature one was missing. So I was interested to see what you kind of think about that.
Yeah. So I think this is something I'm going to propose to them because currently what I'm working on with them is basically radiology residents. So these are students that are residents that are working with models, and their behavior over time is changing in terms of their perceptions of models, and their reliance on models is changing. So that's a completely different area of temporal research, which then I think, as I was considering and reflecting on questions in this talk today, made me think beyond just the perception of a doctor here, in terms of doctors as a group, if I can call it that, over time, and their perceptions, and maybe also not just doctors, but society, and their perceptions on different disorders or different conditions. And again, based on the great question that was asked earlier, can we be fine-tuning, in this case, not one individual, but sets of individuals to be able to actually see trends in how people consider certain diagnoses?
Yeah, that is
treatment
really
paradigms.
interesting. I think it's also just as time is going on, so many new, not new, so many kind of things that we talk about in passing are being paid importance to, which is really important. I know a lot of the times we talk to, sometimes when you talk to older generations, they have different perceptions on these medical kind of, so it would be really interesting to hear. So that's just what I wanted to know.
Yeah. Very, very briefly, I should mention in the group is Sangmitra is doing a follow-up work on, I guess, our area as a whole, but this would be looking at how we can maybe potentially fine-tune as well as a tool, but this is not yet requiring fine-tuning, but looking at how different ages of members in the same community would have completely different perception on cultural common sense. So what one considers is appropriate to bring to another as a gift within India might be not just depending on the subregion, but within the same subregion, a different person from a different era could completely answer that question differently. And I think that's powerful because when you say common sense, we often think that means that it's a shared or implicit knowledge, but it isn't. So now imagine either creating a benchmark out of this, but in addition to that, looking at fine-tuning as a way of measuring these kind of differences.
Yeah, I'm so excited for that. We'll see how that goes.
Yeah. Katya, can we try to see if Katya's audio can try again? I'm very curious about Professor Katya's question.
I can read Katya's question. So
okay.
Katya,
I can't
write
read it.
down. So
I can't
have
read
you
it.
thought? Okay, I can repeat.
Okay.
So have you thought about validating via statistics, such as labor statistics or biological models?
What's the last word on what kind of models?
Sociological models.
On models. Yeah, we've thought about it to the extent of basically, Katya, we got these results. These are these interesting trajectories, these tendencies of, let's say, increasing or decreasing representations of different groups over time. And then I think what we did very honestly, and I really appreciated it from Sangmitra, is once we got these results, then we sort of looked to see if there's corroboration in research and literature about these. And I think that's one step, but I think actually looking to see if there are studies with statistics that we can somehow correlate to this, we didn't. And this is because looking now in retrospect, we didn't start with those studies to see if we can find anything comparable. For example, we had something on the representation of race as an association of mathematicians. And we found something fascinating, which was that Black mathematicians had a higher representation in the 50s and started decreasing. And then when we looked, we actually saw that this was a known phenomenon among sociologists, that there actually was a higher representation, and there was more representation of them in that field before the 60s or 70s. But is there a way of statistically having some study that statistically provides those numbers to us so that we can correlate? We then didn't know, there was nothing like that. But now I think what we should do is start with those numbers and then come up with these trajectories so that we actually have something much more grounded versus just what maybe one historian said. So I think that's a really good point.
Thanks a lot.
Great.
Yeah. Let's move to the next speaker. Welcome to Vivek Gujpal, and he's assistant professor of computer science at Arizona State University. He's leading a research lab and focusing on evidence-based AI systems that coupled large language model with symbolic tools. Yeah, the floor is yours.
Am my screen visible? And did you see the slides?
Yeah.
Okay, cool. So thanks Lee for the introduction. Hi, welcome everyone. So I work on more LLM sites in natural language processing. So today I will talk about temporal reasoning over evolving semi-structured data. So what is semi-structured data, what is evolving, and how temporal reasoning come in picture? Let's look at that. My lab is called Complex Data Reasoning and Analysis Lab. So when I talk about semi-structured data, what I'm talking about is a complex data, which is like a structured format. For example, you can have a table, which can have images, you can have a chart, which has some narrative around it, you can have a map, you can have table in multiple languages, you can have a graph, or you can have a complex chart which is distributed over points, or you can even have a flow diagram kind of thing. So this all I call as complex data, or in particular semi-structured data is the table data where the text is there in free form as well as ordinal and other form of representation. So today I will talk a bit about temporal QA in entity-centric table and beyond. So first, I will try to introduce this data set which we created in 2023, which is TempTap QA, which is temporal QA over entity-centric table. So this is the Wikipedia info box of Joe Biden, and it has a lot of temporal information in it. So you can see in the structured data itself, there is 46 president, there is vice president, and then it's preceded by. So a lot of temporal information are there, and they are connected to each other implicitly or explicitly. One and many of the queries which can have, like what was the Joe Biden political affiliation in 1953, can be answered from this by either directly looking, so it can be explicit, which is directly looking, easy reasoning plus lexical matching, or it can be even something complex, right? What position did he hold in a particular year, or how many positions does he hold in particular year? So you can see, like within this table itself, there is a lot of interconnections between the informations, how they are arranged, and we can do a lot of interesting queries around this, which are very natural if somebody want to ask. For example, how long does he chaired the Senate Foreign Relation Committee? Now, this will even require us to count multiple things and then see the period around it and this. And sometimes the time is not explicitly mentioned, but implicitly mentioned around it. So first, why we created this new data set? Because we find most of the tabular data set, they were not temporal focused as this workshop is around. So they were not focusing on the time aspect, they were focusing on general QA, and time was some mini part of that data set. Secondly, we don't find any entity-centric question answering data sets which are there. So we don't find any data set where there's a table, like entity table like this, which has semi-structured data. So you can see the representation of medals are in different format. It's a table within a table. There is headers, subheaders. So there were no entity-centric question answering data sets even on tables. And secondly, whatever was there were human-created synthetic data set, not interesting temporal data set. Now we look at non-temporal data set. They were data set which was time focused. They were on paragraph, but they were mostly about explicitly asking the question, like what is this thing at this? So they were just easy retrieval kind of retrieval or extraction kind of data set without much reasoning involved, and they were very limited in the temporal context they contain. So it was not very challenging enough for reasoning transfer things from this to table, and we will see in the future slide how we do it. And then there was knowledge graph, which is very clean, very clean temporal context, like a object relation object or entity relation entity, and the relation already have time in it. Reasoning on such time can be even done like by simple graph algorithm. So much not aspect of challenge was there in that. So we end up creating this TempTap QA dataset, which has multiple categories. So it has major portion of sports, but we also have other categories which include other aspects which all are taken from Wikipedia. And then in the fine grain, we have even much more categories. So each color of this represents one of the category which was there in the dataset. Now let's look at how LLM do on this. So first of all, we also divide the data set into two parts, which is head categories and tail categories. So let's say I'm talking about badminton. I know there is some famous badminton player which are frequently visited. So these we can get from Wikipedia frequency count, how they are visited and how popular a page is. And those we count as head categories, which are frequent or popular domain, and tail categories, which are rare or less domain in the same field. So for example, a famous badminton player versus a non-famous or a retired badminton player, which is not that famous. What we first observe is like even for GPT-4, the model performance was much below the human performance. Secondly, we also find that between head and tail, the gap is even more significant, whereas the human actually do equally well on head and tail category. So human reason, despite what the data is, they do equally well on both the data set, head category as well as tail category, whereas a GPT model do better on the head domain versus the tail domain. We also see if the representation of the table is a problem and try to see if we can convert that table into a knowledge graph. So basically we just flatten it and use the key as relation. The the main table entity or title has the entity, and then the value as another entity, and flatten it out and see if that helps. But that doesn't help that much also. In fact, it was very poor performance. So this shows this data set is challenging and uh, not easy to solve. So first we thought of maybe the few shot COT or the prompting is not enough. Maybe we can come with some better approach for prompting and all. So we discussed this approach of clear, where we thought about this task, what actually is needed about this task to solve, and we instruct the LLM to do it. For example, we say, okay, first you have to comprehend information about the thing which you are looking for. In this case, it applied domain knowledge to understand how to approach and solve the problem. Then we ask it, okay, all the table has a lot of complex structures and the information is distributed at multiple places. Extract all the rows and columns which are relevant for you to answer this question. Then we say sometimes the question require multiple steps. So let's break down the question into sub questions such that it solve the thing. Second, the next step, we ask it to each step by step solve the question, because sometimes these sub questions are interdependent on each other. So solve in the order and give step by step reasoning of that. And finally, do a calculation over all the answers which you have got and get the final answer. This is, for example, in this, we can see for how many MLB wins did AI can have before turning 20. Now, this is a very challenging question because he didn't debuted before he was 20, so he don't have any win. Now, this is a common sense question. So you give it to any LLM directly, it was not able to do it well. But with this clear approach where we have comprehend, locate, examine, and sub question division, and then answering those sub questions, it was able to reason well that the final answer will be 0 because he has not debit before the 20th century, which was not able to do earlier with few shot COT model kind of thing. So we see if this has also any effect on the performance as well as robustness. So we find, first of all, like the performance is better with respect to other baselines like zero shot, binder, data. So the clear was outperforming all of them. Secondly, we found, let's say, is it robust also? What happens if I give partial input, which is basically I don't give the information about the table and ask it to reason on the information I give answer, we find that the accuracy drop, which is good because if we don't provide the context, we don't want the model to answer and hallucinate on things. So the accuracy decreases, which is good. Second, we look what happens if I change the name of the table. Instead of McLean, I can put any other random player name, but rest of the content remains same. So it's like a counterfactual world where the the scores and all are shifted to another player or another entity and can still answer equally well. So you see all other model actually decrease performance, but the clear strategy was able to do well because it has step-by-step approach of solving the problem. Now, again, a question comes, this is just prompting and we were still able to not reach the performance which we wanted, which is human level, which is 87, 88%. So we thought of, is there any other way we can do better? So we thought of like, is there a fine tuning or we can do LLM fine tuning on temporal data to do well? Now, the problem we have with this is we don't find any good fine tuning large scale temporal data. So this was 2023. So we found finally a small and easy, large, diverse benchmark of temporal data, which consider all kind of temporal data. This was STRAM data, which was, I think, submitted to ICLR. We found that data and it was publicly available with very well annotation done. So we use that. Now, one good part of the STAMP data set is, first of all, it's not on tables. So it's on unstructured text. Secondly, it contains very simple questions, which are all multi-choice questions. Secondly, it has all kind. Thirdly, it has all kind of questions. So it has relation question, temporal analyze, storytelling question, typical duration question, ordering question. That all the diversity which is needed. Lastly, it also have the text sources which were very valid, very varied. So we are able to use the data. First of all, we convert this data into a question answering format rather than an MCQ format. And then, so this is an example of the data set, how the question answering was there, which was MCQ, which also make the data sets easier for to solve. So we just remove the MCQ and make it open-ended generative data set, like where you are given the question, you have to answer it. And then we took the gold answer as positive and the other options as negative and fine-tune on that. And this fine-tune actually led us to better improvement in performance. So we see if you fine-tune on this auxiliary data, by the way, this data set is cross-training. We are not using temporal data, table data. We are using temporal data in text only, not on tables, and then fine-tuning on that. Furthermore, we find that if you just use 100 examples of this data, because it's so much diverse, it's able to do much well on the thing. In fact, it helps us improving all other baseline also if you fine tune, but with clear, we were able to achieve much more better performance and do better. However, if you still see the human is a very large gap, it's 87% versus the fine tuning is still 82. If you fine tune all the whole train set, you still get 82%. So even fine tuning the LLM on the whole set is not enough for doing. So this is, I think, we fine tune the GPT 3.5 model for doing this, but that was not enough to even do this. So this led to a question like overall improve, but still far away from human, and we need to have much more advances in reasoning over temporal things. So is there any other better or fundamentally different way we can solve this problem? So given a table and a temporal question, can we answer it in a much better way? So then we thought of what is missing in this aspect. So is this the best or can we do better? What is missing out? So the missing out is we are not having good accuracy of small LLMs. We need to fine tune and get better numbers. Secondly, we also find that there is an improvement of robustness with clear, but it's not robust on small LLMs and everywhere. So the robustness is still an issue with counterfactual data. If you have partial input, like if you remove the table, then the model should not able to answer if you ask it. And then also the model answer vary across domain, like head and tail versus small and large table. Even we find that the models do better on small tables versus large tables. So what should we do? So we need some approach which is data and length agnostic. So somehow the model should only reason without looking at the data, because if the LLM look at the data, it try to invoke a semantic bias and fire information to solve the thing. So instead of doing this, what we thought of, why don't we convert the table into a table schema? So for this table, this can be a possible table schema, which we can give it to LLM and ask it to convert. So each table then will convert it in this possible schema, and then we can convert the natural language question into SQL given this schema, and then try to see this thing. So this actually works much better, and we actually create a much stronger benchmark to test this approach. We create counterfactual tables. So earlier we were just either removing the table, or we were having head and tail table, or we were just swapping the name. But this time we actually made perturbation to the table, like we add new information, we delete information, we insert information, we rename the tables. We do a lot of perturbations and create a more challenging benchmark. We also create much more questions by using the TAM-TAP QA human questions. We templated them and then generate much more variations of the question. In fact, we generated much more initialization of the question itself. So for example, we can have a question for Michael Phelps. We can also have a question for Alice Russell. And even for Michael Phelps, we can talk about other tournament, like for example, other Olympic games or other game, and then ask for another medal. So we have a lot of variations we can do in the template and create bunch of lot of questions. Furthermore, we also divide the question into easy, medium, and hard, where easy is like single row extraction, medium is single row complex numerical operation, something is needed, it's like abstractive, and hard is like when there's multi-hop across rows and complex numerical. So first we see what's happening on this data set on the temporal thing. On this, we found with direct chain of thought prompting, we found that the model doesn't do really well. It starts failing at on data set, and the performance was even poorer than the TAM-TAP QA original data set, which was expected. Then we thought, what about if we do our approach where we convert table to schema? For example, this table, we can have this 5 schema, which is converted by LLM. By the way, we just need to convert one table into a schema, and then we can initialize all the tables in the schema. So this is like all the data of all the badminton or all the player will go in the same schema. And then we see if we can use this schema, along with the query and convert into SQL by LLM. So this is converted by LLM, and we got something like a SQL like this. Now this SQL is not easy. This is for a I think, a medium or a hard question. So you can see there's a lot of operation involved in this. So still it's a hard challenge for LLM, but LLMs are much better at generating symbolic code versus doing a direct reasoning. And it's also not interfere with their semantic thing. So this is data agnostic, because when we are answering the question, we never give it the full data. We only give it the schema. So it doesn't matter if you have a large table, small table, if you have a counterfactual table, if you have a original table. The only thing matter is the complexity of this and how much it's able to convert to the SQL and how good your schema is. So there is a lot of variation in the schema. You can have 3NF, 1NF, 2NF. So how good LM is able to convert your schema. So we actually find that this was very useful. So we compare with a lot of baselines. So we compare with a static baseline. We compare an adaptive baseline, which choose between prompts. We have a clear approach, which was outperforming last time on this counterfactual control data set. We have chain of thoughts, we have plan and solve, program of thought, faithful COT, and we see that we were able to outperform all other baselines on both the original and counterfactual data. The most important thing is original we were able to do slightly better, but we were able to do much better on the counterfactual data, where all the other models was actually not doing well because they were using their semantic clues to answer the question. So it was not actually reasoning, but it was able to use its parametric knowledge to answer the thing. So this basically shows that the gap between the original and the counterfactual data diminishes as we use the symbolic SQL-based reasoning approach. Secondly, we see what is the effect on the small and the large table. So the small table, the accuracy was already good. We also get good with our approach. And then we check on the last table. And then we find on the last table also, since we only use the schema, the last table also the model performance was pretty good. So the gap between the last table and the small and the last table diminishes as we use symbolic SQL-based reasoning. Lastly, we see what happens if the question complexity increases. So we found that all other models has large drop in performance as the question complexity decreases. In fact, for hard questions, they were around 55 to 60, 65, but they were not crossing that. Whereas our drop was much more substantially lesser. So easy, we were doing even better. But you can see on the, especially on the hard question and the medium question, our performance is much better. So COT is improved, but like we were able to still outperform COT and other baselines on this aspect. So we also find this symbolic SQL-based thing actually boosts accuracy at even difficulty levels and narrowing the gap between the easy, medium, hard. But again, like you can see that for the easy and the medium and the hard, and even for small lab, there is still a gap which is there. So can we even do something better? So in that case, we thought of, can we now use training, but in a weak supervision way? Because we don't have the ground truth SQL, correct? So we have only the question, the answer has the ground truth and the table. So can we do something better in a weak supervision way to do better? So how we do it is basically we take the reinforcement learning approach where we give reward. If the answer is fully correct, we give it a huge reward. If it's partially correct, we give some positive reward. If it error, then if it's not executing, we highly penalize it. If it's executing but giving a wrong answer, we also penalize it, but not that much. At least the SQL is executed. And then what we find is like the percentage of, if we train on such kind of reward, we use GRPO for that. We found that the model performance. So this is actually done by my former student Athar with my advisor Vivek, and he found that the model performance actually improve. And furthermore, the number of syntax errors which the model was making, so you can see, is decreased a lot. And especially this is true for the large model, like for the 7B SQL code and encode Gemma, with RL, we were able to decrease the number of syntactic error a lot, and also get a huge jump in performance from 31.5 to 50% kind of. So we were able to have the small model do much better with this approach. So we were obviously still not able to beat DeepSeek R1 or GPT-4o, but we are able to get to a very good performance with our approach, which is there. And at the same time, able to decrease all the syntax and the semantic errors which were there. Now, this is about when we are thinking of a single table and a question which we have to answer. But what about there is a sequence of information which is evolving over time? This is a table about Salt Lake City where I did my PhD, and this is the information in like 2010 versus 2020. Now you can see there is some information like this is a country in United States, the state is Utah, the name is there, the elevation is same, but some information changed. For example, the population changed, the mayor changed, the the percentage of water change, the estimated rank change, and a lot of things change in that city. So one can also ask interesting question like, for example, what is the water area of Salt Lake City, or how much is there in a particular year, or how much is the water area decrease, or how much is the population rank increase. So these are like temporally shifted questions which you want to ask across a series of things. So how much is the this is very true in sports when we want to see how much a ranking of a particular player has increased. So in fact, the first question, the area of the Salt Lake City, what is decreasing, this can be evident from this. As you can see, the area has decreased by a huge percentage. Now, how do you answer questions like this, which are on evolving tables? So there is same entity, but the tables are now evolving in nature. So, and this actually importantly said that the information is actually transient in nature and they are constantly updating. For example, my Wikipedia page, if there, it will always change after a few years because I have something added, something deleted, and something remaining constant. So how do I reason on such evolving data which is there? And this is true for any company data or any other clinical data also. Like for clinical records, I am working on this with clinical record data also, where the data of a patient record are continuously changing with time. So you have a history of record where the parameters are changing. Your diagnostic tables also have parameters which are changing with time. So, and the problem is LLMs are trained on static data sets. So to reason, actually, you can't just train on all new data coming up. You have to actually let it learn how to reason on evolving data. So we asked this question, can LLM reason on temporal changing in information through in-context learning? So if we just give it the right data, can it still make sense out of it? So, and this is a challenging task because it needs to understand the temporal context, like what is same, what changed, and how much it changed. For example, it has to also ground the question in the right time period. Who was the captain before Rohit Sharma? Now it has to understand where the captaincy is Rohit Sharma. Till when date the captaincy was Rohit Sharma, and before that, who was the captain, kind of thing. It also involves integrating multiple tables. So in this data set, we have around 13 tables, but real data set or real world can have even 100 of tables like this. So the context can go any length as possible, correct? So how do we have consistency over changes and time and consistent performance across multiple varying length of timelines? There can be also subtle changes. For example, the number of tests played can increase from very small amount across tables. So 518 to 544, then 570. So we have to track all those changes which are around that, and which is very easy for model to confuse. Here, a RAG-based approach will be very confusing because all the data is about the same entity, India, and all the keys are almost similar. So model will definitely has to be confused on what he's trying to retrieve and get things. And lastly, if the timeline become really large, there is also context information. How do you reason? So this is the timeline where there is 3 tables. What about 8 tables, then 10 tables, then 15 tables, and maybe 100 data. So some of the diagnostic data which I'm working on has even like 100 entities of records. So how do you reason on such kind of thing? So first of all, we thought of like simple approaches for doing this. We created first the benchmarks to study this. So we take info boxes, we take their history. So Wikipedia allows you to look at historical updates of all the pages. We get them, we clean, we check changes in them, we populated them. And then we have a human which can create a lot of templated questions, and we initialize with all these info boxes across multiple of categories. So finally, we have around 4,000 questions, around 1,200 categories, and around 14,000 plus tables. So each question has around like 10 to 12 tables of timeline which we are working on. Some has even more, like 30. Then we look like how kind of questions which we are creating. So we create a bunch of implicit questions because they are more challenging and more interesting, and what is really asked. We never ask very explicit factual information because they are generally present in one table or something there. What we ask is the temporal changing information, how it is. So we created around 3,000 implicit questions and around 1,000 explicit questions. Implicit question, like for example, who was the captain when India won the World Cup? And explicit is when you ask who was the captain in 2020, where you exactly give it the time when you are asking the thing. We have reasoning which are multiple, so we have all kind of reasoning or extraction, minimum ratio, everything. And we have complexity from single key questions. So around 2,000 questions require only reasoning on single key. Around 2,000 require reasoning even within a table, multiple keys. So it's asking basically about multiple rows in the table, how it's reasoning and all. So first we look at how this data set should be there. So we thought of why this direct chain of thought kind of prompting approach doesn't work on this. So we found that, let's assume this question: who was the coach of the Indian cricket team when Virat Kohli was captain and the team has its highest ICC test ranking? Now it has 3 pieces of information linked to 3 different times, and they are interconnected to each other. So it has to process the full timeline of the table simultaneously. It must identify all these things: when somebody was a captain, what was the coach at that time, and what was the ranking at that time. And then he has to do all the temporal correlations across this multiple attribute at the same time to reason about the thing. Now this become a very challenging task if you do try to do all of these at once. So without decomposition, all above need to be handled at once, which become a very super challenging task kind of thing. So we thought of why not we just decompose this task. So we thought of this as like decomposing in the form of like 3 ways. So what is needed to answer this? We need to find the right tables. So identify and retrieve the tables from period where somebody was a captain. We need to identify what is the right keys which is there in those tables, like captain, coach, ICC test ranking. And then we have to link them, identify when it is highest for one, and the link when the other things are there, and then finally answer what is the coach value in that thing. So this way we are able to systemize the thing and do better. So this we call retrieval, extraction, and generation can actually make this problem much easier to solve. And so we decompose this into multiple level of decomposition and try how these decomposition. So one decomposition, we just do a right table retrieval and then try to solve the problem. One decomposition, we say, forgot about the table, we just try to find the right keys which are there. For example, in this case is the captain, coach, ICD test ranking, and then the thing. And the last one, we do actually the same whole process iteratively. We first find the table, we find the keys, and then we generate the answer which is there. Obviously, we find that the last IRE approach really works better, which is first retrieving the table, then extracting the key, and doing better. So in fact, the performance was improved drastically for GPT-4o, but then for some models, we didn't find much improvement. For GPT-4o mini also it improved, but for Gemini 1.5, it was not there. We even find that for Oracle baselines, even Oracle, if you give the right tables, like everything right, it's still having an issue to do that task. So that means this is a really challenging task. Where the human baseline was around 80, 82, the models were struggling on this task. And we also see if there is temporal tuning we can do to do better on this task. So we take some temporal model like TMO, Time Llama. So all the temporal models which are fine-tuned are actually small models. So we check similar kind of model, does it improve? So yeah, it do improve like Llama and Mixtel a bit more, but still the performance was really worse, like 30, below 30 things. So we were not even able to improve the Llama 70B billion. So that shows that the task is really difficult, and scale do matter if you try to directly solve this task. So now my question in the real world is, how do we do this task even when we have a very small LLM and still we want to do? Now again, the answer lies we can use neurosymbolic approach to do that. So we recently tackled this problem. This is under review, recently submitted, where we actually look at, can we convert this schema format into a database schema in a 3NF form. So basically what we did is we transpose this table and basically merge all this table into 3 to 4 multi-attribute table. This is all done by LLM. We just give it instruction on transposing the table into 3 to 4 multi-table attributes, and then again use the SQL and do it. But this itself will not be enough because these are complex table and varying structures. The schema might have issues, the SQL might not be, because SQL are very rigid. If you don't get the right exact SQL, it will not even execute. So we also put the reinforcement learning of refining errors, which includes self-verification, self-consistency, and the reward model to further improve this task. And this actually, we are able to now outperform this data by huge margins. So this was the information retrieval and extraction results, which was the last baseline which I showed. Compared to that, we were able to actually cross now 80 and reach somewhat like a human level performance for at least some of the model. Again, for very small model like Llama 8B, we were again in 64, 65, which is much better than 48, 30 and other data. But still it's like 10, it's around 12 to 34% better, which is a huge number. But still it's not able to the human performance like 80. But for very large model like Gemini 2.5 Flash and all, we were able to do much better on this stuff. Lastly, we also avoid like the schema transformation actually really works with very large models. So if you put very small model, the schema transformation gets really hurt. So that's why the Llama 8B was not able to do well. But one good part is if you do a transformation with a good thing, and you just need to do for one table, you can generalize it for other things. So you have to do it for one table, and then you can initialize all the tables in that category in the same way. And that can be rule based and a code generated by LLM, which can execute on all the tables. And if you do that, then even for small Llama model, the SQL generation, you can use even very small models. So you can use Llama 3.18b to generate the SQL on the schema, and Llama 3.370b or even like 22.577b can give you a very good number, which is there around 78% compared to 80%. Even for Llama 3.370b, we were able to get around 78, 75. So this shows that the transformation to a schema and reasoning over the symbolic state without looking at the data is much more robust than this. So we also have some robustness studies around this, where we show that this also leads to better generalization and better guarantees on counterfactual, large and small. So right now we talk about mostly entity tables and evolving entity informations, which are complex and semi-structured in nature because they can have a table in a table, different kind of values. But there is already a lot of table data sets which are hybrid in nature. There are multiple table data sets. They have different structures. So what we thought of, can we take a very grand challenge of solving the web table temporal reasoning? So what we did is we take all the table data sets which we know of. Obviously, this is not complete. There are much more data sets, but we took lots of most popular data sets and extracted the temporal questions in them. So we use clues like before, after, and all the temporal clues and LLMs to extract all the temporal question out there. Now we see that this data set has very wide variety of data. So there is long form QA, there is hierarchical tables, there is hybrid tables, which mean as a table and a text like this kind of thing. There is long form question where the answer is basically a sentence. There can be finance table, there can be non-finance tables, FinQA, TATQA, finance table, there can be numeric data set. So it contains all kind of reasonings also. So it is very diverse in the table structures as well as very diverse in the other very diverse in the table structure as well, very diverse in the reasoning of the questions around it. All of them were temporal question, but the reasoning beyond the temporal was different. So we try a lot of prompting techniques to first see how does it work. We include a clear approach. Narration of thought is another temporal prompting approach. We include some direct prompting approach, which are like evidence extraction, decompose prompting, faithful chain of thought, program of thought. We also discovered some agentic or structured prompting approach, like self-discover, self-ask, plan and solve. And then some agentic approach like tree of thought, graph of thought, self-consistency approach. So one first observation we find is when you use all this prompting and try to, especially the direct prompting, like these are the, because all of the prompting are somewhat like a combination of these prompting happening in ways. So either you are decomposing, you are faithful reasoning on it, or you are generating a code, or you are extracting the evidence. So this actually can generate all the above prompting technique which is there. So we look at how these things are there. One interesting thing found is like across data set, there is no best prompting technique. So the prompting, the best result you get with different prompting for different data sets. Even within the data set, some queries will be answered by some prompting tempting correctly, but for other it was not answered correctly. And then these all patterns vary across LLM. So the best prompt for each data set also vary across LLMs, and the prompting technique was best was also varying this. And within the data set also it was varying a lot. So this shows that there is very hard to get any universal prompt which can do better. So we thought of, can we do something better by unifying all these prompting technique and do? So we did this work of unifying reasoning through adaptive prompting for temporal table reasoning. So the first challenge we find that is the data is very varied across these data sets, correct? The table is different, the reasoning is different. We thought of how can we solve this task. So we come with a CF adaptive prompting, where we first ask model to actually reason the key steps without solving the question. Just think about how do you solve this things and what steps is needed to solve this problem. Then we basically ask to refine those steps and comprehend the selected step which you have. And lastly, we ask you to now take all this step and create your own prompts, which you can use to answer this question. So execute the structure set to derive to the final answer. And this actually helps Furthermore, we also find that the table was varying so much even within a data set that the model was not able to comprehend well even within the data set. So we thought of, is there a way we can unify or clean out or correct the data set? So we do a table refactoring where we ask it, the LLMs, to do not change any information, enhance the semantic. For example, the unit was missing sometime, the percentage was missing, sometime into 100 was missing. Sometimes the date was formatted in multiple different formats. So we use this table refactoring to actually unify all the table into a single format. And this we also used to use in later like neurosymbolic approaches. Now you can use the SQL will work actually well on these tables also because they are unified in a single format. So for example, this was one of the data set, I forgot which one, but then the title was missing. The column was having incomplete aspect or not full name. So the model actually tried to fill. It do bring some of the errors. So for checking that, we actually do a auto consistency where we check, okay, this table versus this table, how much change is there in the semantic way. We found that 99% it was good for theta fin. For some data set, it did hurt. Like for example, multi Herat, it was 88%, and hybrid, it hurt the most. And that's why the performance on hybrid was also not good for our approach. But then it was able to do well. So, and also we find that different data set did different things. Like for example, table structure was issue with theta fin, which was theta has all kind of issues, but other data set has some other issues which are lesser, but some other issues missing. So overall, we find that there were table structure fixed, title clarity was done, row column headers was enhanced, the data was rightly formatted. For example, the dates and unit, and then the emphasis and the border was also make right. Sometimes the border was not properly done, and then there are small other things also which we have. Finally, we also, so now we were using 3-step prompting, but can we also do all this in one step? So we write this simple prompt where we have one step of thinking about the problem first, selecting a series of steps which it can do out of these, creating a reasoning process around it, and then generating the prompt and doing it. So this approach actually, so our approach CR unified actually outperform all other baselines. So this is average across all data sets. You can see like it's all also outperform self-discover. So self-discover is also a close baseline to us. It's also try to discover the best prompt to solve the approach by repeatedly prompting. So we were ever seeing that CR unified and CA unified plus refactoring was able to do outperform this thing. Furthermore, most interesting thing was like across each data set. So averages hide a lot of things. So if you just look at each of the data set, you find that it was one of the top performing baselines among all of these. So either we were first, second, or we were at least in the top 3 baselines which were there in that thing, except for hybrid K. And one reason for not doing on hybrid K because the table refactoring didn't do well on this. And also hybrid Q has much more complex data set where each cell has a hybrid text associated with it. It makes it even more challenging to do well. We had the clear approach, which is just direct reasoning with multi-steps, were able to outperform all of the baselines. So there were cases where narration of thoughts was outperforming, for example, in high tabs and this, but we were also very close. And then at some places, the narration of thought was actually totally failing. For example, a data set like Squall, where the SQL is kind of generated, or something like a TAT-QA, where it was not doing really well. So the CR approach, which is in orange, actually was there in the top 5 approaches. So lastly, I will like to wrap up my talk and have the takeaway. So temporal reasoning or static table or evolving table timeline is harder. So there is a lot of variation in table structure, question complexity, and reasoning, which exaggerate the problem which we have. So prompting techniques which we introduce like clear or cross fine-tuning on different other temporal data set can do help, or CR, which table refactoring can benefit, but they do not work for open source model that much. And then they do improve robustness, but they do not guarantee that the robustness will sustain over counterfactual, long, or any other new table data or slight variations of the data. So using neurosymbolic approaches where you convert the table into a structured schema and make the reasoning data agnostic for generating the SQL, maybe a better approach to do that. Here the catch is how do you transform the data into a SQL ready format and then reason on them. Furthermore, you can also enhance this with self-verification, consistency, and weak reward RL, where you don't have the SQL with you and can outperform. So I will also lastly want to thank this all work is done by multiple students. So this is my lab. This is all my students and many more who are collaborators in this papers who actually did the whole work and Thank you.
Thank you very much, Vivek, for your talk. Because we are running out of time, but we still have time for a couple, one or two questions, I guess. Any questions from the audience? From the room?
I think we don't have questions here for now.
Okay, maybe I ask a question. When you talk about, for example, the temporal reasoning part, you have the questions, right? And then you have the table come into play, which can enrich the model to provide some answers. But my question is, what's the advantage of, because temporal reasoning, so for example, the model can be enriched by incorporating knowledge graph, for instance. But what are the advantage, for example, comparing the method like the table plus models and versus compared to the knowledge graph?
Very good question. So why we need table reasoning? Why can't we just use LLM and like do a RAG kind of thing? So many of the, even if you do RAG, like you have to retrieve the data. And secondly, like this I have shown on Wikipedia data, which might be in the model, no, but like I have applying this on now medical data, which is a clinical record data, which I cannot share, or you cannot have LLM train on that, where you have to actually have the record given and the model has to reason on the record which is there. It cannot actually learn or use the data itself. You can obviously convert the data into a knowledge graph and then try to reason on that, but then that conversion should be lossless and good. So what we thought of is,
it seems to be working. So with that, we can begin the last session of today. So there will be 4 presentations for our presentation, and we will start directly with Mehan, who will speak about the test of time that we already had either before. Let's go to you.
Yeah, okay, so hi everyone. Yeah, so this presentation was given in, earlier in the day as well. So for some of you who heard about that, apologies for repeating some of the content, but I will try to move over it fast. So we know that we have a lot of structured data in the world. We have social networks, knowledge graphs, and many other types of data that are inherently structured. And most of the times we want to build applications on this kind of data, where we want to be able to answer temporal questions represented as text over these types of structures. For example, given a knowledge graph, we want to be able to answer questions such as, which team in the Premier League has changed more head coaches in the previous 10 years? And in this work, we we want to study how strong are large language models in answering such temporal queries. If we look at the existing benchmarks, we see that there's an overemphasis on measuring model performances on temporal knowledge graphs. And this is fine to some extent, but it will also bring some limitations with itself. One of them is that it will conflate temporal reasoning with the ability to recall facts. At the end of the day, we don't know if the model is actually good at reasoning and understanding temporal facts, or if it's just recalling from memory. It will also neglect the fact that in many applications, we have very diverse graph structures. It's not just KG style structure, and it will overlook the fact that for answering temporal questions, we need to be able to do a lot of time. We need a lot of time arithmetic skills. So as an example, if you look at this prompt, given the list below, who was the Chelsea coach before Pochettino? If you are a football fan like me, you probably don't need to look at the list. You just know the answer. It was Frank Lampard. But if you don't know it, you can probably go through the list and you can reason about it and then come up with the answer. Now, if I give you this prompt instead, it's the same prompt, just the names have been replaced with generic entities. This time you cannot remember it from memory. This time you actually have to do reasoning and find out what the answer is. So when we tried this about a year ago, when we were writing this paper, we saw that the model behavior is like this. When we give it all the facts with the names, it can give us the correct answer. But when we give it generic entity names, it makes a mistake. So this is kind of showing that on the left, the model is probably just answering by recalling from the memory, but on the right side, when it actually has to do reasoning, it's failing. So motivated by this, we created the test of time benchmark to focus specifically on reasoning. And we believe to doing temporal reasoning. One of them is understanding the semantics of time, things like what it means for something to be before or after or first or at the same time. And also the other aspect is time arithmetic, the ability to do mathematics on temporal data, on dates and timestamps and stuff like that. And we created two subsets of our benchmark, TOT semantic. This is focusing on probing the model's understanding of semantics and logic of time. For this, we generate some random graphs given different graph generation algorithms. We assign entity and relation names. We textualize the graph into some prompt that has temporal facts. And then we generate different types of questions, single hop or multi-hop questions on top of this. And for test of time arithmetic, we started with a seed set of examples, and we had some annotators going through that and expanding the set. And then we filtered the bad ones. We categorized it into some nice categories so that we can see how well the models perform at doing various types of temporal operations. So now showing some results. So if we look at this question here, who was the R1 of E1 before E5, and we have some facts, we can probably spend just 30 seconds looking at these facts and coming up with the answer. And now if I give you this other question, which is the same question, just the order of the facts is different, the answer should be the same. As a human, we know that the order of the facts don't matter. But when we try this with our models, these are some results averaged over 5 different models. We see that the performance of the models highly depends on the fact ordering. In fact, if you shuffle the facts, then the models tend to do quite bad. But if you sort them in a way that makes things easier for the models, they will do much better. So on the application side, what this means is if you want to build an application, try to optimize the ordering of your facts. On the research side, I guess what it means is we should do a better job of teaching our models that the order in this kind of data doesn't matter. Result number 2, so if I give you this question, when did E1 start to be the R1 of E2? And there's a fact that states what the time was. It doesn't matter if I give you 20 other irrelevant facts or if I give you 2 million irrelevant facts. We know, as humans, we know how to find the correct answer. But with our models, that doesn't seem to be the case. It seems like when we increase the size of the graph just by adding irrelevant facts to it and irrelevant nodes, the performance of the models keep decreasing. And this is another failure mode that we should focus on, and we should try to teach our models to not focus on the irrelevant data, but focus mostly on the relevant bits of the context. And lastly, it seems like the graph structure, the underlying graph structure of the data is quite important. So we have been focusing very much on knowledge graph data. And as you can see, the last column here is a subset of the data where the underlying graphs are coming from Wikidata. We can see that on those kinds of graphs, the models perform much better compared to other types of graphs. And this is showing that we should also try to teach our models that it doesn't matter what the structure of the graph is. They need to learn how to do the reasoning on top of these facts and come up with the correct answer. And finally, on the temporal arithmetic dataset, we observe a large headroom for the models to be closed. It seems like there are categories where the models are good at, like time zone questions, but there are also some categories such as duration where the models are not doing well. and we need to do a better job of teaching our models how to deal with such questions. So you can find the data online. The original data set is available on Hugging Face. And if you are looking for more challenging versions of the data, because this is now 1 year old, you can find much more challenging versions of the data under Big Bench Extra Hard. So if there are any questions, I'm happy to answer.
Do you have questions online?
Hello. I have a small question. You are talking about quite several challenges for temporal reasoning, like in the graph format. But do you have comments on, for example, what set of the technicality would be potential, the right recipe to solve these problems?
Oh, you mean for these kinds of graphs?
Yeah.
So the easiest one would be maybe just some, in terms of data, because I have a feeling that a lot of data that is being used for training models for these kinds of tasks are knowledge graph style data. And because of that, the models are better at learning to deal with those kinds of structures. But maybe it can be as easy as just changing the data mixture to make sure all of these types of graphs are represented. The other way is to even change the way we do things. And instead of feeding text to these models, having a separate GNN model that can operate on the graph, that has the graph inductive bias, that can operate on the graph and kind of synthesize it and put it into the prompt of the model. And then the model can just use the summary generated by GNN. By doing this, we will bypass all of these problems potentially.
Thanks.
Okay, if there are no more questions, then we thank you again.
Yep.
And the next speaker is online or can maybe the next speaker share the screen?
Yes, just give me a second to
Yes, no problem.
present it.
Okay, great.
Can you guys see
Then
my screen?
we can see your screen, and you can go. Thanks.
Okay, perfect. Hi, everyone. Thank you so much for having me here today. My name is Sangmitra Madhusudan, and today I'm going to be presenting our work, Fine-Tuned LLMs are time capsules for tracking societal bias through books. So the motivation behind our research follows the idea that books are an extensive source of information, which makes datasets derived from them, such as book corpus in Project Gutenberg, extremely valuable for training large language models. So while existing and pre-trained models already perform very well on writing tasks, it has been shown that fine-tuning them on book-based corpora further enhances their performance on various writing tasks, such as text summarization or genre-specific content generation. However, books can contain biased content, and utilizing them for pre-training or fine-tuning language models can lead to bias perpetuation, often manifesting in model outputs. While existing methods analyze the biases that are present in text-based corpora, gaps persist in understanding exactly how these biases vary across various historical periods. So to remedy this, we introduce a novel methodology for historical bias analysis by utilizing the fine-tuning and prompting capabilities of large language models. We developed BookPage, a decade-stratified corpus of 593 fictional books spanning 7 decades, and by applying a novel methodology to BookPage, we provide a detailed analysis of societal biases in 4 demographics. Further, we provide evidence that the biases that we see displayed by the fine-tuned models are independent of their model architecture and instead primarily influenced by the content of the books that they were fine-tuned on. So let's look a little bit more at BookPage. Our BookPage corpus D contains decade-stratified subsets from the 1950s all the way up until the 2010s, where each decade-stratified subset contains books that were popular between the years of that decade. So for example, our 1950 subset contains books that were popular between the years 1950 to 1959, with each book containing its title T as well as its complete content C. Each decade-stratified subset of BookPage contains between 64 to 97 books, and these were collected depending on the availability of books online for that specific decade. Perfect. So for our framework, for fine-tuning on BookPage, we fine-tune pre-trained language models on each decade-specific subset of BookPage. So that results in 7 decade-specific fine-tuned models. Now for fine-tuning, we format the content of the books into a sentence completion task. So for example, consider this book, Lord of the Flies by William Golding, which contains the following excerpt. So for fine-tuning, we format this excerpt into a sentence completion task by prefacing the first couple tokens of the excerpt with complete the sentence. And this forms our instruction, while the rest of the excerpt forms our expected response. And together, these are used as an instance for fine-tuning. Now, to validate that our fine-tuning strategy actually works and that the models are able to capture the content that's present in the books, we create entity eliciting prompts, which are sentence completion prompts that are designed to elicit entity-rich responses from models. So for example, one of the EEPs we have reads, complete the sentence. I went to school to finish my assignment. I was met with an angry librarian who asked me my name. I said, the aim with these entity eliciting prompts is to urge the models to complete the sentence with an entity, so a name or a place. And this helps us because we can extract these entities from the model response and compare them to those that are present in the dataset to see how much of the nuanced content the model is able to capture. So let's look at that in action. So our first step would be to perform named entity recognition on a decade-specific subset. This will give us a decade entities. We then use our entity eliciting prompt and prompt the corresponding fine-tuned model for that decade with it, and perform named entity recognition on the model response to get our model entities. We then compare these decade and model entities to then get our count of the total number of matched entities. We use this to compute the entity overlap score. So for the entity overlap score, we run each EEP n times, and using the methodology I described in the previous slide, we compute the percentage of common entities for each run. We then add all of those up and divide that by n, which is our total number of runs, to get the entity overlap score for that specific EEP. So for example, let's consider our 1950 subset, which has these 3 decade entities. For our purposes, let's assume that we run our fine-tuned model 3 times on this specific EEP. For each run, we compute the number of common entities between the model response and the decade entities. We then divide that by 3, which is the total number of runs, to get our percentage of common entities. And then we add all of those up and further divide by 3 once again to get our entity overlap score for this specific EEP. So this entity overlap score is an indication of how well the model has been able to capture the nuanced content that's present in the books. So now that we've validated that our fine-tuning strategy works and that the models are able to capture the content that's present in the books, we can then move on to bias analysis, for which we create role-specific elicitation prompts. Now, these are also sentence completion prompts, but they are designed to uncover biases towards specific societal roles within a demographic. So for example, one of our REP reads, I normally go to work, and while I am gone, the house is cleaned and maintained by. This REP was written within the demographic of gender to target the societal role of a homemaker. So for a demographic D, we create a set of REPs where each REP has the following structure. So if we go back to our example, the role is that of a homemaker, the demographic is that of gender, while the scenario is the complete sentence that targets the societal role of a homemaker. We then use these REPs and prompt our fine-tuned models with them. And on the model response, and from the model response, we try to see which sub-demographic was targeted to fulfill that role. And for that, we use GPT-4. So if you see in this response, we see that a woman was targeted to fulfill the role of a homemaker. We repeat this process 50 times for each of the REPs we have, and this gives us a nice frequency for each sub-demographic. And any skew in this frequency would suggest a bias in the model for that specific role. So for example, for this REP of our homemaker, if I prompt the 1950s model 50 times, and 80% of the times it's associating the role to be fulfilled by a woman, it shows that the model is showing a gender bias for that specific role. So we repeat these experiments across 4 demographics: gender, sexual orientation, race, and religion, each of which contain the following sub-demographics. For each demographic, we create 5 REPs, and with the exception of the sexual orientation demographic, for which we've created 6 REPs to ensure a comprehensive coverage for all of its sub-demographics. For models, we've performed our experiments on the following versions of the mixture, Llama, and Gemini models, with each of them being fine-tuned on each decade-specific subset of book page using the fine-tuning strategy I described previously. For fine-tuning validation, we perform our validation on the 1950 subset of book page, for which we create 10 EEPs, each of which are run 100 times on both the fine-tuned version of that decade, fine-tuned model of that decade, as well as its pre-trained counterpart. Okay, so now let's look at some of our results. So the first table here I have displays the entity overlap percentage of the pre-trained and fine-tuned versions of each of the models that we've analyzed. Here we see that the fine-tuned models display a significantly higher entity overlap percentage when compared to their pre-trained counterparts, which suggests that they've been better able to capture the nuanced content that's present in the books, which makes them suitable for analyzing the bias that's present in these books. So for these biases, this table here shows us Llama 3's responses for REPs targeting the for REPs targeting the roles of CEO, woman fiance, mathematician, and defacing monument. Here we see some really, really interesting trends. So for example, if we focus on the CEO REP, we see that over the years, there's an increased representation of women in leadership positions, with an uptick occurring around the 1990s, coinciding with the third wave feminism movement. We see similar results for the woman fiance prompt, where there's an increased representation of homosexual relationships over the years, with an increase occurring between the 1990s and 2000s, which aligns with broader movements such as the decriminalization of same-sex marriages. This graph here shows us the same result that was in the previous table, but just for the prompt of defacing monument. This helps us to visualize the result a bit more. So here this prompt reads, the person accused of defacing the public monument was reportedly from the religion of. Here we see that over the decades, there's an increased representation of Islam with such negative portrayals, while other religions experience a decreased representation. Now, this aligns with other broader literary analyses that show that there's an increased negative representation of Islam in contemporary literary fiction. And these findings are consistent across all the models that we've analyzed. And this suggests that in this sense, the fine-tuned models are effectively able to act as time capsules in that they're able to capture and also reflect the evolving societal biases that are present in the books over the decades. Perfect. So now let's look a little bit at bias variability. So this radar plot here just shows us the standard deviation that each demographic experiences. Higher the standard deviation, it just means that there's a higher frequency mismatch between the subdemographics. So here we see that sexual orientation and gender are the two demographics that experience the highest bias, while race experiences the lowest bias. And that could mean that there's either a more balanced representation of racial content in the books or a complete absence of racial content in the books. But the other important finding from this radar plot is the consistency of this result across all model families. And this suggests that the biases that we're seeing are primarily influenced by the books that these models were fine-tuned on. And this is further supported by this table here. So this table just shows us the average percentage of responses for each REP in the gender demographic for all of our models analyzed. And here we see that all models show consistent patterns. So for example, all models increasingly associate women to fulfill the role of a homemaker and also that of a nurse, while they increasingly associate men to fulfill this role of a murderer. And these findings are consistent across all the REPs in the other demographics as well. And this result, along with the radar plot shown previously, confirms or further supports our claim that the biases that we observed are primarily driven by the content of the books and are independent of model architecture. So to conclude, we introduced a novel methodology for analyzing historical societal biases by utilizing the fine-tuning and prompting capabilities of large language models. We developed BookPage, a decade-stratified corpus of 593 fictional books, and by applying our novel methodology to BookPage, we reveal temporal variations in societal biases across 4 demographics. Finally, we demonstrated that book content and not model architecture drives bias profiles. Thank you so much. I'll take any questions now.
Thank you very much. Do we have any questions in the audience? No, it doesn't seem we have questions here. So first, maybe I can ask, you looked at the outputs of the models. Mm-hmm. So just like the words that were produced, did you also look at the probability distributions that the models were producing?
No, we only looked at the response distribution of, the responses that the model produced. And we did so because if you see in our RDPs, I don't know if I can go back, but we carefully designed them to kind of omit any patterns such as who do you think would be better suited to fulfill the role of a homemaker, a man or a woman. So kind of those binary or those prompts that give away the fact that we're trying to test the model for these specific biases to ensure that we make it more open-ended, in that the model is just naturally completing those sentences. And from that, we can see which specific subdemographic it's targeting for that role. But we did not look at any of the internal probabilities.
Do we have further questions? No. Maybe in online?
Yeah, I have questions. So when you talk about the bias, historical bias, I understand the bias that's encoded in the book that you use large language model to query these biases, but you assume that the biases are like are distilled from the book content. That, for example, let's say the book published in the 1950, right? Then you look at the bias over 1950, right? And this is the point in time that you find the bias at this particular decade. But the book may, for example, the book published in 1950 may talk about the events in the distant past, for example, in the 18th century, right? But if this issues applies to the setup of your experiments, maybe do you have comments on this?
Yeah, so that's a good point. But the focus of our work was to capture the evolving societal biases, so for which we've used best-selling books. So the difference is in the fact that the bestsellers, as has been shown by literary research, they capture the mainstream societal attitudes of the times in which they were popular. So if a book is a bestseller, it means that it has resonated with the perceptions and the preferences and the attitudes of the people at the time. So for example, and also if a book was written in the 1950s, its content is, for example, set in the 1800s, it doesn't necessarily mean that the reflection of that book is not contemporary. So for example, one of the books we have in our data set, I think we only have 12 such books which have a historical kind of representation different from the time in which they were written. It's called All the Light We Cannot See, and it was written in the 2014s, and it was popular in the 2014s, but it talks about the World War II, so it's set in the 1940s. But it provides a kind of a story of this boy who is German, and he's forced to kind of be a Nazi soldier. It follows his journey of how he feels a lot of guilt in doing the tasks that he's been wanting to do. And if such a book was written in the 1940s itself, I don't think it would gain popularity because of the sentiments of the war at the time, and people wouldn't be resonating with the content of that book at that time. So the important distinction is for us to focus on, is our focus actually on bestsellers as opposed to just picking any books that were written in a specific time, because these bestsellers kind of give us this lens of the societal perceptions that people had at the time and what people were resonating with, what content they were consuming, and what they had, what preferences they had at the time. Does that answer your question?
Yeah, thanks.
Okay.
Thanks. Maybe we will move to the next talk. So we need a few minutes to set it up here. Yeah, it's that. Yes, you have to do it.
On Teams.
Teams, yes.
Oh, well, on Teams.
Yeah. You have the link.
Yeah. The email that you sent. I'll just send the link to myself.
Equation.
Yeah.
Okay, we are here.
Yeah, exactly.
But then it's not presenting that there, right?
Okay, maybe you can mirror your screen. Because, yeah, she wants to have both. Maybe easier for you to present.
Yeah, okay. So let me share the screen and then start.
All right. It's like screen.
This one, I guess.
I think so, yeah. Okay.
It works.
Can you hear us online?
But I can't change the slides here because it's presented there.
Yeah, we can see the slides
There you go.
and
Yeah,
we can
exactly.
hear you.
So we're good. And then
We will just have to look there and talk, right?
basically. Yeah.
I have
Oh, there you go.
Oh yeah, okay.
Nice. Online, can you see the screen?
Yes, we can.
You want to do first half, second half?
First half.
Okay, so I think if it's all good, we will just start this. I think it's fine online. Yeah, so I'll let you guys do the presentation about the context is key, a benchmark for forecasting with essential textual information.
All right, great, awesome. Ready to go?
Yeah.
Test. 1 2 1 2 test. 1 2 1 2. Ground control to Colm. Okay. Hi, everyone. My name is Andrew. I'm a PhD student at Mila and University of Montreal, and this is Arjun. He is also a PhD student at Mila University of Montreal, and we work at ServiceNow. And this work was done in the context of ServiceNow. You can see the full list of authors over here on the right, and at the bottom, we'd like to thank Fanny Rancourt for helping with the design of the presentation, and we'd like to thank this incredibly tenacious audience for still being here with us. So thank you very much for toughing it out. Yeah, let's get started. Okay, ServiceNow makes us say this. It's a safe harbor notice. So we don't know what we don't know. This is research. Please don't base your life decisions on this stuff. But yeah, that's it. Okay, first we're going to go into a bit about forecasting and why context matters in forecasting. Then we're going to go over context is key, the main contribution of this paper, which is a benchmark on forecasting with context. And finally, we'll look at current directions to do this, okay? And at a high level, forecasting is the use of either statistical methods or judgment to try to predict the evolution of key indicators. And it's used to provide insights into critical business functions, right? And that's in the context, what we care about is really that. And the mathematical framework or machinery that we're going to use here is to frame it as a probabilistic forecasting problem. So we have a sequence of observations of random variables x1 through xt, and then we're looking to forecast the we're looking to model the probability distributions of future instances of this random variable from t+1 all the way to capital T. And basically the type of models we're going to consider to do this are machine learning models, usually to model this distribution, right? Yeah. Okay. So typically in forecasting, you usually have a lot more information about the problem than just the data that you're using, okay? Normally, when you think about forecasting, you think about we have like a sequence of variables, as I showed you. You have x1 to xt, and you're looking to model xt+1, and you think about this, and you're like, okay, what model can I apply to x1 to xt? But if you think about actual practitioners of forecasting, they typically use a lot more information than that, right? They know what domain they're operating in. Sometimes they'll model the covariates, but oftentimes they'll have information that they don't quite know how to implement as like a covariate. And so maybe they'll implement some inductive biases in the model, right? They'll decide that like there's a quadratic term or some association between variables that they really want to model, et cetera, right? And our goal is kind of to take a step back and think about if we want to include all that surrounding information, that context, how do we build a model to do this, right? And so that's kind of the goal we're aiming for. And so essentially, when we talk about this notion of context-aware forecasting, what we're saying is that we can condition our probability distribution that we're predicting on additional context, right? And so we just want to open this up, and context in this context is just arbitrary, unstructured additional information that we might want to use to improve our forecasts, right? So in this case, it'll be natural language, but we'll get there, okay? And so the reason that we focus on natural language is, first and foremost, it's intuitive to people, right? Like I could say you can extend to arbitrary context and maybe I allow like images and then you're forecasting and like, what are you gonna do? You have to draw an image? Like, no, that's only applicable in like certain domains and maybe it's really useful for like weather forecasting, you have a radar chart or something like that. But we find that language itself is broadly applicable and it's intuitive to people. And so decision makers can actually just use this and, you know, plug in some language about the problem. And so we restrict ourselves to the setting where this additional context is natural language, right? And we consider at least two types of context. The first is background knowledge, right? Constraints, things like that. Specific things about the problem setting itself, right? So this is electricity data, or this is a photovoltaic power plant. This is a ATM withdrawals, things like that. Right. And then we also consider scenarios that are instances that would be interesting to simulate. Okay, so suppose, you know, electricity transformer breaks down, or suppose that the ATM breaks down, or things like that. And so you can project plausible future scenarios, and this can be extremely useful in business settings for doing contingency planning or things like that. And so that's where we think that context-aware forecasting is really powerful as a setting. And so we're looking for models that can do that and that can use this additional unstructured information. Okay, so the benchmark itself. Let's get into it. How do we make progress on context-aided forecasting? Well, we look around, and despite the fact that we have confirmation from industry and from various experts that like this is useful, and they always use context to model their stuff, right? Because they're trying to inject inductive biases. There really isn't much data around to sort of evaluate this, right? Like one thing you find out is that as abundant as natural language is, actual good like time series data with like additional context, like firms hold on to this for dear life. It's like their most private data, and so like you need to pay out the wazoo if you want some. So we thought we'd build a benchmark that could simulate how well models, especially where the context is necessary. Okay, and this is where the title of the benchmark comes from. Context is key, and it's a benchmark for forecasting tasks, and it requires integrating the textual context with the numerical historical data that's provided. Okay, and this textual context, we make it ourselves, and that allows us to ensure that this textual context is necessary for forecasting, right? That's how we validate it. We're not interested in like scraping a giant data set and maybe the context is useful. We really want the context to be essential so that any model that makes a forecast needs to use that context to make the forecast, right? And so just to reemphasize this point, in the benchmark, accurate forecasts cannot be achieved without incorporating this context. Okay, so let me give you a quick example here. Here you have a history, right? That's the black line over here, and it's example of a task in the benchmark. And then if I ask you to forecast, maybe you make a line, the line goes up, something like that. And I'm going to argue for a second that this blue line right here is a great forecast. In fact, given the history it has, this is an excellent forecast, right? It's kind of, you see it's a little flat before it goes, and then it keeps going. And this is a good forecast. Like a good forecasting model would return maybe a forecast like this. Maybe it could be a bit wider, more uncertain, who knows? The problem is it's extremely off from the ground truth. And that is not the model's fault per se. It's just that there's not enough information contained in this black line for the model to ever be able to forecast the drop properly, right? And so even if the model is good, its prediction is off just because it doesn't have enough information to condition on, right? Now, if you're a decision maker, you can imagine that maybe you'll use this forecast to make important decisions. This might lead you, or if you know intuitively in your heart of hearts that it's not appropriate, maybe what you'll do is you'll just ignore the forecast completely, but then you're losing out on potential information, right? And you're going to go with your gut, which is not always ideal. And so, yeah. If instead what we do is we provide this context somehow, the series contains power production of a photovoltaic power plant in the state of Alabama. Well, what we know is that it's photovoltaic. So as time progresses, this curve is going to go back down, right? There's no photovoltaic energy production happening at night. And so this is actually an off-the-shelf LLM that can forecast this drop. And at the time when we published Context is Key, this was really surprising to us that LLMs could just do this off the shelf. It feels like native multimodality. You're just dealing with time series and context at the same time, and you really didn't plan for it. It just kind of works, right? And we think that this is important because it can help a broad range of users because of the flexibility of the context, right? So even if you don't have like an expertise in the particular domain for which you're forecasting, or like you don't have an expertise in modeling or things like that, you actually can just write out what you're interested in if you have your data, and then you get a forecast going. Okay. So a little bit of information about the tasks in the benchmark. We try to codify the different types of context in the benchmark, and that allows us to get a bit more insight into what types of tasks language models are good at, which ones they're not. And so, for example, one example here is you see in pink, you have historical context. So over the previous 90 days, the maximum power production happened on average at 1122. And in blue, you have what we call intemporal context, which is, this series contains production power, the power production of a photovoltaic power plant in the state of Alabama. Do you want to take over here? It's about 10 minutes, and I think about halfway.
Okay.
Right?
Sure.
Cool.
Yeah. And we also label the context with the kind of capabilities that a model would need to solve the problem. For example, in fact, in the paper, we highlight about 7 capabilities like deductive reasoning, retrieval, causal reasoning, etc. And for example, what deductive reasoning would entail would be something like from photovoltaic, you have to know that after noon, photovoltaic power consumption would go down. That's the deduction you have to make from the context. Retrieval would be something like retrieving from a huge amount of text. And causal reasoning would involve reasoning about the causes and effects of different entities that are specified in the context, and then knowing what to do in your forecast, depending on that. Our tasks are also diverse, as any benchmark should be, across energy, traffic, retail, economics, and all that. In summary, we built a diverse benchmark for context-seated forecasting, where tasks draw from diverse domains with different sorts of contextual information, and then they require different capabilities to be solved. Now, what's the next step? We just benchmark models on it, zero shot. So there are three sorts of forecasting models in the literature. One are traditional models like exponential smoothing and all those statistical models, in fact, that are just simple and fast to fit to the historical data. Then you have time series foundation models, which are just models which are trained on a lot of time series, and they generalize to new time series, etc. And then you have large language models, which are basically universal. They're not forecasting methods, but then they can be used to do forecasting because they're, they just involve prompting. And since context-seated forecasting is a very new field that has only come up in the past year or so, the past models cannot handle anything more than time series, so they cannot handle context. But LLMs you can put anything in the prompt, basically. We built a prompting method to use LLMs. It's super simple. The prompt is given here. I have a time series forecasting task for you. Here's some context, factor it. Here's a time series in that format. And now please predict the value, return the forecast in this format. That's it. I mean, you can use it for any forecasting task. And that's the expected output. To give you an example, this would be something like within those context tags, you would say, hey, tomorrow the weather is going to be rainy, factor that in. Or tomorrow we're only going to have 100 items of this stock, factor that in. And there's historical time series like that. And then you want to predict the value at the future timestamps after the historical time series. And what we expect from the LLM is to output the forecasts in that format. We also built a metric just for this task. So CRPS is basically mean squared error, but for distributions. And since we care about distributions here because you want uncertainty on your forecast, we use CRPS metric. But since we modified the data so that you have spikes and all that, because context, when you have context like there's a heat wave, power consumption is going to increase 5 times. You're going to have something like a spike right there. Now, when you average out over the entire forecast horizon, that spike might be subdued in your CRPS metric. So we just modified the metric. So half the weighting would be inside the region that was modified to account for spikes or like zero values. Basically, the region that is modified by the context and half outside that region, and also constraint violations. The formulation is not important. It's just that we modified the metric so we can really understand progress in the benchmark easily instead of just gaming the metric, So results of models. Yeah, as I said, we benchmarked a bunch of models. I want to explain this bar chart for a couple minutes. So you have exponential smoothing, which performs at 0.6. Lower is better in this metric, by the way. And then you have foundation models, which are at 0.3. When we test Llama 405B, which was the best model when we published this paper, there are probably better models now, but then we can take these results in the context of the models that were there when we published the paper. Llama 3.1 405 billion instruct was the model we benchmarked, and without context, it does at 0.49. But with context, it significantly improves performance, which means that these models can, in fact, not only do forecasting as well as these models, they can also use context and then do context-seated forecasting. Now, you don't have to look at the numbers, but we have results on other LLMs. Some LLMs do really well, GPT-4o and then Qwen 7b, but some do really bad, even worse than statistical models. But overall, these models can't use context. These can, and LLMs seem to outperform models that have been believed to be the best models in forecasting for many years. So, which sort of signifies a paradigm shift in the kind of forecasting models that exist these days. For example, without context, that would be the forecast, and that's a good forecast by 405B. But with context, now you see that the ground truth is going down because in this case, it's the number of field fire incidents responded to by firefighters. In the winter, the field fire incidents drop to almost 0. You would not know that when you just look at the history. And with the context, the model can perform can basically drop that to 0. And We also made sure there's no memorization problems in the benchmark because we took data after the cutoff dates of LLMs or modified the data heavily so that we avoid memorization related problems. Other examples here, you see that the forecast is pretty good for the history that it has, but then the ground truth is way down here. You don't know what happened. Turns out it was 4th of July, which is a holiday in the US. That's why the ground truth is way off. And when you give that context to the model, turns out it can use it and actually predict that really well. More examples, turns out there's a constraint here. Without the context, the model just extrapolates the history. Again, a good forecast, but not what we want. But with the context that is bounded by 6.29, it can actually bound it there. I don't know if you can see it there, but it was bounded. Yeah. We also have a demo with the ServiceNow instance. Well, basically, why we care about this at ServiceNow is that decision makers can use this and make forecasts that actually impact the business, right? At the end of the day. Now, without any context, this is the number of incidents that are open per week in a ServiceNow product, and that's a decent forecast of it. But we want to simulate different scenarios that ServiceNow might face. One scenario is that imagine that we go out of business and we no longer exist, right? Which means the incidents would drop to 0 because as an entity, we don't exist anymore. And other scenarios, imagine that a major breakage happens, which means the product is not working anymore. People are going to file incidents and it suddenly shoots up. So these kind of intuitive scenarios you can basically simulate with what we call Starcaster here, but it's basically the direct prompt method that we proposed earlier. Yeah, that's the crux of it for ServiceNow. There are many areas of improvement. So robustness, turns out LLMs can hallucinate even in forecasting a lot. So when your ground truth values are at 40 and 30, when you give the context to it, it suddenly goes to 2000, which doesn't make sense for some reason. Without the context, it seems to perform well, but there's some misinterpretation happening here. And this is the GPT-4o model, which is supposedly a really good model. So this sort of precludes people from using it in production, which has to be fixed. So it's an area of research that's open out there. Also, forecasting models have been developed for decades to be fast, especially for high frequency trading and all these applications. But then LLMs are the slowest things that are compared to them. So they're slower by 1 to 2 orders of magnitude. For example, GPT-4o is at 10 power 1, while exponential smoothing is at 10 power minus 1, which is insane. So this has to be also fixed. It's an open area of research if you are interested in working on this. They are also very expensive in terms of parameter count, which has implications for deployment on GPUs and all that. Forecasting models were never meant to be deployed on GPUs because it was supposedly a simple task. But now that we want these capabilities to ingest context and all that, when you want the best model, it's going to be extremely expensive, and that's the best performing model as well. When you want a small model, it's not going to perform well on your benchmark. So we have to close this gap and bring the size of models down while also keeping their performance on the benchmark comparable to 405B and other models. So that's ongoing areas of research that we are also pursuing. There has been a lot of progress in this space of multimodal forecasting since we released the benchmark. So if you're looking to work on this, it's a very active area of research. People are building foundation models and all sorts of things. So please take a look at other papers which came out after us, because our paper is probably outdated at this point. And we also extended this work and built better prompting methodologies compared to just directly prompting it. So including reasoning, and then including taking in prior forecasts with in-context learning, and then improving efficiency and all that. So this is under review at TMLR at this moment, and you can take a look at this if you're interested in the methods that we proposed here, because they have improvements over interpretability, performance, resource efficiency, and so on. There are important future directions that I will just highlight and conclude. So real-world datasets. So we built this dataset ourselves. We wrote the context ourselves because we couldn't get real-world contexts. But if you have good ideas to scrape information and make sure they're relevant to your time series, that would be great. But these probably are behind corporate silos because they're very private. They have private information, basically. Efficient models, as I highlighted, and then performing cost-benefit analyses in real-world pipelines. is the increase in cost really giving you that much benefit, right? And also making sure these models are good at normal forecasting tasks instead of just, context data forecasting. And then agentic interfaces. So models can call other forecasting tools and then perform end-to-end analyses or do data scientific analyses and all that. So these are some future directions. There are much more future directions if you want to work on this field and do research. That is basically it. You can visualize the tasks here. Everything is open source, so you can build on it from the GitHub links. This was published at ICML, and the paper is also online. So please reach out if you have any questions. Thank you. Yeah.
Can you come here and say the question for the?
Or I can repeat it too.
Yeah, or you can repeat it.
I can repeat it here. Yeah, you're right. So in that example, if you had access to more data, you wouldn't need the context. For a benchmark purpose, we built it so that you need the context. In the real world case, that would be a bad example because you can learn the seasonality from data, but it's the benchmark is meant to like just test models on their capabilities as a representative way to like test what they would do in real world in cases where you need context. So for that example, you're right. And in many examples with enough historical data, you wouldn't need the context. But in case you do need it, the benchmark can be used as an approximation of what the models perform like. Yeah. Yeah, exactly. But then when you have scenarios like in the future, there's going to be a heat wave, things like that, then this can be never learned from the history. So all future information, you probably need the context or to simulate scenarios like, okay, what will happen if the stock price of this, goes up and then the whole system changes because of that. If you have historical points where this context is annotated with the time series, you can probably learn this. But then if this is a future scenario that was never seen before, then you need the context. So yeah, that's the thanks. Yeah. You want to answer this?
Sure.
Yeah.
Sure. Yeah. So both the history length and the forecasting horizon are diverse across tasks. So we have some that are extremely short, like 3 to 4 steps, and then some that can go up to hundreds, right, in certain of the harder tasks. Yeah. So the question is how long can we make the forecasting window? And it's a good question, right? One of the big limitations of LLMs is the context window. And when we represent a time series point in an LLM's token space, depending on the tokenizer, you'll use fewer or more tokens, but usually like 1 digit is 1 token for a lot of the common tokenizers. So a single floating point can be 20 tokens, right? And so you very quickly will max out your context window. And that's an open area of research for us. We're testing specialized architectures that can handle floating point representations. And the problem compounds if you go to multivariate problems. Our benchmark is solely univariate. So we don't study whether the LLMs struggle with this like extremely long context, but it's a very worthwhile problem exploring, especially with time series. So, thanks.
Okay, that's it. We can thank the speaker again.
Thank you very much.
I will just quit Teams.
Okay. May I start now?
Okay, yes. So everything is good. We see your slides, so you can start for the last presentation of today.
Okay. Good morning, everyone. Actually, I'm Chen Hao, and Though it is 5 a.m. in my time zone, I'm still excited to share with you our research on the temporal generation of the large language models. It is a relatively straightforward and intuitive paper, and the main aim is to point out an aspect that we believe it deserves more attention. But in this workshop, I think it has got enough attention. The performance of large language models across temporal generation is far from uniform, and they tend to have a bias towards the past. And what's more concerning is that their performance is deteriorating rapidly. Let's dive in. First, we have some definitions. When it comes to evaluate large language models, we need to add a time dimension. So what is the past, present, and future? As you can see in the illustration here, the time before models release is past, and around it is present, and the time after it is future. Now, temporal generation itself can be broken down into two parts. Let's see this picture. The y-axis is about performance, and the x-axis is time. So the gray dashed line is release time. So in the left, it is temporal bias. The blue line means it has a nostalgia bias, meaning the model have a strong preference over the past instead of the current time. And the green line means it favors the present. And then there is temporal degeneration, shown by the dashed red lines. It refers to the decline of the model's performance after its release over time. Okay. Now again, temporal generation has two parts, temporal bias and temporal degeneration. Why they matter? For temporal bias, when we interact with an LLM, we expect it to be in sync with our current time and context. We don't want it to be like someone who has time traveled from 7 years ago. And if an LLM has a strong nostalgia bias, it overly rely on old and perhaps outdated knowledge in some areas. And many of these scenarios may not be effectively addressed by retrieval augmented generation, as they involve a great deal of background knowledge and concepts. Now, onto temporal degeneration. Once an LLM is trained, we assume it to be able to at least make some reasonable inference about the future, maintain their effectiveness over a reasonable time. So in summary, understanding and addressing temporal bias and temporal degeneration is crucial for ensuring that large language models can really meet our needs in this fast evolving world. End of a bunch of definitions. Let's look at some methodology. We proposed an evaluation framework, a fresh bench that is free from data leakage and subjective bias. We does this through two key evaluation scenarios. And first is about compression intelligence. That is, we collect different text from along the time, and basically we measure the loss of the content of the text generated at different times. That is, we use a model to compute the wiki text from 2015 to 2025. And if the loss is low, we say we have different text origins. So if in general the loss is low, we say the model has a good performance during this time. And the second scenario is event prediction. Here we use same prediction websites like Good Judgment Open, and we ask model to predict like human predictors do. They have a question and a short description compared to last presentation. And then the options. The two methods are free from judger bias, and they do not have a judge. They do not have a human judger, and free from data leakage. We are here to talk about temporal generation does not happen everywhere. It is highly related to the specific tasks at hand. See some cases. Here BPC can be understood as a normed loss on text to make it comparable between different tokenizers of different models. Let's start with wiki dataset. Thanks to the sharp eyes of our reviewers, we know that more than 90% of new wiki entries actually focus on historical events. So there is little new things. The growth rate is really slow for wiki text. And let's move into BBC News text. It is news, so it is constantly evolving, bringing new information all the time. Notice that models are most familiar with text around 2018. So earlier and later, the text, they are less familiar and have a worse performance. So this is loss. Lower is better. In general, models' performance remains relatively stable over these two dataset type. However, in archive dataset, we notice a sharp decrease in BPC around March 2024, which coincides with the peak in GPT usage. This might suggest that humans are adapting our writing to LLM output rather than LLM is improving their language model ability. Maybe someday we should use LLM output as we choose. Okay. That's last we have seen the observation of compression intelligence. Now let's move to event prediction. Here are some observations. First, knowledge distribution bias. Almost all LLMs we tested have a notable skew towards the past. And here the past means sometime around 2017. It's not 2023 or 24 as we expected. So it is strongly non-uniform. This means when making decisions or generating text, models tend to rely on very historical data. And in fields like technology and finance, this skew is more significant. And open source and closed source models and model versions comparison, newer and stronger GPT and Gemini versions perform better initially, but declines faster. For mini models, they significantly underperform their full-size counterparts in temporal bias, in temporal degeneration. See some cases. As you can see from the two charts, the performance of models show a downward trend over time, and maybe 0.35 could be random, nearly random. And the key issue is that the degeneration of model performance, and it is unsatisfying peak time. So it is very early. Here 2018, here 2019 for Qianwen. We have been thinking about ways to mitigate this situation. For example, we experienced with a variety of different prompt strategies. Unfortunately, the results of prompting attempts have been rather random, and the performance varies significantly among different models. So here. We acknowledge that SFT could be effective. However, it depends on the amount and the quality of the data source. At that time, I can't figure out a proper database, and today I'm excited to see works like time-aware mixture of language experts. I think it's that name, and some interpretation works like looking into the tokenization at this conference. So in general, it isn't easy as expected, but I believe this area is crucial for long-term progress. So we shall good luck if we continue towards a solution. So thank you. And any questions?
Thank you. We have any questions online? Online.
What do you think of the methodology that would be the right methodology to solve or mitigate the temporal bias and the temporal degeneration?
We believe the strong bias is due to the imbalance of data distribution. So I remember some works show that the pre-trained data corpus is highly about that peak time, that is 2018 around. So I think maybe a more balanced pre-trained data corpus would be the most important thing.
Thank you. If there are no more questions, I think this will conclude this session. Thank you very much for waking up so early and giving us this presentation. And I think we can conclude the program already. Thank you very much, everyone.
Okay. Thank you.